In this course, you will learn how to master the design, implementation, and management of robust CI/CD pipelines on Google Cloud Platform or GCP. You will deep dive into advanced deployment strategies, configuring hybrid and multi-cloud environments, and implementing security best practices to ensure the reliability and security of your software delivery process. So let's now talk about the objectives. So in this course, we'll cover a series of objectives. So we'll start with the process of designing continuous integration and continuous delivery, which is CI/CD pipelines for hybrid and multi-cloud environments. We'll talk about the role of artifact registry in the artifact management process. We will also talk about the differences between deployment strategies like canary, blue-green, and rolling updates. Then, moving on in the course, we'll talk about the triggers for CI/CD pipelines in the GCP platform. Then we will talk about the steps for testing new application versions within the CI/CD pipelines. Then, moving on in the course, we will demonstrate configuring deployment processes, including the approval flow. So when you will trigger a pipeline, then there is going to be an approval that is going to be required. So we will talk about that as well, and we will actually see the demonstration on that. Then after that, we will talk about the CI/CD of serverless applications on GCP. Then as we move along in the course, we will talk about analyzing, auditing, and tracking deployments using tools like Cloud Build and Cloud Deploy. Then later on in the course, we will talk about comparing rollback strategies for CI/CD pipelines. Then troubleshooting deployment issues in GCP. We will see a demonstration on that as well. And then towards the end of the course, we'll talk about the management of CI/CD configurations and secrets. And finally, towards the end, we'll talk about the security of CI/CD pipelines with vulnerability analysis. And we will also look at the identity and access management policies. Let's now talk about the CI/CD pipelines for hybrid and multi-cloud environments. Now, in the fast-paced world of software development, CI/CD has become essential for accelerating release cycles and ensuring code quality. Hybrid and multi-cloud environments offer flexibility and scalability, but implementing CI/CD across them can be very complex and can be very difficult. So, in this particular topic, we will outline a 6-step approach to streamline this process from definition of your objectives to continuous optimization, therefore enabling you to deliver software faster, more reliably, and with greater confidence. We'll now go through a series of steps to define a clear roadmap to harness the power of automation across your hybrid and multi-cloud infrastructure. So let's quickly look at these steps. So it will start with defining the objectives and scope. Then we will assess infrastructure and tools. Then moving on to the third step, which is going to be designing the pipeline workflow. Then implementing infrastructure as code or ISE. As the fifth step, we will talk about implementing security and compliance. And finally, we'll perform testing, optimization, and continuous improvement. So now in this particular topic, we are going to move ahead and we are going to look at each and every step in detail. So let's start with defining the objectives and scope. Now in this, you will need to identify your business goals. You will need to outline the desired outcomes. So for example, it could be accelerated release cycles, improved code quality, reduced manual errors, enhanced scalability, or cost optimization. Then you would need to determine the pipeline scope. You would need to define the applications or services to be included, stages of the development lifecycle, which could be build, test, deploy, and target environments, which are going to include development, staging, and production. Let's now talk about assessing infrastructure and tools. You would start with inventory of cloud resources. You would need to document cloud providers like AWS, Azure, GCP, or even on-premises and specific services. You would need to consider compute instances, which are going to include your virtual machines, storage options, databases, networking configurations, and existing IAC templates if you have any. Then you are going to choose the CI/CD tools. You would need to select a CI/CD orchestration tool, something like Jenkins, GitLab CI/CD, or Circle CI, that will support hybrid and multi-cloud deployments, therefore evaluating features such as flexibility, scalability, integration capabilities, and ease of use. Then the third step, which is optional, is using containerization. Now, if you are using containerization, you would need to choose a platform like Kubernetes that works seamlessly across your chosen cloud environments. Let's now talk about the next step, which is the designing the pipeline workflow. So you would start with dividing the pipeline into stages. So there is going to be source control, which will trigger the pipeline on code changes committed to the version control, which is going to be Git or something similar. Then there is going to be build. You would compile and package the application code into deployable artifacts, something like jar files or container images. Then the next stage would be testing. So you would execute automated tests, which could include unit, integration, or end-to-end testing, and you would do this to validate code functionality and quality. The next stage is going to be deployment, where you would automatically deploy the application to target environments. Then the final stage is going to be monitoring, where you would continuously monitor the health and performance of the deployed application. Then there is configuring workflow logic. You would define conditions for progression between stages, something like success or failure, and implement feedback loops for failure alerts and rollback. Let's move to the next step, which is implementing IAC or infrastructure as code. In this, you would use the IAC tools such as Terraform, CloudFormation, and Ansible to define and provision cloud resources consistently across environments, therefore ensuring uniformity and reducing manual errors. Then you would also perform configuration management, or you would use configuration management to manage the CI/CD tools and pipeline configurations with IAC for easy updates, scalability, and disaster recovery. Let's now talk about implementing security and compliance. So in this, you would secure secrets, you would implement secure mechanisms for storing and managing sensitive credentials such as API keys and passwords by using tools like HashiCorp, Vault, or cloud-native solutions. You would also perform code scanning and analysis. You would integrate static code analysis, vulnerability scanning, and dependency checking tools into pipelines to identify security flaws early. Then you would perform compliance checks. You would enforce compliance with industry standards and regulations. For example, it could be GDPR, HIPAA, or PCI DSS by including relevant checks in the pipeline. Let's now talk about performing testing, optimization, and continuous improvement. So in this, you would test thoroughly. You would test the pipeline rigorously in all target environments to ensure smooth operation and reliable deployments. Then you would monitor performance. In this, you would continuously monitor performance metrics. It could be build times, deployment times, and test results to identify bottlenecks and optimize efficiency. Then you would use feedback loop. You would gather feedback from developers and stakeholders to refine the pipeline and address issues. Then you would work with phased rollout. You would gradually introduce the pipeline to different teams or projects to minimize disruption and allow adjustments. Then there is perform iterative enhancements. You would continuously monitor and refine the pipeline based on feedback, changing requirements, and new technological advancements. Let's now talk about the key considerations for hybrid and multi-cloud. Now, in the hybrid and multi-cloud environments, you would need to keep in mind some of the considerations when you are dealing with CI/CD pipelines across hybrid and multi-cloud environments. So one is going to be the portability. You would need to design a CI/CD pipeline to be portable across different cloud providers by using cloud-agnostic tools and standardized infrastructure definitions and avoiding vendor lock-in. Then there is going to be networking. you would need to plan and configure networking between on-premises and cloud environments to ensure secure and efficient communication across these environments. Then there is data transfer. You would need to consider the cost and latency implications of transferring data between cloud providers or between cloud and on-premises environments. Now, just to quickly recap, in this particular topic, we talked about designing CI/CD pipelines for hybrid and multi-cloud environments. So we talked about various steps that you have to perform. So it started with defining the objectives and scope, then assessing infrastructure and tools. Then we moved on to designing the pipeline workflows, after which it was followed by implementing infrastructure as code or IAC, then implementing security and compliance, and finally performing testing, optimization, and continuous improvement. And then towards the end, we did talk about the key considerations for hybrid and multi-cloud, in which we talked about portability, networking, and data transfer. Let's look at the key functions of Artifact Registry. Artifact Registry serves as a unified, scalable, and secure repository for storing, managing, and deploying a wide array of build artifacts with Google Cloud Platform or GCP. It streamlines the entire artifact lifecycle from initial creation to final deployment and beyond. Now, let's talk about the key functions of Artifact Registry. Let's start with comprehensive artifact storage. Artifact Registry acts as a centralized repository for various artifact types, including container images, which could be Docker images used for containerized applications, language packages, which could include Maven, NPM, Python, and Go packages for application dependencies. Then there could be Helm charts, which are basically packages for defining, installing, and upgrading Kubernetes applications. And then there could be other build artifacts, which could be generic build outputs such as compiled binaries or configuration files. Then the next function is Unified Management Interface. Artifact Registry provides a single user-friendly console for managing all artifact types, therefore simplifying the management process and reducing operational overhead. Then there is Fine-Grained Access Control. Artifact Registry integrates with Identity and Access Management or IAM in the Google Cloud Platform. It enables granular control over who can access, modify, and deploy specific artifacts. Now, this ensures that only authorized users or systems can interact with sensitive artifacts. Then there is integration with GCP services. It can seamlessly integrate with other GCP services. For example, it can integrate with Cloud Build for building container images and other artifacts directly into Artifact Registry. It can integrate with Cloud Deploy for deploying container images from Artifact Registry to various environments. It can also integrate with Google Kubernetes Engine or GKE for deploying containerized applications from Artifact Registry. It can also integrate with binary authorization for enforcing policies that govern the deployment of container images. The next function is regional and multi-regional repositories. Artifact Registry supports regional and multi-regional repositories, therefore enabling you to store artifacts closer to your users or applications for reduced latency and improved performance. Then there is vulnerability scanning. Artifact Registry integrates with Google's container analysis service to automatically scan container images for known vulnerabilities. Now, this helps you maintain a secure software supply chain. Let's now talk about the benefits of using Artifact Registry. So there is simplified artifact management. Artifact Registry centralizes artifact management, thereby eliminating the need to maintain separate repositories for different artifact types. Then there is enhanced security. Its granular access control and vulnerability scanning improves the security and compliance. Then there is improved performance. Its regional and multi-regional repositories ensure low latency and high availability. And this is achieved by deploying the artifacts closer to the users or the applications in that particular region. Then there is streamlined CI/CD pipelines. Seamless integration of artifact registry with other GCP services simplifies the creation and management of CI/CD pipelines. Then there is reduced vendor lock-in. Artifact registry supports standard protocols such as Docker Registry HTTP API v2, therefore making it compatible with a wide range of CI/CD tools and systems. Now, just to quickly reiterate or recap, in this particular topic, we talked about the key functions of artifact registry. We talked about comprehensive artifact storage, unified management interface, fine-grained access control, integration with other GCP services, regional and multi-regional repositories, and vulnerability scanning. And then we talked about the benefits of using artifact registry. Now, benefits included simplified artifact management, enhanced security, improved performance, streamlined CI/CD pipelines, and reduced vendor lock-in. Let's now talk about different deployment strategies for software in cloud environments. When you are deploying new software versions in cloud environment, you are required to have strategies that ensure minimal disruption, seamless rollback, and effective risk management. Now, there are mostly three common strategies that are used, and these are canary deployments, blue-green deployments, and rolling updates. And then there are two more strategies which we are going to talk about. Let's first talk about canary deployments, which involves gradually releasing a new version to a small subset of users, therefore allowing real-world testing while minimizing potential issues. GCP facilitates this release with tools like Managed Instance Groups, which are MIGs, and Cloud Deploy. The next strategy is blue and green deployments that maintains two identical environments where a new version is deployed and tested in the green environment before switching all traffic to it from blue environment. GCP Load Balancer and Cloud Run simplifies this process. Then there is rolling updates, which progressively replaces instances of an old version with new one, therefore ensuring minimal downtime and maintaining service availability. GCP supports this replacement with MIGs and Kubernetes, therefore allowing controlled and efficient rollouts. Each of these strategies offer unique benefits and can be chosen based on specific requirements and constraints of the application and operational environments. Now, other than these three strategies, there are two more deployment strategies which can be used in several different scenarios. So there is feature flags. You can deploy new features but keep them hidden behind feature flags. This allows you to activate or deactivate features for specific user groups or at specific times, therefore enabling controlled experimentation and reducing the risk of failed deployments. Then there is A/B testing, which deploy multiple versions of a feature simultaneously and direct a portion of traffic to each version. This helps you evaluate the performance and user response of different versions before deciding on a final implementation. Let's talk about choosing the right deployment strategies. So there are several parameters on which you can decide which is the right deployment strategy for you. So we have listed down some of these key parameters. So there is downtime, ease of rollback, risk, and complexity. So let's look at these deployment strategies and talk about each of these parameters. So let's start with canary deployment. Now, when you talk about downtime, there is minimal downtime with canary deployment because only a subset of users is impacted during the initial rollout. Then there is ease of rollback, which is easy due to small number of affected instances which can be quickly reverted. The risk is the lowest with canary deployment because potential issues are only exposed to a small portion of user base. Then there is complexity, which is medium because it involves setting up traffic routing and monitoring only for a subset of users. Let's now talk about blue and green. When you talk about the downtime for blue and green, there is none, which means absolutely there is no downtime because the switch between blue and green environments is typically instantaneous. Now, when you talk about the ease of rollback for blue and green, it's instant because it involves simply switching traffic back to the previous environment. The risk for blue and green is low given that the new version is thoroughly tested in the green environment before switching. The complexity for blue and green is medium because it requires maintaining two identical environments and managing traffic routing. Let's now talk about the rolling update. So the downtime for rolling update is minimal because instances are updated gradually and the application remains available. The ease of rollback is moderate because it may require rolling back each updated instance if issues are detected. The risk is medium because issues can potentially affect a large portion of users before being identified. And the complexity for rolling update is low due to a straightforward process of gradually replacing instances with the new version. Let's quickly recap. We talked about three different deployment strategies, which is canary deployment, blue and green deployments, and rolling updates. And we did compare them on various parameters like downtime, ease of rollback, risk, and complexity. And other than that, we had a brief discussion on feature flags and A/B testing, which are other types of deployment strategies that may be used in several different scenarios. Let's now talk about the triggers for CI/CD pipelines. Triggers in GCP are the methods that automatically initiate actions within a CI/CD pipeline. They act as the starting point for a sequence of events, which could be building, testing, or deploying your application code. For example, now you can think of triggers like the listeners. So they are waiting for a specific event or condition to occur, and the moment that condition or event occurs, these triggers are kicked off to the corresponding pipeline processes. Now, there could be several different types of events or conditions. So, for example, it could be code changes, a push to a code repository such as GitHub, Bitbucket, or cloud source repository, or there could be a pull request which can cause a trigger to execute. Or it could be scheduled time. It could be a specific time or recurring interval such as daily or weekly. Then there could be external events. For example, messages published to a cloud pub sub topic, incoming webhooks from external systems, or changes in the cloud storage bucket. When you talk about triggers, they are essentially used for automating software delivery workflows by automatically initiating pipelines in response to specific events. They eliminate the need for manual intervention. They reduce the risk of human error and they enable faster and more frequent deployments. For example, you could have a trigger as soon as there is a code change that has occurred. The trigger would kick off and it would basically start the CI/CD pipeline. But if there is no code change for several days, obviously then the CI/CD pipeline is not getting started because there is no trigger that is taking place. Let's now talk about GCP's triggers for CI/CD pipelines. Now, we have talked about what triggers are. Let's now talk about identifying the types of triggers available in GCP that can initiate CI/CD pipelines. So there could be cloud build triggers. Now there could be source repository triggers that automatically initiate builds when code changes are pushed or pull requests are created or updated in connected repositories, which could be cloud source repositories, GitHub, Bitbucket, or GitLab. You can filter by branch, tag, or specific paths within the repository. Now, within the cloud build triggers, there could be cloud scheduler triggers. You can schedule builds to run at specific intervals or on a cron schedule. This is ideal for periodic tasks like nightly builds or test runs. Now, in cloud build triggers, there could be pub/sub triggers, which triggers a build when messages are published to a specific cloud pub/sub topic, therefore enabling integration with various event sources or other systems. Then there are webhook triggers, which allow external systems to trigger builds by sending HTTP post requests to a cloud build webhook URL. The next set of triggers we are going to talk about is cloud deploy triggers. So there is release creation, which automatically triggers deployments when a new release is created in cloud deploy. There is target approval, which triggers a deployment to the next target environment such as production upon manual approval after successful deployment to a previous stage environment such as staging. Then there are rollout progress, which triggers automated rollbacks or other actions based on progress of a rollout, for example, if errors exceed a particular threshold. The next set of triggers is event arc triggers. So there are a wide range of events that trigger cloud functions or cloud run services based on events from various sources like cloud storage, pub/sub, Firestore, or other services. You can then use these functions or services to initiate cloud builds or other CI/CD actions. Then there is custom event filtering, which allows you to trigger actions based on specific events, attributes, or conditions. The next set of triggers is cloud scheduler or cron jobs. Now, these are time-based triggers that schedule regular tasks like running tests, cleaning up resources, or generating reports. This can be helpful for maintaining a healthy CI/CD environment. The last set is manual triggers. On-demand builds deployments trigger builds or deployments usually through the Cloud Build or Cloud Deploy console, gcloud CLI, or API when needed. Let's now talk about choosing the right trigger for CI/CD pipeline. We talked about 5 different types of triggers. Now, how do we get to choose the right one? The ideal trigger for your CI/CD pipeline depends on your specific workflow and requirements. So if there is a certain set of requirement you have, you would use one particular type of trigger, but that trigger may not be appropriate in another use case or scenario. So let's talk about source repository triggers. Now, these are commonly used for automated builds and deployments where code changes are committed. Some of the use cases would be frequent code changes, continuous integration, and deployment workflows. Then there are cloud scheduler triggers that are useful for scheduled tasks that are not directly tied to code changes. Some of the use cases would be routine maintenance tasks, periodic deployments, and scheduled updates. Then for pub/sub or webhook triggers, they are used basically for flexible integration with various external systems or event sources. Some of the use cases would be integration with third-party services, external event handling, and cross-service notifications. Then there are event arc triggers that provide advanced event-driven automation capabilities. Some of the ideal use cases would be complex event-driven workflows, multi-step automation processes, and sophisticated event handling. The last set is manual triggers that offer flexibility for ad hoc builds and deployments. The ideal use cases for them would be on-demand deployments, manual approvals, and special purpose builds. Now, just to quickly recap, we talked about the triggers for CI/CD pipelines. We spoke about what triggers are and how they get executed. So there are certain events or conditions on which they get executed, like code changes, scheduled time, external events. So these are some of the events or the conditions. And then we talked about different triggers for CI/CD pipelines in GCP environment. So there was cloud build triggers, there were cloud deploy triggers, event arc triggers, cloud scheduler or cron jobs triggers, and manual triggers. Let's now talk about the steps involved in testing a new application version within a CI/CD pipeline. So there are a series of steps that we would need to perform. We'll start with configuring triggers. The testing process is triggered by a specific event or condition within the CI/CD pipeline. So there could be different scenarios in which it might get triggered. So there could be a new code commit. A trigger might get kicked off due to a specific condition or event. So there could be numerous of these. Some of the examples could be a new code commit to a version control repository. And these version control repositories could be GitHub, GitLab, and Bitbucket. Another scenario could be a successful build process that produces a new application artifact, such as a Docker image or a jar file. It could be a scheduled event, such as nightly regression test. It could be a manual trigger initiated by a developer or a QA engineer. The next step is to configure the environment. We would need to have a clean, isolated testing environment that is provisioned mostly using IAC tools like Terraform or CloudFormation. Now, this environment should closely mirror the production environment, including dependencies, configurations, and data. Now, depending on the complexity of the application, this might involve spinning up virtual machines, containers, databases, or any other required component. The next step is to prepare the test data. The relevant test data is created from scratch, loaded from a snapshot, or generated using tools that simulate realistic data patterns. The goal is to ensure that the application is tested against diverse and representative data set. Then we move on to the next step, which is execute test. Automated tests of various types are executed in a predefined order. So it starts with unit test, which verifies the smallest component of the code in isolation. Then there is integration test that ensures that different components interact correctly. Then there are API tests, which validate the application's external interfaces and responses. Then there is end-to-end test that simulate user interactions with the application to confirm complete functionality. Then there are performance tests that assess the application speed, responsiveness, and resource utilization under load. Finally, there is security test that identifies vulnerabilities like SQL injection, cross-site scripting or XSS, and authentication flaws. Then comes the next step, which is to perform test result analysis. The CI/CD tool gathers the test results and presents them in a clear and actionable format, and typically it is in the dashboard or report format. Any failed tests are flagged for investigation. Code coverage reports may be generated to highlight areas of applications that lack sufficient testing. Then we move on to the next step, which is to work on the feedback. Now the team reviews the test results and decides whether to proceed with the deployment. If all tests pass and meet quality standards, the pipeline can automatically move on to the deployment stage. If any critical tests fail, the deployment is halted and developers are alerted to fix the issues. Finally, the last step, which is performed only if necessary, and this step is initiate rollback. If a new application version causes problem in production, the CI/CD pipeline can automatically roll back to previous stable version of the application. Now this rollback helps in minimize the downtime and impact on the users. Because now if there is a problem in the current version, you can immediately switch over to the previous version, and that is what the rollback is all about. Let's now talk about the key considerations for application testing. There is test environment parity. The testing environment should closely resemble the production environment to ensure accurate results. There is test automation. You should automate as many tests as possible to reduce manual effort and accelerate the feedback loop. Then there is test data management. You should maintain clean, reliable test data that covers various scenarios. Now remember that if you haven't validated your test data, the results are not going to be as you desire. So you need to ensure that the test data is clean and reliable. Then there is check for continuous feedback. You should monitor your test results over time. You need to identify the trends and improve the testing process. Then there is perform shift left testing. You should involve testers early in the development cycle to quickly detect the issues. Now, this is what shift left testing is all about. Instead of doing testing at the end, you start right from the beginning. You involve the testers right there in the starting stage and then carry on from there onwards. This is what the shift left testing is all about. Now, just to quickly recap, in this particular topic, we talked about the steps for testing a new application in the CI/CD pipeline. We talked about steps like configuring triggers, configure the environment, prepare the test data, work on feedback, perform test result analysis, execute tests, and initiate rollback if required. And then we talked about the key considerations for application testing. We talked about test environment parity, test automation, test data management, checking for continuous feedback, and performing shift left testing. In this demo, we are going to look at an automated deployment process to deploy a build, and we are going to also look at it. How do we inbuild the approval process? To be able to do that, we have these three triggers. Now, in the first trigger, which is first app, I'm going to go ahead and click on this. And once it opens up, I need to scroll down to the approval section. Now, in this, notice that I have already checked on this, require approval before build executes. Now, the process, how it works is, once you check on this, once you trigger the build process will start. Then there is an approval that will go to a person who has the cloud build approver role. Now, anybody who has this role, that person will see a request or notification to approve that particular build in the dashboard. Now, we're going to see that. So this needs to be checked. This particular role needs to be assigned to a person who needs to approve the build, and this assignment needs to happen in identity and access management. So once we have done that, I'm going to go ahead and cancel this, and now we are back onto the triggers page. I'm going to click on run. And so again, the repository, the branch, which is main, and I'm going to click on run trigger. Now, build started on branch main. So I'm going to click on show. Now there is a build summary. So it says awaiting approval. So there is an approval ID that is there. So I'm going to go to dashboard. Now I have assigned cloud build approver rights to myself. So I get this notification. You have one build awaiting approval. So I'm going to go ahead and click on view builds. And once I do that, I'm going to see this request. So I'm going to click on this three dots and select approve build. And if I need to put any kind of message here, so I'm going to just write approved. I can do that here, and I click on approve. Now, build approved. This is the message it shows, or the notification it shows. And then the build process is now started. So basically that status is checked. Now, if I go to history, I will see that there is this particular that is there. So we are already in history. Now I'm going to go back to triggers. And now if I go back to history, I'll see a list of builds that have already been either built successfully or have failed due to some reasons. So now look at this. This was our particular build which got approved, and this has been now completed. Well, this is the end of this particular demo. So in this demo, what we saw is how to run a trigger and start the automated build deployment process, and how to configure the approval process in that entire automated process. CI/CD for serverless applications on GCP leverages the platform's inherent scalability and pay-per-use model to automate the entire software development lifecycle, from code commits to production deployment. This not only accelerates development but also ensures high reliability and resilience. Let's talk about the key components. So the first one is the source code management. A serverless application's code resides in a version control system like Cloud Source Repository, GitHub, Bitbucket, or GitLab. Now, this ensures versioning, collaboration, and a single source of truth for your code base. Then there is continuous integration. So there are triggers. A code change triggers the CI process. Code build is often used to set up this stage. Then there is build. The code is compiled or packaged as needed. In serverless context, this often involves creating deployment packages for cloud functions or artifacts for Cloud Run. Then there are tests, which are automated tests such as unit or integration that run to verify the functionality and correctness of the code. Cloud Build can execute tests in a containerized environment and ensure consistency. Then there is artifact storage. Successful builds produce artifacts such as deployment packages or container images that are stored in a repository like artifact registry for later deployment. The third component is the continuous deployment. A successful CI or continuous integration build or manual approval triggers the CD process. The artifacts are deployed to the target environment, which can be Cloud Function, Cloud Run Service, or other serverless offerings. Post-deployment tests such as smoke test and health checks that confirm the application's correct functioning in the environment. Let's now talk about the considerations for serverless CI/CD. There are numerous considerations that could exist, but we have listed down the top considerations that you should follow. So there is IAC. You should use tools like Terraform or Deployment Manager to define and manage your serverless infrastructure. This allows you to version and reproduce your environment consistently. Then there is environment variable. You should securely manage environment variables and secrets by using tools such as Secrets Manager to avoid hard-coding sensitive information in your code. Then there is cloud build configuration. You can create a cloud build.yml file to define the steps of your build and deployment process. This can be versioned alongside your code. Then there is monitoring and observability. You can utilize cloud monitoring and cloud logging to track the health, performance, and errors of your serverless application. This data is crucial for troubleshooting and optimization. Then there are rollbacks. You can implement automated rollback strategies in case of deployment failures. Cloud Deploy can be configured to automatically roll back to the previous version if a deployment fails health checks. Let's now talk about the GCP services for serverless CI/CD. So there are several services that you can use for serverless CI/CD. So there is Cloud Build, which is a fully managed build service that can compile your code, run tests, and create artifacts. Then there is Cloud Deploy, which simplifies the deployment of serverless application to different environments with features like approvals, rollbacks, and traffic management. Then there is Artifact Registry, which is a centralized repository for storing and managing your build artifacts. Then there is Cloud Functions, which is a serverless compute platform for building event-driven applications. Then there is Cloud Run, which is a serverless platform for running stateless containers that are invocable using HTTP requests. Just to quickly recap, in this particular topic, we talked about CI/CD for serverless applications on GCP. We talked about three key components, which is the source code management, continuous integration, and continuous deployment. We also talked about several considerations for serverless CI/CD. We talked about infrastructure as code, environment variables, cloud build configuration, monitoring and observability, and rollbacks. And finally, towards the end, we talked about different GCP services for serverless CI/CD. We talked about cloud build, cloud deploy, artifact registry, cloud functions, and cloud run. In this topic, we are going to talk about auditing and tracking deployments using Cloud Build and Cloud Deploy. GCP's Cloud Build and Cloud Deploy offer a robust framework for not only automating deployments, but also maintaining a comprehensive audit trail and detailed deployment tracking. We'll learn about them in the next few slides. Let's first talk about Cloud Build. Cloud Build serves as a cornerstone of a CI/CD pipeline. It builds, tests, and packages applications. It provides several crucial features for auditing and tracking. So the first one is build logs. Each build generates detailed logs that capture every step of the process, including commands executed, environment variables, and any errors or warnings. This provides a granular view of what happened during the build and aids in troubleshooting and identifying potential issues. The next one is artifact tracking. Cloud Build stores artifacts generated during the build process, such as Docker images or jar files, in an artifact registry. This allows you to trace lineage of each deployment back to its source code and build artifacts. Then there is Cloud Audit logs. Cloud Build generates with GCP's Cloud Audit logs, which record API calls made to Cloud Build. This allows you to track who initiated builds, when they were initiated, and the outcome of each build. Let's now talk about Cloud Deploy. Cloud Deploy takes over once your build artifacts are ready. It sets up the deployment process across various environments and provides additional auditing and tracking capabilities. So let's look at some of these capabilities. So the first one is the release management. Cloud Deploy organizes your deployment into releases, each representing a specific version of your application. This allows you to track which version is deployed in each environment. Then there is deployment history. Cloud Deploy maintains a detailed history of all deployments, including the time of the deployment, the deployed version, and the status, which could be success or failure. Then there is rollout tracking. For progressive rollouts like Canary or blue-green deployments, Cloud Deploy provides metrics and logs to track the progress of the rollout, therefore allowing you to monitor the impact of the new version. Then there are approval gates. You can configure approval gates in Cloud Deploy, requiring manual sign-off before a deployment proceeds to the next stage. This provides an additional layer of control and ensures that deployments are authorized by the appropriate personnel. Then there is deployment verification. Cloud Deploy allows you to define post-deployment verification steps, such as running integration tests or health checks. The result of these verifications are recorded, providing insights into the overall health of your application. Then there is Cloud Audit logs. Similar to Cloud Build, Cloud Deploy integrates with Cloud Audit logs, therefore enabling you to track user actions and provide events related to deployments. Now, just to quickly recap in this particular topic, we talked about auditing and tracking deployments, we talked about Cloud Build, and we also talked about Cloud Deploy. Rollback strategies for CI/CD pipelines. In this particular topic, we are going to talk about the rollback strategies for CI/CD pipelines. So let's start with automatic rollback with Cloud Deploy. Cloud Deploy enables automatic rollbacks to the previous stable version of an application when its deployment either fails specific health checks or exceeds error thresholds. You can define the failure criteria for Cloud Deploy. Now let's talk about an advantage. So there is fast recovery. It can swiftly return to a working state, therefore minimizing the downtime and user impact. One of the disadvantages is limited flexibility. Rollback criteria are predefined and may not be suitable in all scenarios. Let's now talk about another advantage, which is the reduced manual intervention. Now, automatic rollback eliminates the need for manual intervention during critical situations. Disadvantage is potential data loss. In some cases, data modifications made by the failed deployment may not be fully reversible. Another advantage is reliability. Automatic rollbacks offer a safety net for unexpected issues, which increases confidence in deployment. Another disadvantage is complex state management. Handling the state of the application and its dependencies, such as database migrations, can be challenging and may require additional safeguards. Let's now talk about the manual rollbacks with Cloud Deploy. Just like the automatic rollbacks, Cloud Deploy also allows you to manually trigger a rollback to a specific earlier version of an application. Again, there are advantages and disadvantages. The first advantage is control. You have full control over when and to which version you want to roll back. Now, the disadvantage is slower recovery. It requires manual intervention and therefore more time than automated rollbacks. Another advantage is versatility. It's suitable for situations where automatic rollbacks are not sufficient or appropriate. Now, another disadvantage is human error. Mistakes are possible when manually selecting the rollback version. Then again, going back to the advantages, customizability is another advantage. You can plan tailored rollback strategies based on the context of the deployment issue. Disadvantage is inconsistent rollbacks. Manual processes may lead to inconsistency if they are not carefully managed and documented. Let's now talk about IAC, or infrastructure as code rollbacks. Now, for IAC, we have talked about this earlier. We use Terraform or Deployment Manager. You can revert your infrastructure to a previous state defined in the IAC configuration. Now, again, there are going to be advantages and disadvantages. For advantages, let's start with comprehensive process. It handles rollbacks of both application code and infrastructure changes. It ensures that infrastructure across different environments remain consistent and align with the defined configuration. One of the disadvantages is complexity. It requires well-maintained IAC configurations and a good understanding of your infrastructure. Let's now go back to the advantage, which is reproducibility. It allows you to easily and confidently create the previous environment. Now, going back to the disadvantage again, there can be potential downtime. Depending on the scope of this change, the rollback process may involve downtime. Another advantage is version control. It enables tracking and versioning of changes of the infrastructure, which in turn enable precise rollbacks. Now, another disadvantage could be resource dependencies. Rollbacks might be complicated by dependencies between resources, which could lead to partial or failed rollbacks. It also requires team members to have knowledge and expertise in IAC tools and best practices. Let's now talk about blue-green deployments with manual rollback. While blue-green deployments themselves ensure zero downtime, you can manually switch traffic back to the blue environment if issues are discovered in the green environment. So there are advantages and disadvantages. The first advantage is instantaneous rollback. It can revert to the previous stage very quickly. Users are not impacted during the rollback. Disadvantage could be resource intensive. It requires double the resources to maintain both environments. It requires running two parallel environments, which can be expensive, especially for a large-scale application. Switching back to the advantage, there is zero downtime deployment. It allows for new versions to be deployed without any downtime, as traffic can be switched seamlessly. Then there is another disadvantage, which is the manual intervention. It requires manually switching traffic back in case of problems. Another advantage is easy testing. It enables thorough testing of the new environments, which is the green environment, while old environment, which is blue, remains live, therefore ensuring issues can be identified before full traffic cutover. Disadvantage is complex management. It requires careful coordination as managing two environments simultaneously can be complex. Let's now talk about the considerations for application rollbacks. Now, your rollback strategy depends on your requirements. So it could be different set of requirements. For example, it could be criticality of an application. For mission critical applications, automatic rollbacks with cloud deploy offer fast and reliable recovery. Then there is control and flexibility. If you need more control over when and how to roll back, you need to go for manual rollbacks or IAC rollbacks. Then there are infrastructure changes. IAC rollbacks are ideal if your deployments involve significant infrastructure changes. Then there is minimized downtime. Blue and green deployments with manual rollback offer the fastest recovery and minimal disruption. Just to quickly recap, in this particular topic, we talked about automatic rollbacks with cloud deploy. We talked about manual rollbacks with cloud deploy. We talked about IAC rollbacks. We also talked about blue-green deployments with manual rollback. And towards the end, we did talk about considerations for application rollbacks. And some of the considerations that we talked about: criticality of an application, control and flexibility, infrastructure changes, and minimized downtime. Now, whenever we try to deploy a build, and if there is a smallest of an error, it can cause the build to failure, and this deployment failure can be very frustrating. If we follow a methodical approach, we can identify or even resolve these issues efficiently. So there are some certain steps that we can follow. So let's go ahead and talk about this. The first one is to gather information. You should start by carefully examining the error messages provided by the GCP services. They often offer valuable clues about the nature of the problem. So look for specific error codes, messages, and timestamps. And this information can be helpful if you can go onto the internet and try to search for those specific error messages. In most cases, you will find the answers in some of the forums where somebody would have faced the similar issues and they would have posted the answer if they would have been able to resolve that particular error. You should also check for logs. You should check logs for relevant services like Cloud Build, Cloud Deploy, Compute Engine, or even Kubernetes Engine. These logs often contain detailed information about what went wrong during the deployment process. You should pay attention to error logs, warnings, and any unexpected behaviors. The next is data monitoring. You should also utilize GCP's monitoring tools like cloud monitoring or cloud logging to analyze metrics related to resource usage, network traffic, and application performance. You should look for anomalies or spikes that might correlate with the deployment failure. The next step is to identify the root cause. Now, you have gathered a lot of information from the logs or the error messages. Now, based on this gathered information, you should try to pinpoint the root cause of the issue. So, here are some common culprits that you can identify. So, first one is the misconfiguration. There are going to be incorrect settings in your deployment configuration, IAC templates, or application code that would have led to failures. You should double check your configuration for typos, missing values, or incorrect permissions. Then there are resource constraints. Sometimes insufficient resources such as CPU, memory, or even disk space or quota limits can prevent deployments from succeeding. You should monitor resource utilization and request quota increases if needed. Then there could be networking issues. Problems with network connectivity, firewall rules, or load balancing can disrupt deployments. You should verify the network configuration and ensure that they are correct and there are no connectivity issues between the different components of your infrastructure. Then you should look for application errors. You should look for bugs or errors in your application code that can cause failures during deployment or runtime. You should analyze application logs for errors and stack traces to identify and fix code issues. Then there can be dependency problems. Issues with external dependencies such as libraries, databases, or even APIs can also impact deployments. You should check that your dependencies are available, accessible, and configured correctly. The next step is to apply troubleshooting techniques. You should test in isolation. You should try to reproduce the issue in a smaller, isolated environment to narrow down the problem. This could involve deploying a simplified version of your application or testing specific components individually. Then you should also utilize debugging tools. You should use debugging tools provided by GCP services or your development environment to inspect the state of your application and identify errors. Then there are going to be rollbacks. If your CI/CD pipeline supports rollbacks, try reverting to a previous working version of your application to restore functionality quickly. Then there is an obvious step, which is consult documentation. You should refer to the official GCP documentation and community forums for troubleshooting guides, best practices, and potential solutions. Then the next step is implement preventive measures. You should ensure that you have thorough automated tests in place to catch issues early in the development cycle before they reach deployment. Then there is validation. You should validate your development configurations, IAC templates, and application code before deploying to production. Then there is monitoring and alerting. You should set up comprehensive monitoring and alerting system to detect issues proactively and notify you when problems arise. Then there is CI/CD optimization. You should continuously refine your CI/CD pipeline to make it more resilient and less prone to errors. Let's now talk about the examples of common deployment issues and solutions. Let's talk about the first issue, which is deployment fails with a permission denied error. When a deployment fails with a permission denied error, it indicates that the service account used for the deployment lacks the necessary permissions to perform the required actions. Now, the potential cause of this issue is insufficient permissions granted to the service account. This could be due to misconfiguration or oversight during the setup of identity and access management roles. How do you troubleshoot this? To resolve this issue, it is essential to review and update the IAM roles assigned to service account. You should ensure that the service account has the appropriate permissions required for the deployment process. Now, this may involve gathering additional roles or permissions to the service account through the IAM console or using G-Cloud command line tools to assign the permissions. Let's now talk about the next issue, which is application fails to start after deployment. When an application fails to start after the deployment, it suggests that there are issues preventing the application from initializing and running properly. The potential cause could be that this issue can arise due to various reasons, including incorrect environment variables, missing dependencies, or errors in the application code itself. Now, how do you troubleshoot this? You should start by analyzing the application logs to identify any error messages or exceptions thrown during the startup. You should verify the correctness of the environment variables set for the application, therefore ensuring they are configured as expected. In addition to this, you should also check for missing dependencies and ensure that all required libraries or components are installed. You should also review the application code for bugs, defects, or errors that may prevent it from starting. The next issue is slow or unresponsive application. Now, this could indicate that there are performance issues that affect the responsiveness and user experience of the application. Now, the potential cause could be different factors such as insufficient resources allocated to the application, high network latency affecting the communication between components, or performance bottlenecks within the application code itself. Now, how do you troubleshoot this? You should start by monitoring resource usage metrics such as CPU, memory, and disk utilization to identify any resource constraints. You should optimize network configurations to reduce latency and improve communication between components. Additionally, you should profile the application code to identify any performance bottlenecks or inefficient code patterns that may be causing slowdowns. By systematically addressing these factors, you can actually enhance the performance and responsiveness of the application. Just to quickly recap, in this particular topic, we talked about troubleshooting deployment issues. We talked about different steps that we could perform. So these steps were gathering information, identifying the root cause, applying troubleshooting techniques, and implementing preventive measures. Then we also looked at some of the common examples of deployment issues and their solutions. Management of CI/CD configuration and secrets. In this particular topic, we are going to talk about how to manage CI/CD configuration and the secrets. So let's start with CI/CD configuration management. So there are different aspects that you have to look at it. So first one is the version control. You should always store your CI/CD pipeline configurations, which could include your Jenkins file, GitLab CI/CD, YAML file, and cloud build.yml file in a version control system, something like Git. This allows you to track changes, revert to previous configurations if needed, and collaborate effectively with team members. Then there is IAC. You should use IAC tools such as Terraform, CloudFormation, or Plumi to define and manage your CI/CD infrastructure, which will include build servers and deployment environments. This ensures consistency, reproducibility, and easier management of changes. Then there are configuration templates. You should utilize templates such as Jinja 2 and Helm charts to avoid duplication and streamline the management of configurations across different projects or environments. Then there is parameterization. You should parameterize your configurations to make them reusable and adaptable to different scenarios. You should use environment variables or configuration files to dynamically inject values during runtime. Then there is validation. You should implement validation mechanisms to check the integrity and correctness of your configurations before applying them. This helps prevent errors and unexpected behavior. Let's now talk about the management of secrets. So first one is no hard-coded secrets. You should avoid storing sensitive information like password, API key, or tokens directly into your configuration files. Hard-coded secrets are security risks, which makes it difficult to rotate or revoke credentials. So what is the alternate? You can use environment variables if, for example, if you're using Terraform. Then there are tools for secret manager. You can leverage dedicated secret management tools like Google Cloud Secret Manager, which is a secure and convenient way to store, manage, and access secrets within Google Cloud Platform. Then there is HashiCorp Vault, which is a versatile secret management solution that offers encryption, access control, and auditing capabilities. Now, if you're using another cloud provider, for example, Amazon Web Services or AWS, there you can use AWS Secret Manager. And if you're using Azure, you can use Azure Key Vault. They both function in the same way as Google Cloud Secret Manager. Then there is encryption. You need to ensure all secrets are encrypted both at rest and in transit. You should use strong encryption algorithms and rotate encryption keys regularly. Then there is access control. You should implement strict access controls to limit who can view, modify, or use secrets. You should use role-based access control, which is RBAC, or attribute-based access control, which is ABAC, to enforce the principle of least privilege. Let's continue to the next slide and look at some more methods of management of secrets. So there is auditing. You should enable auditing to track who accesses secrets and when. This helps in identifying unauthorized access or potential security breaches. Then there is rotation of secrets. You should regularly rotate secrets to reduce the risk of exposure. You should set up automated rotation processes wherever possible. Then there are temporary credentials. You should use short-lived credentials or tokens wherever possible to minimize the window of vulnerability. Let's now talk about integration with CI/CD tools. So there is secure integration. You can integrate your chosen secret management tool with your CI/CD platform. For example, Jenkins, GitLab CI/CD, and Cloud Build. Then there is dynamic injection. You can inject secrets into your CI/CD pipeline environment at runtime, therefore avoiding the need to store them in plain text, and this is what you do using the environment variables. Then there is masking. You can mask or obfuscate sensitive information in logs and output to prevent accidental exposure. Let's now talk about the best practices for CI/CD configurations and secrets. By adhering to certain best practices and utilizing the right tools, you can establish a robust and secure CI/CD pipeline that can protect your sensitive information while streamlining your software delivery process. Let's look at some of these best practices. So one is centralized management. You can consolidate the management of CI/CD configurations and secrets in a central location to simplify administration and ensure consistency. Then there is least privilege. You should grant only necessary permissions to users and systems or services that need to interact with configurations and secret. Then there is regular review. You should periodically review and audit your configurations and secrets to identify any potential vulnerabilities or area of improvement. Then finally, there is documentation. You need to maintain clear and up-to-date documentation onto how to manage configurations and secrets, therefore ensuring that everyone on your team understands the processes and security practices. Just to quickly recap, in this particular topic, we talked about CI/CD configuration management, in which we talked about version control, IAC, configuration templates, parameterization, and validation. Then we talked about management of secrets, which included no hard-coded secrets, certain tools for secret management, encryption, access control, auditing, rotation of secrets, and temporary credentials. And then we talked about integration with the CI/CD tools. So it was secure integration, dynamic injection, and masking. And then finally, we talked about the best practices for CI/CD configuration and secrets. We talked about centralized management, least privilege, regular reviews, and documentation. In this topic, we are going to talk about securing a GCP CI/CD pipeline using a multi-layered approach, and then we are going to look at an example of IAM policy for a deployment service account. So let's first start with securing a GCP CI/CD pipeline. And it's going to be using a multi-layered approach in which basically we are going to talk about different methods that will be employed to secure your CI/CD pipeline. The first one is secure code repository access. You can grant developers and CI/CD tools the least privileges necessary to interact with your code repositories such as cloud source repositories and GitHub. You can use IAM roles to restrict actions like pushing code, creating branches, or approving pull requests. Then you can also enforce branch protection rules to prevent direct commits to critical branches such as main or master. You should require pull requests and code reviews before merging changes. And you should also mandate code reviews for all changes to catch vulnerabilities, security issues, and potential errors early in the development cycle. Then there is vulnerability analysis. You should integrate static application security testing tools into your pipeline to scan your source code for vulnerability, secure coding practices, and potential exploits. Some of the popular static application security testing tools include SonarQube, Checkmarx, and Fortify. If you are using container, you should scan images for known vulnerabilities using container analysis. This will help you identify outdated dependencies, known exploits, and misconfigurations in your container images. You should also employ dependency scanning tools to identify and update vulnerable dependencies in your application. Now, these tools will help you analyze your project libraries and frameworks to flag any known security issues. The next method is secure build environment. You should use dedicated build agents or virtual machines for each build to prevent cross contamination and ensure a clean environment. You should also grant build agents the minimum necessary permissions to perform build tasks. You must avoid giving them excessive access to sensitive resources. Then you should also build the ephemeral environments. You should destroy build environments after each build to minimize the attack surface and prevent unauthorized access. The next method is secure artifact management. You should store your build artifacts such as container images and binaries in artifact registry that provides fine-grained access control. It integrates with binary authorization to enforce deployment policies based on security criteria. You should also sign your artifacts with cryptographic signature to ensure their integrity and authenticity. You should verify these signatures before deploying to production. The next method is IAM policies for deployment. You should create separate service accounts for CI/CD stages such as build, test, and deploy with distinct IAM roles. This ensures that each stage has only the permission it needs to perform its tasks. You should also grant service accounts the minimum necessary permissions to interact with GCP resources during deployment. You should avoid granting overly broad permissions that could be exploited by attackers. You should also use Cloud Deploy's approval gates to require manual approvals for deployment to production. This adds an extra layer of security and control. Then the next method is continuous monitoring and logging. You should enable and monitor cloud audit logs to track actions taken within your CI/CD pipeline, including to initiated builds or deployments, changes to configurations, and any unauthorized access attempts. You should set up monitoring and alerting for your CI/CD infrastructure and deployed applications. You should detect anomalies, security incidents, and performance degradation in real time. Let's now talk about an example of an IAM policy for deployment service account. Now, there is a code given on the slide. This particular policy that contains this code allows the service account to manage compute engine instances in a specific project but does not grant any broader permissions. You can implement such policies throughout your CI/CD pipeline. You can significantly reduce the risk of vulnerabilities, unauthorized access, and malicious deployments and safeguard your applications and data. Just to quickly recap, in this particular topic, we talked about different methods that can be used for securing a GCP CI/CD pipeline. So these methods included secure code repository access, vulnerability analysis, secure build environment, secure artifacts management, IAM policies for deployment, and continuous monitoring and logging. And then we also looked at an example of an IAM policy. So we've reached the end of this particular course. Now, in this particular course, we covered various topics. So we talked about designing CI/CD pipelines for hybrid and multi-cloud environments. We talked about deployment strategies like canary, blue-green, and rolling updates. And then we also talked about triggers for CI/CD pipelines in GCP. Then, moving ahead in the course, we did talk about testing a new application version, deployment processes, and CI/CD for serverless applications on GCP. We did talk about rollback strategies, auditing, tracking, troubleshooting, and securing deployments. And then we also talked about management of CI/CD configurations and secrets. So what's coming up next? The next course is going to be applying Site Reliability Engineering or SRE practices to a service. In this course, you will learn the foundations of Site Reliability Engineering or SRE, its core principles, and how to apply them effectively within Google Cloud Platform environments. You will gain insights into defining SLIs, SLOs, and SLAs while exploring strategies for managing the service lifecycle, capacity planning, and auto scaling. You will also develop an understanding of incident response, postmortem analysis, and toil reduction. You will discover how to foster collaboration, prevent burnout, and drive continuous improvement using feedback loops. Let's now talk about the objectives that you will cover in this course. So, you will start with site reliability engineering definition. So, you will describe what it is. You will define the concepts of change, velocity, and reliability in the context of SRE. You will also learn to identify key service level indicators or SLIs for cloud services. Then you will learn the process of defining service level objectives or SLOs and significance of service level agreements or SLAs. Then, moving on, you will also learn about the strategies for managing the service lifecycle, including deployment and maintenance. Then, you will learn to distinguish between capacity planning and auto scaling in GCP. Then, moving on, you will learn about the methods for ensuring healthy communication and collaboration within DevOps teams. Then, moving on, you will learn about the strategies for mitigating incident impact on users and services. Then, towards the end of the course, you will learn about the steps to conduct an effective postmortem analysis, automation of toil and its impact on service reliability. Then, you will learn about comparing different strategies for preventing burnout among operations teams. Then, towards the end of the course, you will go through a case study that will focus on the implementation of SRE practices in a GCP environment. And finally, you will also learn about the role of feedback loops in continuous service improvement. Let's now talk about site reliability engineering or SRE. Now, SRE is a way of thinking and working that combines software engineering skills with IT operations. Now, IT operations is basically the team of people who keep systems running. It is about building and running reliable, scalable systems, and particularly online services and websites. Now, SRE is a field within software engineering that is focused on maintaining and improving reliability, performance, and overall health of large scale systems and services. SRE teams use software engineering principles to solve operational problems, automate tasks, and ensure that systems run smoothly and efficiently. Let's now talk about the responsibilities of site reliability engineers. Site reliability engineers need to ensure availability, latency, performance, efficiency, change management, monitoring, emergency response, and capacity planning of a service within the GCP environments. So let's look at some of these key aspects. So we'll start with availability. Now, this is the heart of SRE. SREs ensure your service is up and running as much as possible, therefore minimizing downtime. They set targets for how often your service should be available. For example, a service, if it is not mission critical, needs to be up 99.9% of the time. And SREs work to meet these targets. So they will put up mechanisms that will ensure that they receive this much uptime of that particular service. So, how do they do it? They build resilient systems that can handle failures without crashing. They set up redundant servers and infrastructures to keep the services running even if some components fail. So, for example, just a hypothetical example of a server which has dual power supply. Now, if one power supply fails, the server will still continue to run. So, that is one way of ensuring availability and reliability of that particular server. Then they design systems that can quickly recover from failures, and they conduct chaos engineering experiments to test the system's resilience under stress. This means that they will put up some mechanisms that will ensure that availability of the system, but They will not just go ahead and implement it in the production environment. They will do chaos engineering. They will test out that particular mechanism. And once they are satisfied that, okay, the results are positive, then they will go ahead and implement in the live environment. Let's now talk about latency. Latency is how fast your service responds to your user requests. SREs aim to keep response times low so that users have a smooth experience with the service. And how do they achieve this? They optimize code and infrastructure to make services run faster. They use caching techniques to store frequently accessed data so it can be retrieved quickly. They load balance traffic to distribute requests across multiple servers and prevent bottlenecks. They also configure monitoring, which is for network conditions, and make adjustments to improve response times. Let's now talk about performance, which refers to how well your system handles different amounts of traffic and usage. SREs want to make sure the service performs well even during peak usage periods. And how do they do this? They conduct performance testing to identify bottlenecks and areas for improvement. They optimize code and databases for better performance. They scale up infrastructure during peak times to handle increased traffic. They implement auto scaling mechanisms to automatically adjust resources based on demand. Let's now talk about efficiency, which is about using your resources, which could be your servers, databases, in most effective way possible. SREs look for ways to get the most out of your infrastructure while keeping the costs under control. So example could be, if there are lot of servers that are there and you need to implement some new application, you don't want to just blindly go ahead and buy new servers. You have to see whether you can free up some servers and effectively and efficiently use your resources so that this application can be installed and configured on one of the available servers. So, how do they do it? They analyze resource utilization and identify areas where resources are either underutilized or overutilized. They automate tasks to reduce manual efforts and free up resources. They use cloud based services that offer flexible scaling options and pay as you go pricing. They implement energy saving measures to reduce power consumption. Let's move to the next slide and look at some more responsibilities of the site reliability engineers. So, moving on from the previous slide, we did talk about the responsibilities of site reliability engineers. So, we are going to continue and talk about the rest of the responsibilities. So, the next one is the change management, which involves making changes to your system. It could be new features or bug fixes without causing disruptions or downtime. The engineers help ensure that changes are rolled out smoothly and safely. How do they do this? They establish standardized change management processes and procedures. They use canary or blue green deployments to test changes in a controlled environment before rolling them out to all users. They implement automated rollback mechanisms to quickly revert to a previous version if something goes wrong. Let's now talk about monitoring, which involves constantly watching your systems for sign of trouble. The engineers set up alerts to notify them about any issues so they can be addressed quickly. So, how do they do it? They collect and analyze logs, metrics, and other data from your system. They set up alerts for specific thresholds, for example, high CPU usage or slow response times. Then they use monitoring tools to visualize data and spot trends. And they conduct regular post mortem analysis to learn from past incidents and prevent future problems. Let's now talk about emergency response, which is about having a plan in place to quickly fix problems when they occur. Engineers are often on call and ready to respond to emergency at any given time. How do they do it? They create detailed incident response plans and procedures. They define roles and responsibilities for different team members during an incident, and they practice incident response drills to ensure everyone knows what to do in a crisis. Let's now talk about capacity planning, which involves forecasting future growth and ensuring that your system can handle it. Engineers look at current usage patterns and make predictions about how much computing power and storage you will need in the future. How do they do it? They analyze historical usage data to identify trends and patterns. They conduct load testing to see how the system performs under stress. They work with developers to understand upcoming features and their potential impact on resource usage. And they plan for future infrastructure upgrades and expansions. Let's now talk about the benefits of SRE. So, there is increased reliability. SRE focuses on ensuring that systems are resilient and reliable. By using techniques such as redundancy, failover mechanisms, and thorough testing, SRE teams can minimize the risk of system failures. This reliability means that the services are constantly available when users need them, therefore, reducing the likelihood of downtime and maintaining user trust and satisfaction. Then there is faster recovery. When issues do occur, SRE teams are equipped to respond quickly. They use monitoring tools to detect problems early and have predefined incident response plans to address them promptly. Quick detection and resolution of problems minimize the duration and impact of usage, therefore, leading to less disruption for users and quicker restoration of normal service operations. Then there is improved performance. SRE practices include optimizing system performance by identifying and eliminating bottlenecks, therefore, ensuring efficient resource use and continuously monitoring system behavior under different loads. Now, this leads to smooth and efficient system operations, which provide faster response times and a better overall experience for users. Optimized performance also means that the system can handle more users and higher loads without degradation of performance. Then there is reduced cost. By automating routine tasks and proactive problem solving, SRE reduces the need for manual intervention and reactive fixes. Automation can handle tasks like scaling, backups, and routine maintenance. This leads to cost saving as fewer human resources are needed for operational tasks, and the efficient use of resources prevents over provisioning and underutilization. Proactive issue prevention also reduces the costs associated with downtime and emergency fixes. Then there are happier users. Reliable, high performing services contribute to a positive user experience. Users can rely on service to be available, responsive, and functioning correctly. Satisfied customers are more likely to stay loyal to the service, recommend it to the others, and contribute to the service's successful execution. High user satisfaction can lead to increased user engagement, retention, and overall business growth. Now, just to quickly recap, in this particular topic, we talked about what site reliability engineering is. We also talked about the responsibilities of site reliability engineers, which included availability, latency, performance, efficiency, change management, monitoring, emergency response, and capacity planning. We also talked about the benefits of SRE, which is increased reliability, faster recovery, improved performance, reduced costs, and happier users. Let's now talk about the types of change in SRE or site reliability engineering. Now, before we do that, let's define what a change is. In SRE, change refers to any modifications made to a system or service. This can include a broad spectrum of activities, including code changes, which could include updates, bug fixes, or new feature implementation in an application or software. Then this could be configuration changes, which are basically adjustment to settings, parameters, or infrastructure configurations. So, for example, you might want to implement a new firewall rule that will go under configuration change. Now, if you want to update a particular software or fix a particular bug, that would go under code changes. The next one is the deployment changes, which is rollout of new versions of the software or infrastructure. Now, this is specifically tracked in change management because that deployment may cause bottlenecks for other applications or services running. So, therefore, this also gets tracked, and you have to get that change approved before you roll out a new version of the software. Then there is scaling change, which is increasing or decreasing the capacity of a service to handle varying load. You might want to add more RAM or memory to a particular server. Now, that is also a change because you are making a scaling change. You are increasing the capacity by including or adding more RAM to that particular server. Now, in any environment, whether site reliability engineering or any infrastructure, it is inevitable that the changes are going to take place, and they are also necessary for innovation and growth. And this is what site reliability engineers do recognize, that changes will happen, they will take place. However, they also understand that change introduces risks and potentially disrupts the stability and reliability of a system. So for example, if you have an application running which is stable, users are able to access it, it is available round the clock, and absolutely there is no performance bottleneck. Now you upgrade that application to a newer version, but that is where the problem starts. So maybe there are code errors in that particular application, which is the newer version, or there are some other issues which are basically creating a performance bottleneck. So you have to understand these risks. And whenever you are doing a change, it is always better to test it out in the test environment before you roll it out into production or live environment. So now, to minimize the risks and ensure that there is no disruption to the stability and reliability of the system, SRE engineers focus on managing changes effectively to reduce these risks and ensure that changes are rolled out smoothly. Now, let's understand the concept of velocity. Velocity in SRE signifies the speed and efficiency with which changes can be delivered to production. It encompasses both the technical aspects of deployment automation and the organizational processes that enable rapid and safe releases. Now, SREs strive to strike a balance between velocity and reliability. While they aim to accelerate the delivery of new features and improvements, they also prioritize stability to ensure that changes do not compromise the overall system performance or availability. So basically, what they try to do is minimize the risk to ensure that systems performance and availability is not hampered. Let's now talk about the key factors that contribute to high velocity in SRE. So there is automation. Automating repetitive tasks like testing, deployment, and monitoring will reduce manual effort and accelerate the release cycle. Automation will also ensure that there are less number of defects because there is no manual effort that is getting involved and everything is consistent. Then there is continuous integration and continuous deployment, or CI/CD. Implementing CI/CD pipelines to streamline the code to production workflow will also increase the velocity. Then there are well-defined processes. Then there are well-defined procedures. You need to establish clear procedures for code reviews, testing, and deployment approvals to ensure quality and minimize errors. Let's now talk about reliability, which is the cornerstone of SRE. It refers to the ability of a system or service to perform its intended function consistently and accurately over time. Reliability encompasses of various aspects which can include availability, which is the percentage of a time system is up and running without interruptions. Then there is latency, which is the time it takes for a system to respond to requests. Then there are error rates, which are the frequency of errors or failures in a system. Then there is durability, which is the ability of a system to recover from failures and maintain data integrity. Let's now talk about the interplay of change, velocity, and reliability in SRE. Now, all these three, which are the change, velocity, and reliability, these three concepts are tightly integrated in SRE. Now, change is driving force behind the innovation and improvement. Velocity enables the rapid delivery of changes, but it must be balanced with reliability, which ensures that changes do not compromise the stability and performance of a system. Site reliability engineers continuously navigate this delicate balance, striving to achieve high velocity while maintaining exceptional reliability. By focusing on automation, well defined processes, and proactive monitoring, they empower organizations to deliver reliable and innovative services at scale. Now, just to quickly recap, we talked about the types of changes in SRE. We talked about the code changes, configuration changes, deployment changes, and scaling changes. Then we talked about velocity, we talked about reliability, and then we talked about the interplay of change, velocity, and reliability in SRE. In this topic, we are going to talk about service level indicators. So let's understand what they are. Now, when identifying key service level indicators for cloud services, it is essential for you to consider metrics that directly reflect the performance, reliability, and availability of the service. SLIs are quantitative measurements that represent specific aspects of services performance, and they play a crucial role in defining and monitoring service level objectives, which are SLOs, and service level agreements. So now we have understood what SLI is. We will look at the different metrics for identifying SLIs. Now, when identifying SLIs, it is essential to select metrics that align with these services' objectives, user expectations, and business goals. These SLIs serve as the foundation for establishing meaningful SLOs and SLAs, therefore, allowing organizations to set performance targets, track service performance, and prioritize improvements effectively. So let's look at some of these metrics. So there is performance metrics, reliability metrics, scalability metrics, security metrics, and user experience metrics. So let's look at these in the upcoming slides. Let's first talk about performance metrics. So there are different performance metrics. So there is response time that measures the time taken for service to respond to the requests. This metric indicates how quickly the service can handle user interactions. So for example, if you try to access a particular web application or a web page, but then the load time of that particular application or web page is pretty slow. So that means the response time is not what you would have thought it would be. The next one is latency that reflects the delay between the time a request was sent and the time when a response was received. Lower latency signifies better performance. So, for example, if you send a ping request to a remote server on the internet, now if the response time is in few hundred milliseconds, obviously there is a latency problem here. Now, if the response time is in few milliseconds, then there is a lower latency, which means that the access to the server is pretty quick and the server is performing well. Then there is throughput, which represents the rate at which a service processes requests or transaction. Higher throughput indicates better efficiency. Let's now talk about reliability metrics. So there is error rate that tracks the percentage of failed requests or transactions over a specific time period. Lower error rate indicates higher reliability. Now, if you're trying to access a website, out of 10 times you access, 6 times it is not able to respond back. So the error rate is about 60%. Then there is availability, which measures the percentage of time when the service is operational and accessible to users. High availability ensures better reliability. Now, again, out of 10 times, 6 times the web server is down or the web application is not available. So there is only 40% availability of that particular web application or the web page or the server. Then there is uptime and downtime. that quantifies the duration when the service is available or unavailable. Maximizing uptime and minimizing downtime are crucial for reliability. Then there are scalability metrics. So there is resource utilization that monitors the utilization of computing resources such as CPU, memory, and storage. Efficient resource utilization ensures scalability and cost effectiveness. Then there is scalability testing results that evaluates how well a service handles increased workload or user demand. It helps anticipate performance issues under load. Then there are security metrics. So there are security breaches that track the frequency and the severity of security incidents, including unauthorized access, data breaches, and vulnerabilities. Then there is compliance that measures a service's adherence to industry regulations and security standards. Compliance metrics ensure data protection and regulatory compliance. Then there is user experience metrics. So there is user satisfaction that gauges user satisfaction through surveys, feedback, or Net Promoter Score or NPS. Positive user feedback indicates a good user experience. Then there is user retention that measures the percentage of users who continue to use the service over time. High user retention reflects a positive user experience. So, for example, if you have taken a subscription of a particular web application and it is a monthly payout, now after 1 month, you realize that you don't really like that web application and you want to switch over to something else. That means the company is going to lose you as a user. So there is an impact on user retention. Now, when you opt for the second web application and you like that particular web application, it's easy to use, it gives you better performance, and it is available all the time. That means there is a positive user feedback that you can give it to the company, and because you are happy, it is more likely that you are going to be their customer for the next month or month after. So which means the company will have a higher user retention, so there will be other users who are thinking on the same lines as you, so company has better user retention. Just to quickly recap, in this particular topic, we talked about service level indicators or SLIs. We also talked about identifying SLIs based on different metrics. We talked about performance, reliability, scalability, and security metrics. We also talked about the user experience metrics. In this particular topic, we are going to talk about service level objectives or SLOs and service level agreements or SLAs. So let's get started by comparing both of them. So we are going to compare SLOs with SLAs on various aspects. So we are going to talk about purpose, measurement, and enforceability. So now, service level objectives or SLOs are specific and measurable targets set by an organization to define the desired level of performance or reliability of a service. SLOs are based on key metrics known as SLIs or service level indicators, which quantify aspects such as response time, error rate, and uptime. SLOs provide a clear benchmark for evaluating whether a service meets the expected standards. They are used internally within an organization to guide service improvements, monitor performance, and ensure that the user expectations are met. Now, because they are used internally within an organization, they are not legally binded documents or standards. Now, when you talk about SLAs or service level agreements, they are formal contract between a service provider and a customer that define the expected level of service. SLA outlines the specific SLOs that must be met and include penalties or remedies if these objectives are not achieved. SLAs are legally binding and ensure that there is a mutual understanding of the service expectations, including performance metrics, responsibilities, and consequences for failing to meet the agreed standard. Let's now talk about the key aspects of SLO. So there are targets. You have to clearly define goals for each SLI. For example, it could be 99.9% uptime for a internal application. Then there is measurement, which is the quantitative data that can be monitored and reported. Then there is user focused, which is the reflection of the performance aspects that are most important to users. Then there are actionable, which are helpful in making decision about changes and improvements. Let's talk about this in an example. An SLO might state that a web application should have an uptime of 99.9% and a response time of under 100 milliseconds for 95% of the requests. And obviously, when you gather the data, you can actually measure whether these SLOs were met or not. Let's talk about the key aspects of SLAs. So, the first one is commitments. These are the binding promises about service performance. So, it could be uptime or response time. Then there are penalties, which are defined consequences if the service provider fails to meet the commitment. For example, financial compensation or service credits. Let's take a quick example here. A vendor promises to deliver a particular hardware component within 10 days. Now, that is the SLA you have. But if that vendor does not deliver that hardware component within 10 days, then you can impose a penalty, which could be 10% discount on that particular component's price. Then there is scope, which is the detailed description of the services covered by the agreement. Then there are responsibilities, which are roles and obligations of both the service provider and the customer. Let's talk about an example. An SLA might guarantee that cloud storage service will be available 99.95% of the time, and if this target is not met, the customer will receive a credit or a refund. Let's talk about the key differences between SLAs and SLOs. So, when you talk about the scope, SLOs are internal targets used to guide performance, while SLAs are formal agreements between the organization and the vendor, or it could be with an external customer. Then there is enforceability. Now, SLAs are legally binding with specified penalties, where SLOs are not legally binding, but they serve as performance benchmarks. Then there are audiences. SLOs are primarily for internal use within an organization, while SLAs are for external use between a service provider and its customer. Now, by defining SLOs and SLAs, organizations can ensure they are both meeting internal performance standards and fulfilling their contractual obligations to customers. Let's talk about the process for defining SLOs. So there are essentially 5 steps, but it depends from organization to organization how they want to define it. But broadly, when you talk about it, there are mainly 5 steps. So first one is you understand user expectations. You need to start by understanding the expectations and requirements of your users. This involves identifying what aspects of the services are most critical to them. Now, these aspects could include performance, reliability, availability, and responsiveness. Then there are identify key metrics. Once you understand user expectations, identify the key SLIs that directly reflect those aspects of the service. These SLIs are quantitative measurements such as response time, error rate, and uptime percentage. Then there are set targets. Based on the identified SLIs, you need to set specific and measurable targets for each metric. These targets represent the desired level of performance or reliability that the services should achieve. For example, you might want to set a target of 99.9% uptime or response time of less than 100 milliseconds. The next step is establish thresholds. You need to define acceptable thresholds or boundaries related to each target. These thresholds indicate the acceptable range of performance or reliability. For example, if the target response time is 100 milliseconds, you might establish a threshold of 150 milliseconds as the upper limit of acceptability. Then there is document SLOs. You need to document the defined targets and thresholds for each SLIs as SLOs. that provide a clear and measurable definition of the service's expected level of performance and reliability. Let's now talk about the significance of SLAs. So, they formalize expectations. SLAs formalize the expectations and commitments between service providers and customers. They define the agreed upon level of service, including performance, reliability, availability, and support. SLAs also establish accountability by outlining the responsibilities of both parties. Service provider commit to meeting the defined SLOs while customers agree to certain terms and conditions such as payment terms and dispute resolution processes. Then there is quality of service. SLAs ensure the quality of service by providing clear benchmarks and standards for performance and reliability. They serve as a basis for monitoring and measuring the service's performance and holding service provider accountable for any deviations from the agreed upon levels. Then there is manage expectations. So SLAs help you manage expectations by providing transparency and clarity about what customers can expect from the service. They outline the consequences of failing to meet SLOs, such as penalties, service credits, or termination clauses. Then there is drive continuous improvement. SLAs drive continuous improvement by setting targets and incentivizing service providers to continually enhance the quality and identify areas for improvement and drive corrective actions. Let's now talk about the relationship between SLIs, SLOs, and SLAs. Now, SLIs are the raw metrics you measure to assess your service's performance. SLOs are the targets you set for those metrics to ensure user satisfaction. SLAs are the formal agreements you make with customers based on your SLOs. Now, just to quickly recap in this particular topic, we started out with comparison of SLOs and SLAs. Then we talked about key aspects of SLO. We also talked about key aspects of SLAs. Then we talked about key differences between SLAs and SLOs. Then we also talked about defining SLOs. And finally, talked about significance of SLAs and towards the end we also covered relationship between SLIs, SLOs and SLAs. In this particular topic, we are going to talk about the strategies for managing service life cycle. So let's talk about the service lifecycle management strategies. Now, there are two types of service lifecycle management strategies, which is deployment and maintenance strategies. Let's go ahead and look at both of them in detail in the upcoming slides. So let's start with the deployment strategies. Now, we did talk about deployment strategies earlier. Now, just to reiterate, they are the following. So there is canary deployment, which involves gradually releasing a new version to a small subset of users or traffic, therefore allowing real-world testing while minimizing potential issues. GCP facilitates this release with tools like Manage Instance Groups or MIGs and Cloud Deploy. Then there is blue-green deployments, which maintains two identical environments where a new version is deployed and tested in the green environment before switching all traffic to it from the blue environment. GCP load balancers and Cloud Run simplify this process. Then there is rolling updates, which progressively replace instances of an old version with a new one, ensuring minimal downtime and maintaining service availability. GCP supports this replacement with MIGs and Kubernetes, which is Google Kubernetes Engine or GKE, therefore allowing controlled and efficient rollouts. Each of these strategies offer a unique benefits and can be chosen on specific requirements and constraints of the application and operational environment. Now, other than these three strategies that are listed on the slide, there are two more strategies that can be used in different scenarios. So there is feature flags. You can deploy new features but keep them hidden behind feature flags. This allows you to activate or deactivate features for specific user groups or at specific times. therefore enabling controlled experimentation and reducing the risk of failed deployments. Then there is A B testing, in which you deploy multiple versions of a feature simultaneously and direct a portion of traffic to each version. This helps you evaluate the performance and user response of different versions before deciding on a final implementation. Let's now talk about the maintenance strategies, and there are several of them. So let's start with monitoring and alerting. You need to continuously monitor your service's health, performance, and key metrics such as response time, error rate, and resource utilization. You can set up alerts to identify anomalies or issues before they impact users. Then there is logging and tracing. You need to collect logs and traces to gain insights into how your service is performing and troubleshoot problems. Centralized logging and distributed tracing tools can help you correlate events across different components of your system. Then there is incident management. You need to have a well defined incident management process in place to quickly identify, diagnose, and resolve issues when they occur. This includes clear roles and responsibilities, communication channels, and escalation procedures. Then there is capacity planning. You need to regularly review and adjust your service capacity based on use patterns and growth projections. This ensures that the service can handle increased traffic and load without sacrificing performance. Now, in continuation from the previous slide, let's look at some more maintenance strategies. Then there is automated testing. You need to implement automated testing throughout your development and deployment processes to catch bugs and perform regression early. Testing includes unit tests, integration tests, end to end tests, and performance tests. Then there is patch management. You need to keep your software and dependencies up to date with the latest security patches and bug fixes. You need to automate patch deployment wherever possible to reduce manual effort and minimize risk. Then there is backup and disaster recovery. You need to regularly back up data and configurations so that you can quickly recover from unexpected failures or data loss. You need to test your disaster recovery procedures regularly to ensure they are effective. Let's now talk about continuous improvement. So there are feedback loops. You need to gather feedback from users, stakeholders, and internal teams to understand how your service is being used and identify areas for improvement. Then there is post incident reviews. You need to understand thorough post incident reviews after any significant issue to understand the root cause, identify contributing factor, and implement preventive measures. Then there is performance optimization. You need to continuously analyze service performance and identify bottlenecks or areas for optimization. This could involve code refactoring, database tuning, or caching strategies. Then there is technical debt management. You need to actively address technical debt to prevent it from accumulating and impacting your services, maintainability, and performance over time. Now, just to recap, we talked about service life management strategies, which included deployment and maintenance strategies. We talked about different types of deployment strategies, which included canary deployment, blue green deployment, rolling updates, feature flags, and A B testing. We also talked about various maintenance strategies, which included monitoring and alerting, logging and tracing, incident management, capacity planning, and then we moved on to talk about automated testing, patch management, and backup and disaster recovery. And finally, we talked about continuous improvement, which included feedback loops, post incident reviews, performance optimization, and technical debt management. In this particular topic, we are going to talk about capacity planning and auto scaling in Google Cloud Platform or GCP. So let's get started with capacity planning first. Now, before we move ahead, we need to understand what capacity planning is all about. Capacity planning involves forecasting the resources your applications will need to handle the expected workloads. It's a proactive approach that helps you ensure that your services remain responsive and available even during peak usage periods. So, there are certain activities that you would do to ensure that you have done optimal level of capacity planning. So, there is resource estimation. You need to analyze historical usage patterns, traffic trends, and anticipated growth to estimate the required resources, which could be compute, storage, or network bandwidth for your applications. Then there is performance testing. You need to conduct load testing and stress testing to understand how your applications perform under various load conditions. This helps you identify potential bottlenecks and optimize your infrastructure accordingly. Then there is resource allocation. You need to allocate the estimate resources based on your performance testing results. You can utilize GCP's wide range of compute instances, storage options, and networking configurations to tailor your infrastructure to your specific needs. Then there is monitoring and analysis. You need to continuously monitor your resource utilization to identify trends, anticipate future needs, and optimize your capacity planning strategy. Let's now talk about the considerations for capacity planning. So, capacity planning involves forecasting and allocating resources to meet the current and future demands effectively. In GCP, capacity planning is essential for ensuring that your infrastructure can handle varying workloads while maintaining optimal performance and cost efficiency. So, here are some considerations. So, first one is the workload patterns. You need to begin by analyzing historical data and understanding the patterns of your workloads. You need to identify peak usage times, seasonal fluctuations, and any trends that may impact resource demands. The next is estimation of resource requirements. Based on your workload patterns and growth projections, you need to estimate the resources required to support applications and services. This includes computing resources, which could be your CPU or memory, storage capacity, and network bandwidth. Then there is right sizing resources. You need to optimize resource allocation by right sizing instances and services to match workload requirements. You need to utilize tools like Google Cloud's compute engines, right sizing recommendations to identify over provisioned or under provisioned instances and adjust them accordingly. Then there is scalability considerations. You need to plan for scalability by designing your architecture to scale horizontally or vertically based on demand. You can utilize managed services like Google Kubernetes Engine or GKE for containerized workloads or Google App Engine for serverless applications, which automatically scale resources based on traffic. Then there is performance monitoring. You need to continuously monitor the performance of your infrastructure and applications using GCP's monitoring and logging tools. You can track key performance metrics like CPU utilization, memory usage, and network traffic to identify bottlenecks and adjust resource allocation accordingly. Then there is cost optimization. You need to consider cost implications while planning capacity. You can use tools like Google Cloud's pricing calculator to estimate costs and optimize resource usage to minimize expenses while meeting performance requirements. Let's now talk about autoscaling. Autoscaling allows your infrastructure to automatically adjust resources based on real-time demand, therefore ensuring optimal performance and cost efficiency. Autoscaling complements capacity planning by dynamically adjusting your resources based on real-time demand. It ensures that you have enough resources to handle peak traffic without over-provisioning during periods of low demand. Let's look at the types of autoscaling in GCP. So there is horizontal autoscaling, which adds or removes instances which are virtual machines or containers based on demand. This is suitable for stateless applications that can be easily scaled out or in. Then there is vertical autoscaling, which increases or decreases the resources, something like CPU or memory of individual instances. This is useful for applications that are not easily scalable horizontally. Then there are managed instance groups or MIGs. GCP's MIGs provide built-in auto-scaling capabilities based on various metrics like CPU utilization, load balancing capacity, or custom metrics. Then there is Google Kubernetes Engine or GKE autoscaling. GKE offers cluster autoscaling to adjust the number of nodes in a cluster and horizontal pod autoscaling to scale individual pods within the cluster. Let's now talk about the settings for autoscaling. So there are autoscaling policies. You can define policies that specify when and how to scale your resources. You can configure scaling based on various metrics such as CPU utilization, request rates, queue lengths, or custom metrics from cloud monitoring. Then there is scaling limits. You can set minimum and maximum instance counts or resource limits to prevent overspending and ensure availability. Then there is cooldown periods. You can define cooldown periods to prevent excessive scaling actions in response to short-term fluctuations in demand. Let's now talk about the considerations for autoscaling. So there is application architecture. You need to understand your application scaling characteristics, which could be stateless or stateful, to choose the appropriate autoscaling approach. Then there is monitoring metrics. You need to carefully select the metrics that best reflect your application's performance and user experience. Then there is testing. You need to thoroughly test your autoscaling policies to ensure they work as expected under different load conditions. Then there is cost management. You need to monitor your costs closely to ensure that autoscaling is not leading to unexpected expenses. Let's now talk about the benefits of capacity planning and autoscaling. So there is cost optimization. Capacity planning and autoscaling avoid over provisioning by scaling resources based on actual demand and reducing unnecessary expenses. Then there is performance optimization. Capacity planning and autoscaling ensure that your applications have the resources they need to perform optimally even during peak traffic. Then there is improved reliability. Capacity planning and autoscaling can prevent downtime due to resource exhaustion by scaling up during peak loads. Then finally, you have simplified management. Capacity planning and autoscaling automate resource allocation and scaling, and thereby freeing up your team to focus on other tasks. Now, just to quickly recap, in this topic, we talked about capacity planning, we talked about considerations for capacity planning, and then we moved on to talking about autoscaling, settings for autoscaling, which included autoscaling policies, scaling limits, and cooldown periods. And then we talked about considerations for autoscaling. And then finally, we talked about the benefits of capacity planning and autoscaling, which included cost optimization, performance optimization, improved reliability, and simplified management. The success of DevOps team, which implements SRE principles, hinges on its ability to foster open communication, seamless collaboration, and a shared sense of purpose. In this topic, we are going to talk about key strategies that are prioritized for maximum impact. Teams can break down silos, accelerate innovation, and deliver high-quality software solutions efficiently. These strategies not only address the technical aspect of collaboration, but also emphasize the importance of building a healthy team culture that values transparency, continuous learning, and mutual support. So let's get started with these key strategies. The first one is clear communication channels. You need to select a primary platform, which could be something like Teams or Slack, where all team members are active and responsive. You should use these channels for specific topics, which could be deployments or incidents, to keep discussions organized. Then, you should set expectations for response times and escalate urgent issues to avoid delays. The next one is transparency and openness. You need to encourage a blame free culture where mistakes are seen as learning opportunities. You need to create safe spaces for team members to voice concerns, ask questions, and challenge ideas constructively. You should regularly share progress updates, roadblocks, and lessons learned to build trust and understanding. Let's now talk about shared goals and objectives. You need to clearly define the team's mission, vision, and key performance indicators or KPIs. You should ensure everyone understands how their individual work contributes to the bigger picture. Then you need to regularly review and adjust goals to stay aligned with business priorities. The next one is regular team meetings. You should hold daily stand up meetings for quick updates and identify blockers. You should also schedule weekly or bi weekly team meetings for deeper discussions, planning, and retrospectives. Then, you should also vary the team meeting format to keep meetings engaging. For example, it could be presentations or even brainstorming sessions. The next one is cross functional collaboration. You should organize cross functional workshops and training sessions to share knowledge and skills. You should create opportunities for informal interactions between teams, for example, coffee chats or lunch and learns. Then you should also encourage a one team mentality where everyone works towards a common goal. Let's now move to the next slide and look at some more strategies. In continuation from the previous slide, let's look at the rest of the strategies. The next one is feedback loops. You should conduct regular surveys or retrospectives to gather feedback on team processes and dynamics. You should actively seek inputs from team members on one-on-one basis and then act on feedback promptly to show that you value their opinions. The next one is documentation and knowledge sharing. You can use a wiki, a knowledge base, or similar tool to centralize information. You should encourage team members to document their work, processes, and learning, and then you should also make it easy to search for relevant information. Then there is remote collaboration. It is essential that you invest in high quality video conferencing and screen sharing tools. You should use virtual whiteboards for brainstorming and visual collaboration. You should also set clear guidelines for communication and expectations for remote team members. The next one is continuous learning and development. You should provide budget and time for team members to attend conferences, workshops, and online courses. You should offer opportunities for internal knowledge sharing, such as lunch and learn or brown bag sessions, and encourage experimentation and learning from failures. The last one is assessment of success and failures. You should recognize and reward individuals and team achievements. You should also encourage a culture of experimentation where failure is seen as an opportunity for growth, and you should also analyze failures to understand root causes and prevent future occurrences. Let's now talk about the challenges for DevOps teams and solutions. So, there is a time constraint. Now, in the fast paced world of DevOps, where deadlines loom and tasks pile up, it is easy for essential collaboration and knowledge sharing to fall by the wayside. To counter this, teams must proactively schedule dedicated time for these activities. This can involve regular tech talks, pair programming sessions, brown bag lunches, or even hackathon or innovation days. By blocking time on everyone's calendar and treating these events with the same importance as project meetings, teams can foster a culture of continuous learning, improve communication, and ultimately enhance productivity. The next constraint or challenge is geographical distribution. The rise of remote work and globally distributed teams present unique challenges to collaboration. To bridge the geographical gap, teams should harness the power of virtual collaboration tools like video conferencing, chat platforms, and project management software. Scheduling overlapping working hours, even for a few hours a day, can enable real time discussions and problem solving. Additionally, asynchronous collaboration through Thorough documentation and regular virtual check-ins ensures everyone stays connected and informed. The next challenge is communication overload. We are constantly bombarded with messages from various channels. It could be emails, chat, project management tools, and much more. This can lead to information overload, making it difficult to find relevant information and potentially causing missed messages. To mitigate this, teams should centralize communication by choosing one or two primary platforms. You should establish clear guidelines for channel usage, customizing notification settings, and promoting concise communication practices can help you further streamline the flow of information and ensure everyone stays on the same page. The last challenge is conflicting priorities. Unclear roles and responsibilities can breed confusion, duplication of effort, and conflicts within a team. To avoid this, it is crucial to clearly define each team member's role and their contribution to overall goals. Utilizing tools like Reiki matrices and project charters can help clarify expectations. Encouraging open communication about workloads and priorities, along with a well defined escalation process for disagreements, will help you ensure that conflicts are addressed promptly and effectively. Just to quickly recap, in this topic, we talked about 10 different strategies for healthy communication and collaboration within the DevOps team. We also talked about some of the key constraints or the challenges for DevOps teams and solutions. So these challenges were time constraints, geographical distribution, communication overload, and conflicting priorities. In this topic, we are going to talk about the mitigation of incident impact in Google Cloud Platform and how it should have minimum impact on users and services. Now, GCP incidents, whether caused by human errors, software bugs, or infrastructure failures, can disrupt services and negatively impact users. To minimize this impact, a combination of proactive planning and reactive responses is crucial. So, we are going to talk about these. So, let's talk about proactive strategies to prevent incidents. So, there is design for resilience, there is monitoring and alerting, and there is incident response planning. So, let's get started with design for resilience. You should implement redundancy at multiple levels. So, it could be at the hardware level, software, or even at the data center level to ensure that if one component fails, others can take over seamlessly. Then comes the load balancing. You should distribute traffic across multiple instances to prevent one single instance from becoming overwhelmed. Then there is fault tolerance. You should design applications to gracefully handle errors and failures, therefore, automatically retrying failed operations or switching to backup resources. Then, as part of resilience, there is chaos engineering. You should proactively test your system's resilience by simulating failures to identify weaknesses and improve their ability to withstand unexpected disruptions. Let's now move to monitoring and alerting. As part of monitoring and alerting, you have comprehensive monitoring. You should monitor your infrastructure, application, and services for key metrics like CPU usage, memory, disk space, and network traffic. You should also monitor for error rates and latency. Then, as part of monitoring and alerting, you also have real time alerts. You can set up alerts to notify you immediately when thresholds are exceeded or anomalies are detected. This enables you to react quickly before issues escalate. Then there is log analysis as part of monitoring and alerting. You should analyze logs from various GCP services to identify patterns, trends, and potential problems before they cause disruptions. Let's now move to incident response planning. So, as part of incident response planning, you have incident playbooks. You should create detailed playbooks that outline the steps to take in various incident scenarios. This ensures a coordinated and efficient response when an incident occurs. Then, as part of incident response planning, you have on call rotations. You should establish on call rotations with clear escalation paths to ensure that someone is always available to address issues. Then there is communication channels as part of incident response planning. You should define communication channels to notify stakeholders, team members, and users about incidents and their progress. Let's now talk about the reactive strategies for incidents in GCP. So there is rapid detection. You should use dashboards that consolidate key metrics and provide a real time view of your system's health. You should also rely on alerts to trigger notifications when critical thresholds are breached. Then there is swift diagnosis. You should analyze logs and traces to quickly pinpoint the root cause of the issue. You should also use debugging tools. You can leverage GCP's debugging tools to inspect the state of your application and infrastructure. Let's now talk about mitigation and recovery. So there is rollbacks. If the incident was caused by a recent change, you can use Cloud Deploy or other tools to quickly roll back to a previous stable version. Then there is failover. If a resource fails, you can automatically switch traffic to redundant resources in another zone or region. Then you also have scaling. You should increase capacity to handle increased load or mitigate performance issues. Then there is incident communications, in which you should keep stakeholders and users informed about the incident's progress, estimated resolution time, and key workarounds available. Now, just to quickly recap, in this particular topic, we talked about the mitigation of incident impact in GCP. We talked about the proactive and reactive strategies. In proactive strategies, we talked about design for resilience, monitoring and alerting, and incident response planning. As part of reactive strategies, we talked about rapid detection, swift diagnosis, and mitigation and recovery. In this topic, we are going to talk about postmortem analysis of incidents. A postmortem analysis is a critical step in the incident management lifecycle. It is a structured review of an incident that aims to understand the root cause, identify contributing factors, and extract valuable lessons to prevent similar incidents in the future. Let's look at the steps that you need to follow for postmortem analysis. So, first one is the preparation. You need to gather the relevant information. You should collect all relevant data related to the incident, including logs, monitoring data, incident reports, and communication records. You should also assemble the team. You should invite key stakeholders involved in the incident, such as engineers, operators, managers, and customer support representatives. You should then clarify the goals of analysis. You should emphasize that the goal is to learn and improve, not to assign blame. You should create safe space for open and honest discussion. The next step is timeline reconstruction. You need to define the chronological order. You should build a detailed timeline of the incident, starting from the first sign of trouble to the resolution. You should also identify the key events, the actions taken, and the decisions made throughout the incident. Then you need to gather the supporting data, which could be reference logs, graphs, or other evidence to support the timeline. The next step is root cause analysis. You need to use the 5 whys techniques to drill down the underlying cause of the incident. You should ask why repeatedly until you reach the root cause or the root causes. You need to identify any factor that contributed to the incident, such as technical debt, process failure, human errors, or external events. The next step is impact assessment. So there could be user impact, there could be business impact. So for the user impact, you need to assess the impact of the incident on users, which could include downtime, data loss, performance degradation, or other negative consequences. For business impact, you need to evaluate the financial and reputational impact of the incident on the organization. The next step is lessons learned and action items. You need to document the key takeaways from the incident analysis. What went wrong? What went well? What could have been done differently? Then, based on this information, you need to create action items. You need to develop specific, actionable recommendations to prevent similar incidents in future. You need to prioritize the most impactful actions based on their potential to reduce risk and improve reliability. Then you need to assign ownership. You need to clearly assign ownership of each action item to ensure accountability and follow through. The last step is communication and documentation. You need to share the post-mortem report. You need to share the post-mortem findings with the relevant stakeholders, including team members, managers, and maybe sometimes the customers as well. Then you need to implement the changes. You need to track the progress of action items and communicate updates regularly. Let's talk about the best practices for postmortem analysis. By conducting effective postmortems, you can turn incidents into valuable learning opportunities, therefore, continuously enhancing the reliability and resilience of your systems and services. So, let's look at some of the best practices. So, first one is the blameless culture. You should focus on learning and improvement, not to blame anyone. Then there is timeliness. You should conduct the postmortem as soon as possible while the details are fresh. Once there is a delay, then the postmortem analysis may not be effective at all. Then there is thoroughness. You need to be comprehensive in your analysis, therefore, leaving no stone unturned. Then there is actionable recommendations. You should focus on creating specific, actionable items that can be implemented to prevent future incidents. Then there is continuous improvement. You should make postmortems a regular part of your incident management process to foster a culture of continuous improvements. Just to quickly recap, in this particular topic, we talked about the postmortem analysis and the steps that you need to perform. So there were basically 6 steps that were part of this. So there was preparation, timeline reconstruction, root cause analysis, impact assessment, lessons learned, and action items, and communication and documentation. And then we talked about the best practices for postmortem analysis, which included blameless culture, timeliness, thoroughness, actionable recommendations, and continuous improvement. Automation of toil and its impact on service reliability. In this topic, we are going to talk about toil. Now, what is toil? Now, toil is something that encapsulates the mundane and repetitive tasks that can consume a significant portion of site reliability engineers' time. These tasks, often manual and reactive in nature, include activities like routine server maintenance, responding to repetitive alerts, and performing manual deployments. While toil is an unavoidable aspect of keeping systems running smoothly, it's important to recognize its inherent limitations. Toil heavy work doesn't drive innovation, improve system design, or create lasting value. In fact, excessive toil can lead to burnout, stifle creativity, and hinder the team's ability to focus on strategic initiatives. The SRE philosophy emphasizes minimization of toil through automation and process improvements, therefore, freeing up engineers to focus on higher level tasks that contribute to the long term health and scalability of the system. Let's now talk about the effect of toil. Toil can have several negative consequences for both engineers and service reliability. So let's talk about these. The first one is the engineer burnout. Engaging in repetitive manual tasks can lead to fatigue, frustration, and ultimately burnout among engineers. This can result in reduced productivity, lower morale, and increased turnover. Then there is reduced innovation. Toil consumes time that could be better spent on creative problem solving, designing new features, or improving the overall system architecture. Then there is increased error rate. Repetitive manual tasks are prone to human error, which can lead to service disruptions, data loss, or security breaches. Then there is scalability challenges. As the service grows, the amount of toil required to manage it also increases, therefore creating a bottleneck for scalability. Let's now talk about automating toil. Automating toil is a cornerstone of the SRE philosophy, a strategic response to the challenges posed by manual, repetitive tasks. By leveraging automation tools and scripts, SRE teams can liberate their engineers from time consuming work of routine maintenance and reactive responses. This shift not only enhances the job satisfaction of engineers who can now dedicate their skills to more meaningful work, but also yields substantial benefits for the service itself. With reduced manual intervention, systems become more reliable, less prone to human error, and more easily scalable. Automation enables SRE teams to proactively address potential issues before they escalate, therefore, ensuring smoother operation and a better user experience. In essence, automating toil is just not about efficiency, it is about unlocking the true potential of SREs to innovate, optimize, and drive continuous improvements within their systems. Some examples of toil automation can be automated provisioning, testing, deployment, monitoring, alerting, and incident response. Let's now talk about the benefits of automating toil. There is improved engineer morale. Engineers feel more empowered and engaged when they focus on challenging and creative work instead of mundane tasks. Then there is increased innovation. By eliminating toil, SRE teams create more time for innovation, therefore, leading to improved features, better performance, and enhanced user experiences. Then there is reduced error rates. Automated processes are less prone to human error, therefore, resulting in more reliable and stable services. Then there is enhanced scalability. Automation enables services to scale more easily as demand increases without requiring a proportional increase in manual effort. Then there is minimized downtime. Automated tools can detect and respond to incidents faster than humans, therefore, minimizing the downtime and impact on use. Let's now talk about the challenges and considerations for automating toil. The first one is toil identification. Not all tasks are suitable for automation. It is important to prioritize automating tasks that are truly manual, repetitive, and have a significant impact on service reliability. Then there is automation overhead. Automating a task requires initial investment in development and testing. However, the long term benefits outweigh the initial costs. Then there is monitoring and maintenance. Automated processes require ongoing monitoring and maintenance to ensure they function correctly and adapt to changing needs. Just to quickly recap, we talked about toil in this topic, and then we talked about the effects of toil, which is engineer burnout, reduced innovation, increased error rate, and scalability challenges. Then we talked about automating toil and the benefits of automating toil. So we talked about benefits as improved engineer morale, increased innovation, reduced error rates, enhanced scalability, and minimized downtime. And then we also talked about the challenges and considerations for automating toil. The challenges were toil identification, automation overhead, and monitoring and maintenance. In this topic, we are going to talk about burnout and the strategies to prevent burnout. So let's get started. Now, in IT operations, where the pressure to maintain uptime and deliver seamless service is relentless, burnout poses a significant threat to individual well being and overall team performance, in addition to toil. The constant demands of troubleshooting, incident response, and system maintenance, often compounded by long hours, on call responsibilities, and high pressure environment, can quickly take a toll on even the most dedicated professionals. Burnout manifests not only in physical exhaustion, but also in emotional exhaustion, pessimism, and a decreased sense of accomplishment. To mitigate this risk and foster a healthy work environment, a variety of strategies can be employed. Let's look at them in the upcoming slide. So, let's talk about the strategies for a healthy work environment. Let's start with workload management. There should be a fair distribution of work.
You should ensure a balanced distribution of tasks and responsibilities amongst the team members. You should avoid overloading individuals with excessive work. Then you should also help them prioritize tasks based on urgency and importance. This prevents them from feeling overwhelmed by a long to do list. You should set realistic goals and deadlines that are achievable within normal working hours. You should avoid promoting a culture of overwork. Then you should also encourage delegation of tasks when appropriate. This empowers team members and prevents individuals from becoming bottlenecks. Let's now talk about the second strategy, which is skill development and growth. You must invest in ongoing training and development programs to help team members learn new skills and technologies. This keeps them engaged and motivated. You should also provide them with clear career path and opportunities for advancement within the organization. This gives team members a sense of purpose and direction. Then you should pair experienced team members with newer ones to provide guidance and support. This fosters a learning culture and helps new employees ramp up quickly. Let's talk about the next one, which is recognition and appreciation. You must provide regular feedback on performance, both positive and constructive. This helps team members understand their strengths and area for improvement. Then there should also be public recognition. You must acknowledge and celebrate individual and team achievements. This reinforces a sense of value and contribution. Then you should also offer rewards and incentives for either exceptional performance or going above and beyond. The next strategy is work life balance. You should offer flexible work arrangements like remote work, flexible hours, or compressed work weeks. This allows team members to better balance work and personal life. You should also promote regular breaks throughout the day to help team members recharge and avoid fatigues. You should also set clear expectations around overtime and discourage excessive work outside of normal hours. Then there is communication and support. You should have open communication channels. You should foster an environment where team members feel comfortable discussing challenges, stressors, and signs of burnouts. You should also schedule regular one on one meetings between managers and team members to discuss workload, well being, and career goals. Then you should also have employee assistance programs or EAPs that offer counseling and support services for employees who experience stress, anxiety, or other mental health challenges. The next strategy is stress reduction and wellness programs. You should conduct mindfulness and stress management trainings. You should offer workshops or training programs to help team members manage stress and develop coping mechanisms. Then there should be wellness initiatives. You should encourage healthy habits through initiatives like fitness challenges, healthy eating options, or ergonomic workstation assessments. Then there are team building activities. You should organize team building activities to foster fellowship and create a supportive environment. Let's now talk about comparing the strategies to address burnout. A multi pronged approach is crucial to address the pervasive issue of burnout within IT operations teams. Implementing effective workload management strategies directly tackles the root cause by promoting fairness and efficiency, though it may necessitate substantial changes in workflow or resource allocation. Now, investing in skill development and growth program enhances motivation and long-term career prospects, but might not provide immediate relief. This investment requires ongoing commitment. Recognizing and appreciating employee efforts can significantly boost morale, yet it is crucial to ensure these gestures are genuine and accompanied by meaningful actions. Encouraging a healthy work life balance, while essential for stress reduction and well being, may be challenging to implement in certain work environments or industries. Establishing open communication and support channels can create a safe space for discussing challenges and seeking help, but building a culture of trust and openness is paramount. Lastly, incorporating stress reduction and wellness initiatives can bolster resilience, but these may demand additional resources or might not fully address the underlying causes of burnout. Now, the most effective approach to prevent burnout often involves a combination of these strategies tailored to the specific needs and the culture of your organization. Regularly assess the effectiveness of your chosen strategies and be open to adjusting them as needed. By prioritizing employee well being and investing in multi pronged approach to prevent burnout, you can create a thriving work environment where operation teams are empowered, engaged, and equipped to deliver exceptional results. Just to quickly recap, in this particular topic, we talked about burnout. We also talked about several strategies for a healthy work environment. We talked about workload management, skill development and growth, recognition and appreciation, work life balance, communication and support, and stress reduction and wellness program. And then we compared these different strategies. So we talked about the pros and cons of different strategies. In this topic, we are going to talk about a case study about Acme Corp, which is a hypothetical organization, and they are an e-commerce company which is running an on-premises infrastructure, and they are facing a lot of challenges in terms of frequent downtime, slow response time, manual operations, and lack of visibility. Now, all this is happening because they had sudden growth. And as they scaled up their online platform, they did a lot of ad hoc implementation of their network, storage, servers. So there was nothing pre planned. Now, along with this came a lot of challenges. So there was frequent downtime. Now, platform experienced outages during peak hours or peak periods, leading to lost revenues and frustrated customers. Along with this came the slow response times. Now, pages of their online platform loaded slowly, which obviously affected the user experience and conversion rate. Then because this was sudden expansion, so there were a lot of manual operations that came into the play. Now engineers spent a lot of time in manual tasks like firefighting the incidents. So as and when servers went down, they were firefighting these incidents, or as the demand grew, they were scaling up the resources manually, which obviously took a lot of time. And on top of all this, there was lack of visibility. Now there was limited insight into root causes of incidents and performance bottlenecks. Now, finally, because their growth was now becoming a bottleneck because of these challenges, now Acme Corp decided to adopt the SRE principles and leverage GCP's tools and services. And we are going to see what solution they applied and what were the benefits they gained. So let's talk about the solution. Now, they established SLOs. So they defined SLOs for key metrics like availability, latency, and error rates. Now, along with this, they used cloud monitoring to track these metrics and set up alerts to notify site reliability engineers about the potential breaches and the bottlenecks. Then they built a reliable infrastructure in GCP or Google Cloud Platform. What they did was they migrated their infrastructure to GCP and leveraged managed services like Compute Engine, Cloud SQL, and Cloud Storage. They also implemented redundancy and failover mechanisms across multiple regions to ensure high availability. And along with this, they adopted infrastructure as code or IAC using Terraform to manage their GCP resources consistently and reliably. Then, along with this, they automated everything. They implemented CI CD pipelines using Cloud Build and Cloud Deploy to automate the build, test, and deployment process. And along with this, they automated scaling using managed instance groups or MIGs to handle traffic spikes and maintain performance. And they also created automated scripts and workflows to handle routine tasks like log rotation, backups, and certificate renewals. Now, for monitoring and observability, they set up comprehensive monitoring using cloud monitoring and cloud logging to collect logs, metrics, and traces from their applications and infrastructure. They also used Cloud Trace to trace requests across services and pinpoint performance bottlenecks. Along with this, they also created custom dashboards and alerts to visualize key metrics and receive notifications of potential issues. Along with this, they implemented incident management, which was probably one of the most implementation in the entire migration and adoption of SRE principles. They established on-call rotation and defined clear escalation paths for handling incidents. They also created detailed incident playbooks that outlined the steps to be taken for different types of incidents. Along with this, they conducted post incident reviews, which are postmortems, and we have talked about this to analyze root causes and identify improvements. Now, with these solutions that they implement in the GCP environment, they gained a lot of benefits. So, there was improved availability. The platform achieved 99.95% uptime, exceeding their SLOs and significantly reducing downtime. They also achieved faster response time. The page load time increased by 50%, therefore improving user experience and conversion rates. Then they also reduced manual effort with the help of CI/CD, where automation freed up engineers to focus on more strategic work, such as developing new features and optimizing performance. They also gained visibility into their infrastructure. The monitoring and logging systems provided deep insights into system behavior, therefore enabling faster incident resolution and proactive identification of potential problems. Now, this visibility came along with monitoring as well as putting up the custom dashboards. Then they also increased customer satisfaction. Now, with the improved reliability and performance, obviously brought in a lot of happier customer and increased sales. Now, just to quickly recap in this particular topic, we talked about Acme Corp, who had several challenges. They had frequent downtime, slower response time, manual operations, and lack of visibility with their on premises infrastructure, where their online platform was struggling to serve the customers. Now, to resolve this, they put up various solutions. So, they established SLOs, they built reliable infrastructure, they automated everything, and then they implemented monitoring, observability, and incident management. As an outcome, Acme Corp received a lot of benefits. So, they had improved availability, faster response time, reduced manual effort, improved visibility, and increased customer satisfaction. In this topic, we are going to talk about feedback loops, and then we are also going to talk about feedback loops for continuous improvement and implementing effective feedback loops. So, let's first understand what feedback loops are. Now, in service management and delivery, feedback loops are the methods or the mechanisms that enable organizations to gather information, analyze it, and use it to make iterative improvements in processes, products, and services. They are essential for maintaining high quality services, enhancing customer satisfaction, and driving innovation. Now, these loops may incorporate feedback from various sources, including customers, users, stakeholders, and internal teams to drive meaningful improvements and deliver greater value. So, let's look at each one of these. So, there is customer feedback. Now, this is the most direct and valuable form of feedback. It comes from surveys, reviews, social media mentions, support tickets, and direct interactions with the customers. Customer feedback provides insights into how users perceive the service, what they like and dislike, and what area needs improvement. For example, agile methodologies rely heavily on feedback loops to gather customer feedback, prioritize features, and iterate on product development. Then there is operational feedback. Now, this feedback comes from monitoring systems, logs, and performance metrics. It provides insights into technical health of the service, identifying bottlenecks, errors, and areas where optimization is needed. For example, support teams use feedback loops to identify common issues, improve response times, and enhance the overall customer experience. Another example can be of SRE team, which can be using monitoring tools and alerts to gather operational feedback, detect anomalies, and trigger automated responses. The next one is the employee feedback. Your employees, especially those directly involved in service delivery, have valuable insights into the strengths and weaknesses of the service. Regular feedback sessions and surveys can help gather this information. Then there is competitive feedback. Analyzing competitor offerings and industry trends can reveal areas where your service can be improved or differentiated from others in an industry. Let's now talk about feedback loops for continuous improvement. So, the first one is identifying issues. Feedback loops help pinpoint problems, whether they are technical glitches, usability issues, or customer dissatisfaction. This allows for early detection and prompt resolution. Then there is prioritizing improvement. By analyzing feedback, you can prioritize improvements based on their impact on user experience, business goals, and overall service quality. Then there is measuring progress. Feedback loops provide a way to measure the effectiveness of implemented changes. By tracking the key metrics and gathering feedback after changes, you can determine whether the improvements are having the desired effect. Then there is fostering a culture of continuous improvement. Regular feedback gathering and analysis instills a culture of continuous improvement within the organization. Employees are encouraged to identify problems, suggest solutions, and take ownership of their work. Then there is driving innovation. Feedback loops can spark new ideas and solutions. By listening to customers and understanding their needs, you can identify opportunities for innovation and create new features or services that deliver greater value. Let's now talk about implementing effective feedback loops. So, you need to establish clear channels. You need to create channels for customers, employees, and other stakeholders to provide feedback easily and regularly. This could include surveys, feedback forms, suggestion boxes, or regular meetings. Then you need to analyze and categorize feedback. You need to organize and analyze the feedback you receive. You need to identify patterns, trends, and recurring themes. You need to categorize feedback by different types, which could include technical, usability, or feature requests. And then you need to prioritize them. Then, next one is take action. You need to develop an action plan based on your feedback analysis. You need to assign owners to specific issues, set timelines for resolution, and track progress. Then there is communicate with stakeholders. You need to keep your stakeholders informed about the feedback you have received and the actions you are taking to address it. This demonstrates your commitment to improvement and builds trust. Just to quickly recap, in this particular topic, we talked about feedback loops. We talked about different types of feedback loops. So there is customer feedback, there is operational feedback, there is employee feedback, and there is competitive feedback. Then we talked about feedback loops for continuous improvement, which included identifying issues, prioritizing improvements, measuring progress, fostering a culture of continuous improvement, and driving innovation. And then we talked about implementing effective feedback loops, which included establishing clear channels, analyzing and categorizing feedback, taking action, and communicating with the stakeholder. Now, in this course, we covered a lot of different topics. We talked about SRE overview and the concept of change, velocity, and reliability. Then we talked about SLIs, SLOs, and SLAs. And then we talked about strategies for managing the service lifecycle. Along with this, we talked about capacity planning and auto scaling in GCP. We talked about healthy communication and collaboration within DevOps teams, and then mitigating and management of incidents. And finally, towards the end, we did talk about addressing toil and burnout in DevOps teams. We talked about a case study on Acme Corp on SRE practices. And then finally, we talked about the role of feedback loops in continuous service improvements. Now, what's coming up next? It is a course on implementing service monitoring strategies. In this course, you will learn how to effectively manage logs and metrics within Google Cloud Platform or GCP using powerful tools like cloud logging and cloud monitoring. You will master the configuration of the cloud logging agent, explore log collection from various sources, and learn to create custom metrics. You will also gain proficiency in setting up monitoring dashboards, configuring alerts based on SLOs and SLIs, and compare GCP's Prometheus offering with other solutions. Additionally,
you will deep dive into access controls and optimization strategies for efficient log management. Let's look at the objectives that you will be covering in this particular course. You will learn about the benefits and considerations of cloud logging and cloud monitoring. You'll also learn the concept of configuration of the cloud logging agent and its importance. Then, moving in the course, we'll also talk about the processes of collecting logs from outside Google Cloud and sending application logs directly to the cloud logging API. Moving on in the course, you will talk about the steps to create and analyze custom metrics from logs, then set up and customize monitoring dashboards in GCP. Moving on to the rest of the course, you will also learn about configuring alerting policies based on SLOs and SLIs, compare Google Cloud Managed Service for Prometheus and other monitoring solutions. Then, towards the end of the course, you will talk about distinguish between logging and monitoring access controls, assessing the applicability of the strategies for optimizing logs in different scenarios. Finally, towards the end of the course, you will learn about the benefits of enabling VPC flow logs for network monitoring. You'll also go through a case study of troubleshooting with cloud monitoring and cloud logging. And then finally, you will learn about the advanced log filters and their applications in the real world scenarios. In this course, you will learn how to diagnose, troubleshoot, and optimize service performance and costs within Google Cloud Platform or GCP. You will learn to master the use of GCP's operation suite, service mesh telemetry, and cloud trace for in-depth performance analysis. You will also learn to troubleshoot compute, deployment, runtime, and network issues. Later in the course, you will also learn to explore the optimization strategies using preemptible virtual machines, committed use discounts, and cloud profiler. Then you will learn about utilizing cloud monitoring and error reporting for effective application management and analyze case studies to streamline resource usage and reduce costs. Let's now look at the objectives. In this course, you will learn to identify methods for diagnosing service performance issues using Google Cloud's Operations Suite. And then you will learn about using service mesh telemetry to interpret service performance and strategies for troubleshooting compute resource issues in GCP. Then we are going to be talking about addressing deploy time and runtime issues with applications and the process for troubleshooting network issues using tools like VPC flow logs. Then we will talk about monitoring system performance by using cloud trace and compare preemptible virtual machines with committed use discounts for cost optimization. Then later in the course, we'll talk about implementing Cloud Profiler to identify performance bottlenecks and then also explore the role of cloud monitoring in tracking application performance. Then finally, towards the end, we will discuss a couple of case studies on optimizing resource utilization and reducing costs. And finally, we'll talk about the use of error reporting for managing application errors effectively and also the strategies for effectively using network tiers to optimize performance and costs. In this topic, we are going to talk about cloud logging and cloud monitoring. So let's get started. Now, cloud logging and cloud monitoring form the backbone of GCP's observability suite, offering a comprehensive solution for collecting, analyzing, and visualizing logs and metrics generated by your applications and infrastructure. So let's get started with cloud logging first. Now, cloud logging acts as a centralized repository for all logs generated by your GCP resources and applications. It provides powerful capabilities for managing, searching, analyzing, and alerting on your logs. So let's look at some of the key features. So first one is the log ingestion. Cloud logging automatically ingests logs from various GCP services such as Compute Engine, Kubernetes Engine, Cloud Functions, and many other services. You can also ingest logs from custom sources or external systems by using the logging agent or the API. Then there is log storage and retention. Logs are stored in scalable and durable manner with customizable retention policies to control how long logs are kept. You can export logs to cloud storage, BigQuery, or PubSub for long-term archival or further analysis. Then there is log search and filtering. Powerful search and filtering capabilities of cloud logging allows you to quickly find relevant log entries based on various criteria like timestamp, log levels, resource types, or custom labels. Then there are log-based metrics. You can create metrics from log data to track specific events or patterns. These metrics can then be used for alerting or visualization in cloud monitoring. Then there is log export and integrations. Cloud logging integrates with various tools and platforms, therefore enabling you to export logs to third-party systems, trigger alerts based on log events, or stream logs to real-time analysis platforms. Let's now talk about cloud monitoring. Cloud monitoring builds upon cloud logging by providing a unified platform for monitoring, alerting, and dashboarding your metrics and logs. Let's look at some of the key capabilities. First one is the collection of metrics. You can collect metrics from various sources, including GCP services, custom metrics, or external monitoring systems. Cloud monitoring automatically aggregates and processes these metrics for analysis and visualization. The next is custom dashboards. You can create custom dashboards to visualize key metrics and logs that are relevant for your applications and infrastructure. You can either use pre-built widgets or custom visualization to tailor the dashboards of your needs. Then there is alerting. You can define alerting policies based on threshold for your metrics. You can trigger notifications via email, SMS, or other channels when alerts are triggered, therefore enabling you to proactively respond to issues. The next one is uptime checks. You can monitor the availability of your websites or APIs from various locations worldwide, therefore ensuring your services are accessible to users. Then there are service level objectives or SLOs. You can define SLOs for your services and track their performance against those targets. Cloud monitoring helps you visualize your SLO compliance and identify areas for improvement. Then there is incident management. You can integrate with incident management tools to automate incident creation and escalation based on alerts. Let's now talk about leveraging cloud logging and cloud monitoring. Now, by combining cloud logging and cloud monitoring, you can achieve end-to-end observability of your GCP environment, and with this, you can do a number of tasks. So let's talk about the first one, which is troubleshoot issues faster. You can quickly identify and diagnose problems by correlating logs and metrics. Then you can proactively detect anomalies. You can set up alerts to detect unusual patterns in logs or metrics before they impact users. You can also optimize performance. You can analyze performance data to identify bottlenecks and optimize your applications and infrastructure. Then you can also ensure reliability with the combination of cloud logging and monitoring. You can track your SLOs and ensure that your services meet the expectations of your users. Let's now talk about the considerations for cloud logging and cloud monitoring. So the first one is log filtering and exclusion. You can use log exclusions and filters to control the volume of logs ingested and reduce costs. Then there are log-based metrics. You can leverage log-based metrics to gain deeper insights into specific events or behaviors within your logs. Then there are alerting strategies. You can fine tune your alerting policies to avoid alert fatigue and ensure that you are notified only about critical issues. Then there is integration with other tools. You can integrate cloud logging and cloud monitoring with your existing monitoring, alerting, and incident management tools to create a unified observability platform. Just to quickly recap, in this particular topic, we talked about cloud logging and its features. We talked about cloud monitoring and its features. We also talked about leveraging cloud logging and monitoring. And then we talked about the consideration for cloud logging and cloud monitoring which included log filtering and exclusion, log based metrics, alerting strategies, and integration with other tools. In this topic, we are going to be talking about the methods for diagnosing service performance issues. Now, Google Cloud's Operations Suite offers a powerful set of tools to identify and resolve performance issues in your applications and services. So, let's look at these methods. So, first one is monitoring metrics. You need to carefully select metrics relevant to your application's performance. So these metrics could involve such as response time, latency, throughput, error rates, and resource utilization, which could be your CPU, memory, or disk. You also need to define custom metrics to track specific aspects of your application's behavior that aren't covered by the standard metrics. Now, this would depend whether you actually need the custom metrics or not. So, accordingly, depending on your application's behavior or any specific business requirement you would have, you would want to define custom metrics. Then you would set up alerts based on predefined thresholds to be notified promptly when performance deviates from the expected levels. So you would need to know that immediately if there is any kind of performance deviation. Once that happens, you need alerts to be executed promptly so that you can proactively take care of the issue before it multiplies. The next one is logging and tracing. You need to analyze log data for errors, exceptions, warnings, and unusual patterns that can indicate potential performance problems. You can also use traces to visualize the flow of requests across different services and components, therefore revealing bottlenecks and latency hotspots. You can also use structured logging formats like JSON to make log analysis easier and enable powerful querying and filtering capabilities. The next method is distributed tracing. Now, you would need to implement distributed tracing to gain end-to-end visibility into request journeys across microservices and components. You would need to ensure proper context propagation in your distributed tracing implementation to accurately correlate events and trace requests across service boundaries. The next method is anomaly detection. You can leverage Google Cloud's anomaly detection capabilities to automatically identify unusual patterns in metrics and logs that might not be easily spotted through manual analysis. You also need to fine-tune anomaly detection thresholds and algorithms based on your application's performance and performance characteristics. Let's move to the next slide and look at some more methods. Now, in continuation from the previous slide where we talked about several methods for diagnosing service performance issues, let's continue and talk about some more methods for diagnosing service performance issues. So the next one is performance profiling. You can use Cloud Profiler to gain deep insights into the CPU and memory usage of your production applications, therefore identifying functions or code paths that consume excessive resources. You can also optimize your code based on profiling data to reduce resource consumption and improve performance. Then the next method is synthetic monitoring. You can set up synthetic tests that simulate real user interactions with your applications from different geographic locations. Synthetic monitoring allows you to detect performance degradation before real users are affected, therefore ensuring a consistent experience. The next one is integration with DevOps workflow. You can automate the deployment of monitoring configurations, alerts, and dashboards as part of your CI/CD pipeline using tools like Google Cloud Build and Cloud Deployment Manager. You can also leverage infrastructure as code or IAC to maintain consistency and version control. Then there is collaborative analysis. Google Cloud's Operations Suite provides a centralized platform for sharing monitoring data, logs, and traces across teams. You can use this to foster collaboration between development, operations, and support teams to quickly diagnose and resolve performance issues collectively. Now, just to quickly recap in this particular topic, we talked about several methods for diagnosing service performance issues. So we talked about monitoring metrics, logging and tracing, distributed tracing, anomaly detection, And then we talked about performance profiling, synthetic monitoring, integration with DevOps workflow, and collaborative analysis. In this topic, we are going to talk about the cloud logging agent and its importance. Let's talk about cloud logging agent first. Now, it is also known as Google Fluent D, and it is a powerful tool that enables the collection and forwarding of logs from various sources, which could be your virtual machines or even the on premises servers. Now, all this information or logs are forwarded to cloud logging. This centralized log management tool allows you to store, search, analyze, and monitor logs across your entire GCP environment. Now, Cloud Logging Agent can collect log data from various sources into Cloud Logging Service. It is primarily designed for environments where native integration with cloud logging isn't possible or feasible, or in scenarios where additional customization and control are desired. Let's talk about the importance of cloud logging agent. So there is centralized log management. The cloud logging agent enables centralized log management by collecting logs from all virtual machines and instances in your GCP environment and sends them to the cloud logging tool. This ensures that all log data is stored in a single centralized repository and therefore makes it easier to search, analyze, and monitor. Then there is real time monitoring and analysis. By continuously collecting and forwarding logs in real time, the cloud logging agent facilitates real time monitoring and analysis of system events, errors, and performance metrics. This allows organizations to quickly detect and respond to issues as they occur, therefore, minimizing the downtime and impact on users. Then there is compliance and auditing. Centralized log management provided by a cloud logging agent helps organizations meet compliance requirements and conduct auditing activities. By retaining and securely storing log data, organizations can demonstrate adherence to regulatory standards and internal policies. Then there is troubleshooting and debugging. Logs collected by cloud logging agent are invaluable for troubleshooting and debugging issues in distributed systems. They provide detailed insights into system behavior, error messages, and application performance, therefore helping engineers identify and resolve issues faster. Then there is integration with GCP services. The cloud logging agent integrates seamlessly with other GCP services, which could be cloud monitoring or BigQuery. Now, these are just two examples. This allows organization to correlate log data with performance metrics, create custom dashboards, and perform advanced analytics for deeper insights into system health and behavior. Let's now talk about the steps for configuring cloud logging agent. So you start with the installation, you install the cloud logging agent on the machines or virtual machines from which you want to collect logs. GCP provides detailed instructions and packages for various operating systems. Then you have to create the configuration file. The agent's behavior is controlled by this particular configuration file, which is usually located at /etc/google-fluentd/google-fluentd.conf on Linux systems. And if you talk about Windows, now on Windows, it is located in program files x86 slash stack driver slash logging agent slash fluent.conf. Now, this is basically, these are two different paths, one on Linux and one on Windows. Now, what does this file hold? This file defines the sources, which is the location or services from which the log needs to be collected. It also defines parsers, which help you interpret and structure log data into fields and labels for easier searching and filtering. Then it also defines filters, which are rules for including or excluding certain log entries based on their content or attributes. Then it defines the destinations, where to send the collected log data. So, for example, it could be cloud logging where you want to send your data. The next step is the customization
of configuration file. Now you can customize the configuration file to add or remove sources. You can define custom parsers. You can set filtering rules, add labels, or even modify buffering or retry settings. The final step is monitoring and maintenance. You need to regularly monitor the agent's logs and health status to ensure it's functioning correctly. You need to update the agent periodically to benefit from new features and bug fixes. Just to recap, we talked about what cloud logging agent is. We also talked about the importance of cloud logging agent, in which we talked about centralized log management, real time monitoring and analysis. We talked about compliance and auditing, troubleshooting and debugging, and integration with GCP services. And finally, we talked about the steps for configuring the cloud logging agent. So we talked about installing the cloud logging agent, creating the configuration file, customizing the configuration file, and performing monitoring and maintenance.
In this topic, we are going to talk about service mesh telemetry. Now, in a microservices architecture where applications are composed of numerous independent services that communicate with each other, gaining insights into performance of these services and their interactions is crucial. These insights can be gained using service mesh telemetry, which is provided by platforms like Istio. It offers detailed insights to diagnose bottlenecks and optimize efficiency and ensure a seamless user experience. Now, let's talk about what service mesh telemetry is all about. Service mesh telemetry involves collecting and analyzing data generated by service mesh's sidecar proxies. These proxies are deployed alongside each microservice to manage and monitor the communication between services. The telemetry data typically includes various pieces. So first one is the metrics, then there is logs, and then there are traces. So let's start with metrics. Now, metrics is basically the quantitative measurement of service behavior. It could be such as request latency, error rates, throughput, and resource consumption, which would be typically your CPU, memory, or disk utilization. So there is request latency, which measures the time it takes for a request to travel from the client to the service and back. Lower latency indicates better performance. Then there are error rates, which track the frequency of errors occurring in the service, which helps identify reliability issues. Then there is throughput, which measures the number of requests processed by a service within a given time frame, therefore indicating the service's capacity. Then there is resource consumption, which monitors the usage of resources such as CPU and memory by each service, which helps in optimizing resource allocation. Then there is logs, which are the detailed records of events and activities within the service mesh, including request response details, error messages, and debug information. Let's look at event records, which are the captured detailed information about events and activities within the service mesh, such as request response details and error messages. Then you have the debug information that has in-depth insights into the internal working of the service, and it is useful for troubleshooting and identifying the root causes of issues. Let's now talk about the third piece, which is traces. This is the end-to-end representations of requests as they flow through multiple services, therefore capturing timing and dependency information. Now, end-to-end request tracing represents the journey of a request as it travels through multiple services, therefore capturing timing and dependency information. Then there is dependency mapping, which helps in visualizing how services interact with each other, therefore making it easier to identify and resolve performance bottlenecks. Let's now talk about the uses of service mesh telemetry. Service mesh telemetry plays a crucial role in interpreting service performance by providing comprehensive insights into the behavior and interactions of services within a distributed system. So let's talk about the use cases or the uses of service mesh telemetry. So the first one is collection of metrics. Service mesh telemetry collects various metrics related to the performance and behavior of microservices, such as latency, throughput, error rates, and resource utilization. These metrics are gathered from each service instance and are aggregated and stored for analysis. Then there is traffic monitoring. Telemetry data includes information about traffic patterns between services such as volume of requests, response times, and error codes. By monitoring traffic, teams can identify bottlenecks, detect anomalies, and optimize service to service communication. Then there is distributed tracing. Service mesh telemetry enables distributed tracing, which tracks the flow of requests as they propagate through microservices architecture. Traces provide visibility into the end-to-end journey of a request, therefore highlighting the path it takes across different services and identifying latency hotspots and dependencies. Then there is error detection and debugging. Telemetry data captures error and exception logs generated by individual service instances. By analyzing these logs, teams can quickly detect errors, diagnose root causes, and debug issues in real time, therefore improving the reliability and resilience of the system. Let's now move to the next slide to look at some more uses of service mesh telemetry. So, in continuation of the previous slide where we talked about various uses of service mesh telemetry, we'll just continue on this slide and talk about more uses. So, the next one is the performance profiling. Telemetry tools often include performance profiling capabilities, therefore, allowing team to analyze the CPU, memory, and network use of each service instance. Performance profiles help identify resource intensive operations, memory leaks, and inefficiency that impact service performance. Then there is anomaly detection. Service mesh telemetry employs anomaly detection algorithms to identify abnormal patterns and deviation in service metrics. By detecting anomalies in real time, teams can proactively address performance degradation, prevent service outages, and ensure consistent user experience. Then there is SLO monitoring. Telemetry data is used to monitor service level objectives or SLOs defined for each microservice, such as availability, latency, and error rates. By continuously measuring and analyzing service performance against SLOs, teams can assess the health of their services and take proactive measures to meet performance targets. Then there is visualization and dashboards. Telemetry platforms provide visualization tools and customizable dashboards to display metrics, logs, traces, and alerts in user-friendly interface. These visualizations enable teams to gain actionable insights into service performance, track key metrics over time, and make data-driven decisions to optimize system behavior. Now, just to quickly recap, in this particular topic, we talked about service mesh telemetry, and then we talked about various components like metrics, logs, and traces. And then we talked about the uses of service mesh telemetry, and these uses included collection of metrics, traffic monitoring, distributed tracing, error detection and debugging, and then we also talked about other uses like performance profiling, anomaly detection, SLO monitoring, and visualization and dashboards. In this particular topic, we're going to talk about the process for collecting logs. So there are certain steps that you need to follow. So these steps would include choosing a logging library or framework. Then you have to instrument your application, then configure the logging library or the framework, then send log to cloud logging, and finally handle errors and retries. So let's take each step one by one and talk about it. So let's start with choosing a logging library or framework. Now, Google provides client libraries for various programming languages, which could include your Python, Java, and Go, that help you simplify the interaction with the cloud logging API. Now, these libraries handle authentication, request formatting, and error handling. Then you have popular logging frameworks like Log4j, which is a Java-based framework, Winston, which is Node.js, and StructLog, which is a Python-based framework that often have plugins or extensions that can integrate with cloud logging. Now, if you have specific requirements or constraints, you can directly interact with Cloud Logging API using HTTP or gRPC requests. However, this approach requires more manual effort. The next step is instrument your application. You need to add logging statements to your application code to capture relevant events and data. You also need to include important context information like timestamps, severity levels, and relevant identifiers. And then you need to structure your log messages using a consistent format like JSON for easier parsing and analysis. Then the third step is configure the logging library and framework. You need to set up authentication credentials to authorize your application to access the Cloud Logging API. You can use service account keys or other supported authentication mechanism. Then you also need to specify the Google Cloud project ID where you want to store your logs, and then you need to configure the log destination. For example, it could be a specific log name or resource type within the cloud logging. The next step is send logs to cloud logging. You need to use the logging library or framework to send log entries to Cloud Logging API. And depending on your chosen approach, which may involve calling specific functions or methods provided by the library or framework, or constructing and sending HTTP or gRPC requests directly to the API endpoint. Then the final step is handle errors and retries. You need to implement error handling mechanisms to gracefully manage situations where sending logs fails. So there could be network issues, API rate limits, or there could be any error which may occur. So you need to implement error handling mechanisms to gracefully handle these errors. And you should consider using retry strategies to ensure that important log entries are not lost due to temporary errors. Let's look at the example of using the cloud logging library. Now, to be able to use the cloud logging library, you need to ensure that logging library is installed in your environment. And you also need to set up proper authentication using a service account that is needed to access the cloud logging API. So these are going to be just two prerequisites that you need to configure in your environment. Let's look at the code on the screen. Let's start with import google.cloud.logging. Now, this line imports the google.cloud.logging module, which provides the necessary tools to interact with Google Cloud's logging service from your Python application. The second line talks about client equal to google.cloud.logging.client. Now, this particular line creates a client object. This client is your main interface to the Cloud Logging API, and it handles authentication, project identification, and manages connection to the service. Now, how does this particular line work? Now, the constructor google.cloud.logging.client attempts to automatically detect your Google Cloud project ID from your environment. So, for example, if you're running Google Cloud VM or have set the Google application credentials environment variable, so it will detect from there. Now, if it cannot auto detect, you will need to provide the project ID explicitly. So, you would have to mention something like client is equal to google.cloud.logging.client, and in brackets, you would have to mention project is equal to your project ID. Now, authentication here is typically handled automatically if you have set up the Google application credentials environment variable to point your service account key file. Then there is logger is equal to client.logger, and in brackets you have the log name. Now the third line talks about logger is equal to client.logger, and in brackets, in quotes, you have the logger object name, where in this case, it is my-log. Now this gets a reference to a logger object named my-log. In cloud logging, logs are organized into logs, which were previously called sinks. Each log represents a specific source or type of log entry. Now, the client.logger method either retrieves an existing log with the name my-log or creates a new one if it doesn't exist. The logger object is then used to write log entries to this particular log, which is my-log. Then there is the fourth line, which talks about logger.log_text, and then there is a text message, which is informational message. Now, this is where the actual log entry is created and sent to cloud logging. The log underscore text method takes the log message as a string, and behind the scenes, it builds a structured log entry, including timestamp and severity level, etc., and then sends it to the cloud logging API. The log entry is then stored in the my-log you specified earlier. Now, just to quickly recap in this particular topic, we talked about the process for collecting logs, and we also looked at an example of using cloud logging library. In this topic, we are going to talk about the strategies for troubleshooting compute resource issues. Now, when problems occur in your GCP compute resources, something like virtual machines, instances, or even containers, you can use systematic approach to identify and resolve the problems promptly. So there are going to be some effective troubleshooting strategies that we will look at in the upcoming slides. And before we proceed ahead, let's just quickly look at what these strategies are. So this is checking resource quotas and limits, examining logs and metrics, utilizing diagnostic tools, verifying network connectivity, inspecting the health of instances and virtual machines or VMs, and then considering external factors. So let's go ahead and talk about each one of them in detail. So let's first talk about checking resource quotas and limits. You need to review your project's quotas in the GCP console to ensure you haven't exceeded the limits for resources like CPUs, memory, or GPUs. GPU is basically graphical processing unit, something like CPU, but this works basically with the graphics acceleration within your system. Now, if you are running into quota restrictions, you can request a quota increase, and depending on your request, you might get an approval for quota increase. And then you also need to verify that your instances or virtual machines are not hitting their individual resource limits. You might need to resize your instance or create additional ones to distribute the workload. When you talk about resizing your instance, you might actually need to upgrade to a bigger instance, or you might want to, in fact, add more instances to distribute the workload. Let's now talk about examining logs and metrics. So you need to scrutinize the logs from your instances, virtual machines, or container clusters. You need to look for error messages, warnings, or unusual patterns that might indicate resource issues. You also need to analyze metrics related to CPU and memory utilization, disk input output or disk IO, network traffic, and other relevant parameters. You need to look for spikes, anomalies, or consistently high resource usage that could point to bottlenecks or misconfigurations. So basically, in nutshell, what you need to do is you need to look at specific metrics and see if there are any kind of spikes or high utilization of that particular resource. Then let's talk about utilizing diagnostic tools. So there are various diagnostic tools. There is Cloud Debugger, Cloud Profiler, and Cloud Trace. So when your application code is causing resource issues, you can use Cloud Debugger to inspect the running code in production and identify problematic areas. Then you can also use Cloud Profiler. You can profile your application's CPU and memory usage to pinpoint performance bottlenecks and optimize resource utilization. Then there is Cloud Trace, which was previously known as Stack Driver Trace. Now, this can trace requests across your distributed systems to identify latency issues and understand how different components interact. Let's now talk about verifying network connectivity. So there would be different components in your network. So there are going to be firewall rules. There is going to be network configuration. There might be load balancing. So depending on the network configuration, you might want to check out all three of them or any of these. So when you talk about firewall rules, you need to ensure that these rules allow the necessary traffic to and from your compute resources. If there is any incorrect firewall setting or rule, it can prevent access or communication between components. So that is the first thing that you might want to check if there is no communication happening between different compute resources. Then there is network configuration. You might want to double check your virtual private cloud or VPC configuration, and this would include checking on your subnets, routes, or network tags, and this needs to be done to ensure that there is proper connectivity. Then there is load balancing. Now, if in case you are using load balancer, you would need to verify that they are configured correctly and distributing traffic evenly across instances. There could be some configuration problem where one instance still might be getting overloaded with the requests and the other instance is virtually sitting idle. So you might want to check the configuration of your load balancer to ensure that there is even distribution of traffic across instances. Let's now talk about inspecting the health of instances and virtual machines. So there would be status checks and then there is serial console that we are going to look at. So when you talk about checking the status of your instance or virtual machines in the GCP console, you would need to look for errors, warnings, or unhealthy statuses. Now, if there are any errors, warnings, or unhealthy statuses, then you need to promptly take an action and fix those issues. Then there is serial console. You need to access the serial console of your instance to view boot logs and low-level system information. This can help diagnose issues that occur during startups or before operating system fully loads. Now, this might be a scenario where your operating system of a virtual machine fails to load. In that case, you may want to use the serial console to see where the problem is occurring. Let's now talk about considering external factors. So there are traffic spikes. So these are the sudden increases in traffic that can overwhelm your resources. You can analyze traffic patterns to identify and prepare for periods of peak use. Then there are dependencies. If your compute resources rely on external services, which could be your databases or APIs, you need to verify that these services are healthy and responsive. In many cases, you would find that there is an API that is causing the trouble, or there is some performance issue with your database, or there is connectivity issue between the database and the dependency, or database and the application. So in that case, you may want to check these relevant services which are external to your application. Then there are maintenance events. You need to check if there are any ongoing maintenance events in the GCP region where your services are located. These events can sometimes impact performance or availability. Even though GCP or in fact any other cloud service provider, they will intimate you in advance, in fact many days in advance, or there would be maintenance occurring on this particular date from this time to that time. So you would need to be careful. Let's now talk about the troubleshooting tips. So you start with the obvious. Now, this is the basic fundamental concept in troubleshooting that you should always start with the obvious. You should check for the simple issues like typos in configuration files, incorrect resource names, or outdated software versions. Now, even a smallest typing error in a code can break down your entire application or that particular component that code is meant for. So you may want to start with the obvious and check for these kind of issues. Then you need to isolate the problem. You should try to isolate the problem by restarting the instances, disabling certain features, or temporarily removing load from that particular instance. This would help you isolate the problem in a way that, for example, if you shut down the instance, but the other instances are working fine, so that means the problem is with this particular instance. Now, you may want to go one step further and maybe check the network configuration or the CPU or the memory utilization. So then you would have to further isolate the problem one by one. Then you need to collaborate within your team. You need to engage your team and leverage their expertise to investigate and resolve the issue faster. Then there is document everything. You need to document your findings, troubleshooting steps, and resolution for future reference and improvement of your overall incident response process. Now, documenting your incidents is very critical because tomorrow you may not be around in the same company or the organization. Then if there is a new person who's going to be facing the same issue, that person can actually use the documentation to troubleshoot. Now, if there is no documentation, then that particular person is going to restart from scratch and may spend more time than you did, or may not be able to troubleshoot the issue at all. So, if the documentation is available, then it not only cuts down the time to research and hit and try in resolving the issue, but it also helps you resolve the issue much quicker. Let's now talk about an example of troubleshooting a slow virtual machine. So, first is you would check metrics. You would use cloud monitoring to see where the metrics are having problems. So, there might be a high CPU utilization on a virtual machine. Then you would analyze logs. You would look at logs to reveal a specific process is consuming excessive CPU capacity. Then you would inspect the code. In this case, you would use the cloud debugger or profiler to identify the code causing the issue. Then finally, you would resolve the issue, in which you would optimize the code or allocate more CPU resources to the virtual machine. Now, just to quickly recap, in this particular topic, we talked about the strategies for troubleshooting compute resource issues. We talked about strategies like checking resource quotas and limits, examining logs and metrics, utilizing diagnostic tools, verifying network connectivity, inspecting the health of instances and virtual machines, and considering external factors. And then we talked about troubleshooting tips. Something like start with the obvious, isolate the problem, collaborate with your team, and document everything. And then we also talked about an example of troubleshooting a slow virtual machine. In this topic, we are going to talk about creation and analysis of custom metrics from logs. Now, when you talk about logs, they are a treasure of information from your application's behavior. But going through them manually to extract meaningful insights can be a daunting task, and it's a manual task. So you might spend hours in trying to find one piece of meaningful information from these logs. Now, by creating custom metrics from logs, you can transform this raw data into actionable information, therefore, enabling you to monitor, analyze, and improve systems more effectively. And how do you do this? So there are series of steps that you would need to follow. So let's start with the first one, which is define your objective. This is the first step to clearly define what you want to measure. What specific events or patterns within your logs are indicative of important aspect of your application's performance, health, or user behavior? Are you interested in tracking error rates, request latencies, resource utilization, or something else? Now, by pinpointing your goals, you can create metrics that truly matter. The next step is choosing a log source. You need to identify the log source that contains the information you want to extract. This could be logs from your application, web server, database, or any other system that generates the relevant logs. You need to ensure that the log entries are structured in a consistent format, preferably JSON, to simplify parsing and analysis. Then you need to create a log based metrics. Now, depending on your chosen logging and monitoring platform, you have different options to create log based metrics. In cloud logging in GCP, you can use the log based metrics feature to define filters that match specific log entries and extract relevant data points. For example, you could create a metric that counts the number of error log entries containing a specific error code. The next step is aggregate and transform. Once you have extracted data points from your logs, you can aggregate and transform them into meaningful metrics. This might involve calculating averages, percentile, or other statistical measures. You can also apply mathematical operations such as dividing one metric by another to drive ratio or rate. Then the next step is visualize and analyze. The real power of custom metrics comes from visualizing and analyzing them over time. You can use monitoring dashboards to create graphs, charts, and other visualizations that showcase the trends and patterns in your metrics. This helps you identify correlations, spot anomalies, and gain deeper insights into your application behavior. Then there is setting alerts and triggers.
Based on your analysis, you can set up alerts and triggers to notify you when specific metrics exceed or fall below predefined thresholds. This enables you to react proactively to potential issues and take corrective actions before they impact your users or your business. Let's now talk about the examples of custom metrics from logs. So there is error by rate type. You can count the occurrences of specific error codes in your application logs to track the frequency of different types of errors. Then there is request latency by endpoint. You can measure the response time of specific API endpoints to identify performance bottlenecks. Then there is resource utilization by component. You can also track the CPU, memory, or disk usage for different components of your application to detect resource constraints. Then another example is user behavior metrics. You can extract user actions from logs such as login attempts, page views, or purchase events to understand the user engagement and conversion rate. Let's now talk about the benefits of custom metrics from logs. So there are deeper insights. You can go beyond the basic metrics to gain a deeper understanding of your application's behavior and performance. Then there is proactive monitoring, in which you can detect issues early and prevent them from escalating into major problems. Then there is data-driven optimization. You can use metric data to identify areas for improvement and make informed decisions about resource allocation, code optimization, and architectural changes. Then there is enhanced observability. You can obtain a complete picture of your system's health and performance by combining custom metrics with other monitoring data. Just to quickly recap, in this topic, we talked about creating and analyzing the custom metrics from logs. We talked about various steps, which included defining your objective, choosing a log source, creating a log-based metrics, aggregating and transforming the log data, then visualizing and analyzing the log data, and finally setting up alerts and triggers. And after that, we talked about some of the examples of custom metrics from logs, and then we did talk about the benefits of custom metrics from logs, and these benefits included deeper insights, proactive monitoring, data-driven optimization, and enhanced observability. Now, in this topic, we are going to talk about addressing deploy time and runtime issues with applications. Issues can occur at deploy time and runtime, and they can significantly impact the availability and performance of applications. To tackle these issues effectively, it is crucial to adopt a very systematic and proactive strategy. Now, in the upcoming slides, we'll learn how to handle these issues in a more systematic manner. So let's first talk about addressing deployment issues. So there are various methods that you can use. So there is comprehensive logging and monitoring. You need to ensure your deployment process generates detailed logs, capturing each step, including environment setup, configuration changes, and artifact installation. This aids in pinpointing the exact stage where an error occurred. You also need to use monitoring tools to track the progress and health of your deployment in real time. You need to set up alerts to be notified immediately if the deployment either deviates from the expected outcome or exceeds the threshold for the time. Then there is error handling and rollback mechanisms. You can implement error handling mechanism in your deployment scripts or automation tools. This ensures that if an error occurs during deployment, the process can gracefully stop or revert to a previous state, therefore preventing partial or incomplete deployment. You also need to define a clear rollback strategy that outlines the steps to revert your application to a stable state if the deployment fails. You need to first test this rollback process, and then you need to test it regularly to ensure that it is reliable and it will work when needed. Then there is automated testing. So it could be pre-deployment testing, it could be post-deployment testing. Now, when you talk about the pre-deployment testing, you need to integrate the automated tests into your CI/CD pipeline to validate the application's functionality, performance, and security before deployment.
This helps catch potential issues early and reduce the risk of deployment failures. Then there is post deployment testing, something like smoke or regression tests that can help you verify that application is functioning correctly in the target environment. Then there is environment parity. You should maintain consistency between your development, testing, and production environments. You should use tools like Docker or Kubernetes to containerize your applications and ensure consistent dependencies and configurations across environments. This reduces the risk of environment specific issues arising during deployment. Let's now move to the next slide and look at some more methods to address deployment issues. In the previous slide, we talked about several methods for addressing deployment issues, and we will just continue doing the same on this particular slide. Now, the next method is continuous integration and continuous deployment, which is CI/CD. You need to implement the CI/CD pipelines to automate the deployment process and ensure consistency and reliability across environments. You should use tools like Jenkins, GitLab CI/CD, or Google Cloud Build to automate build, test, and deployment workflows. You should also perform thorough testing, including unit, integration, and end-to-end tests of your CI/CD pipeline to detect issues early in the deployment process. And in fact, this would save you a lot of time in troubleshooting at the end because you have fixed the issues as your pipeline is in progress. Then there is infrastructure as code. You need to define infrastructure resources using code. So you can use Terraform or Google Cloud Deployment Manager to ensure consistency and repeatability in deployments. You can use version control systems like Git to manage and track changes to infrastructure configurations, therefore enabling rollback to previous versions in case of issues. Then there is containerization and orchestration. You can containerize applications using Docker or similar containerization tools to encapsulate dependencies and ensure portability across different environments. You can orchestrate containers using Kubernetes or other container orchestration platforms to manage deployment, scaling, and lifecycle of application components. So we just spoke about different methods of addressing deployment issues, and now we are going to talk about different methods for addressing runtime issues. So there are different methods that you can use. You can use monitoring and observability. You can do root cause analysis. You can also talk about scalability and load testing, and then you can also do incident response and management. So let's start with monitoring and observability. You need to continuously monitor your application's performance, health, and logs in production. You can use various tools. You can use tools like application performance monitoring or APM, infrastructure monitoring, and log aggregation to gain visibility into your application's behavior. You can set up alerts based on predefined thresholds or anomaly detection to be notified about potential runtime issues. The alerts allow you to proactively address problems before they impact users significantly. You can use applications with logging, metrics, and tracing to gain visibility into their behavior and performance at runtime. You can utilize monitoring tools such as Prometheus, Stack Driver Monitoring, or Datadog to collect and analyze application metrics such as response time, error rates, and resource utilization. You can also implement distributed tracing using tools like OpenTelemetry or Jagger to trace requests across microservices and identify performance bottlenecks. Let's now talk about root cause analysis or RCA. You need to ensure that your application is able to log detailed information about errors, exceptions, and performance metrics. This helps understand the root cause of runtime problems. You can also utilize distributed tracing to follow requests across services and identify bottlenecks or latency issues. Then you can employ debugging tools and techniques to analyze application behavior in real time and identify the source of errors. Then there is scalability and load testing. You can implement autoscaling to dynamically adjust resources based on demand. This helps you remove manual effort in scaling your resources. So this would be done automatically when you have auto scaling enabled. And this also ensures that your application can handle traffic spikes and prevent performance degradation due to overload. You should also regularly perform load tests to simulate real world traffic patterns and identify potential performance issues before they occur in production. Then there is incident response and management. You need to develop comprehensive incident playbooks that outline the steps to be taken in different scenarios. So, for example, one of the scenario could be your application crash, or it could be performance degradation or security breaches. Now, if you have these steps outlined, you would be able to troubleshoot them very quickly. Then there is on-call rotation, which helps you ensure that someone is always available to respond to incidents promptly. Then there are communication channels that help you notify stakeholders and team members about incidents and their resolution. You need to foster a culture of continuous improvement by regularly reviewing and refining deployment processes and application architecture. You need to encourage collaboration between development, operations, and quality assurance teams to share insights, learning, and best practices for addressing deploy time and runtime issues. Let's now talk about the best practices. So, there is version control. You need to maintain proper version control of your application code, configuration files, and deployment scripts. This would allow you to easily roll back to previous versions if necessary. Then there is documentation. You would need to keep thorough documentation of your deployment process, environment configurations, and troubleshooting steps. This helps onboard new team members and streamline incident response. Then there is collaboration. You must foster collaboration between development and operations teams to identify and resolve issues efficiently. Then there is continuous improvement. You must regularly review your deployment and monitoring processes to identify areas for improvement and implement changes to prevent future problems. Now, just to quickly recap in this particular topic, we talked about two key things. We talked about the addressing issues in deployment. We also talked about addressing issues in runtime. And then we talked about the general best practices, which included version control, documentation, collaboration, and continuous improvement. Demonstrate setting up and customizing a monitoring dashboard in GCP. In this topic, what we are going to do is we will learn how to set up a custom dashboard to visualize key metrics. And this will ensure that the health and the performance of our applications and infrastructure is optimal. Now, the way to set it up is you need to go to monitoring. So you can simply search for cloud monitoring in the search bar and visit this particular page. Once you come here, you need to select dashboards in the left pane. Now, once we are here, we need to do certain things. And before we proceed ahead, we're going to just list down a few things that we are going to do. So we are going to create a new monitoring dashboard. We are going to add a widget to display essential metrics. Now, without the widget, the dashboard is going to stay blank. So this is going to be one of the key steps. And then we can customize the dashboard layout and appearance if we like. And we can also configure alerts to trigger notifications for anomalies. And here in this particular demo, what we are going to do is we're going to walk you through a particular alerting policy that is already created, and then we will observe that alerting policy and how it features. Now, let's go ahead and talk about the prerequisites. There needs to be two key prerequisites that you need to meet. One, you need to have an active GCP project with resources. So, for example, you can have compute engine instances, cloud functions, etc. And then you need to also have the basic familiarity with GCP console. So this what we are looking at is the GCP console. Now, once we are into this monitoring page, what we need to do is go to dashboards, and then from here we can click on create dashboard. Before we do that, I'm going to just walk you through an existing dashboard that I have created, which is SKS001. I'm going to click on this, and what we see is different set of widgets with different information. So One is the logs. Second one is the policy, alerting policy that I was talking about. And then there is monthly bytes streamed into log buckets, and then global bytes streamed into log buckets. That is the sum. Now, both of these log buckets widgets are basically summing up and displaying the total value. Now, let's go back and create a new dashboard. So I'm going to click on this create dashboard. And once this page is loaded, notice that this is blank. Now, this is going to be an important step. You need to know what you want to monitor, and therefore, accordingly, you would need to add a particular widget, and then you need to set the appropriate metrics. So I'm going to click on this add widget. Now, once I come here, there is this add widget page that is displayed. So I'm going to click on metrics. I can add this metric, I can add logs, or I can add observability analytics. And then for detection, I can add alerting policy, SLOs, incidents, errors. And similarly for visualization, I can add different types of graphs, heat map, stacked bar, top list, gauge, scorecard, etc. So there are different things I can add for visualization. Now, what I'm going to do is I'm going to add an alerting policy here. So I'm going to click on alerting policy. And from here, I'm going to click on this drop down, which is alert policy. And I'm going to select SKS 001 underscore policy. Once I do this, this particular policy is now added. I'm going to go ahead and click on apply. Now, what has happened is this widget is now added. Now I'm going to add another widget and add logs. And I'm going to just keep the severity level default. And once the log values are added, I'm going to just go ahead and click on apply. Let's add another widget. And this time we are going to add a metric. So I'm going to click on add widget and I'm going to click on metric. Now, from the metric drop down, I need to select a metric. And once I click on this, I can go to VM instance. And from here, I can go to network and I can click on TCP connection. Once I select this, I need to click apply. All right, so this widget is also added. I'm going to click on apply here. Now I have got 3 widgets. So this is how you create a dashboard and set up widgets. And the next thing we had to do was customize this. Now I can just move these around. I can customize them the way I want. Maybe I want to see logs later, but then I want to add the TCP connection widget on the top. So I can move this around. So this all can be done. And then I can auto save. I can select this, and then there are other filters that I can add. Now, this is about the dashboard. Now, let's go back to the alerting policy, which was SKS 001 underscore policy. So I'm going to click on alerting. Once I come here, there are already this policy is running. So there is one alert policy and there are 4 incidents firing. So now if I click on this view all, there is SKS 001 underscore policy. I can click on this. Now the status is basically disabled as of now. So I need to click on disabled. Now the policy is enabled. I can edit this policy, copy it, delete it, or I can download the JSON file. Now, what this is doing is this is monitoring the state of the TCP connection for our VM instance, which is running in the background. Now, let's go ahead and create one policy. So I'm going to click on create policy on the policies page in the right pane. And once I do this, I need to select a metric. Again, I click on this. I go to VM instances. Again, let's just pick the easy one, which is network and TCP connection. And I click apply. Now, once this is done, I need to set the rolling window and rolling window function. So we will leave this data as is, and then we're going to click on next. Then there is a threshold, metric absence, and forecast. So we'll just leave threshold. And above threshold and threshold value, let's say if I just add 5 and then I click next. And then notification channel, configured my email address as the notification channel. So I'm going to just go ahead and click on my name and click OK. And notification subject line, alert above threshold. So I'm going to just type this and notify on incident closure. Now, once the incident is closed, you will get another email notifying you that the incident is closed, and incident auto close duration. So that could be 30 minutes or whatever time. You can just select, let's say 30 minutes, and then severity level is critical. Name of the policy, SKS002. That is the name I'm going to give, and I'm going to click on next. All right, so this is now enabled. So this policy is now enabled and it's going to function. So I'm going to click on create policy. Now alert policy SKS002 is saved. So this policy is now functioning, and notice that it's already started to capture data. Now, as and when there are alerts, anything above 5, it's going to start sending you notifications, and those notifications will come to your email address. Some of the notifications might go to spam folder or junk folder, so you might want to keep a tap on that and keep checking the junk or the spam folder. Otherwise, you will get them in your inbox. Well, just to recap, in this particular demo, what we talked about is creating a dashboard, adding a widget to a dashboard, customizing the dashboard a little bit where we shuffled around the widgets, and then finally we talked about an existing alerting policy, and then we also created a alert policy. In this topic, we are going to use VPC flow logs for network troubleshooting. Now, VPC flow logs is an invaluable tool for diagnosing network problems within your GCP environment. It can capture information about the traffic flowing through your VPC network, and therefore it provides crucial insights into connectivity, security, and performance issues. And we are going to talk about a structured approach to leverage VPC flow logs for troubleshooting network issues. So we are going to talk about various steps. So the first one is gather initial information. You need to clearly define the problem you are facing. Is it a connectivity issue between two instances? Is traffic being dropped unexpectedly? Are there unusually high latency spikes? Or the more specific you can be, the easier it will be to narrow down the problem. You also need to identify specific resources involved, such as virtual machines, load balancer, network interfaces, or subnets. This will help you focus your investigation and troubleshooting in the relevant areas. You need to determine when the issue started, whether it is persistent or happening on and off, which means it can happen once or then it doesn't happen for some time and then it repeats itself. So you need to be sure of that. This information will be crucial in correlating events and identifying potential causes. The next step is enable VPC flow logs if already not enabled. You need to choose where you want to store your flow logs, whether it is cloud storage, BigQuery, or PubSub. BigQuery is often preferred for easier querying and analysis. You also need to configure the sampling rate. VPC flow logs typically sample a subset of traffic. You need to select an appropriate sampling rate based on volume of traffic and your analysis requirements. Then you need to choose the meta fields. You need to determine which meta fields you want to include in your flow log. So it could be something like source and destination IP addresses, ports, protocols, or bytes transferred. Then you need to analyze VPC flow logs. If you are using BigQuery, you can use SQL-like queries to filter and aggregate flow log data. For example, you could query all traffic destined for a specific IP address or a port. Then you need to look for patterns in the flow log data that might indicate the source of the problem. This could include something like drop packets, high latency, or unusual traffic. Then you need to correlate the flow log data with logs from other sources like cloud logging or application logs. This can help you pinpoint the exact location and cause of the issue. The next is narrow down the problems. You need to start isolating components. Try to isolate the problem by temporarily disabling or modifying specific components such as firewall rules, load balancers, so you can do hit and try and observe the impact of the traffic flow. Then you can use tools like ping, traceroute, or iperf to test connectivity between resources and identify any network path issues. Now, based on this analysis of flow logs and troubleshooting efforts, you need to implement remediation actions to resolve network issues. This may include adjusting firewall rules, updating routing configurations, optimizing network performance, or addressing security vulnerabilities. The next is resolving the issue. If flow logs indicate blocked traffic, you need to adjust firewall rules to allow the necessary communication. You might have to modify routing tables, network tags, or load balancer configurations if needed. Now, if the issue is related to resource exhaustion, you may need to scale up your instance or add more capacity to your network. Then, if it is a problem with application code, you need to fix that particular bug or the issue with the application code. Now, you also need to continuously monitor network traffic and performance metrics after implementing remediation actions to ensure that the issue has been successfully resolved. You can use VPC flow logs and other monitoring tools to track changes in network behavior and verify that the desired outcomes have been achieved. Let's now talk about the key considerations for using VPC flow logs. So there is log retention. You must set up an appropriate retention period for your flow logs to ensure you have enough historical data for analysis. Because short-term data will not help you in identifying and troubleshooting issues. So therefore, you need to have your appropriate retention period configured for these logs. And you may need to look at your organization's data retention policy, and accordingly you may want to configure the log retention. Then there is alerting. You would need to set up alerts based on flow log data to proactively detect anomalies or security threats. Then there is automation. You may consider automating parts of your troubleshooting process. So for example, you may want to automate log analysis or triggering alerts. Now this would help you speed up issue resolution. Just to quickly recap, in this particular topic, we talked about using VPC flow logs for network troubleshooting. So we talked about various steps that we would need to perform. So there is gather initial information, there is VPC flow logs to be enabled if they are already not enabled, then analyzing the VPC flow logs, narrowing down the problem, and finally resolving the issue. Then we also talked about the key considerations for using VPC flow logs. We talked about log retention, alerting, and automation. Now, in this topic, we are going to talk about configuring alerting policies based on SLOs and SLIs. Now, SLO stands for service level objectives, and SLI is service level indicators. So, we are going to talk about these. Now, you can configure your alerting policies based on your SLOs or SLIs. Now, this will empower your team to respond swiftly to potential issues, minimize downtime, and deliver a more reliable and satisfying experience to your users. Now, when you talk about SLOs and SLIs, we did talk about them in another course. And now, just to recap that, what they are, when you talk about SLOs, they are specific quantifiable targets that define the level of service quality expected by users over a certain period. For example, an SLO could specify that a system should have at least 99.9% availability in a given month. Now, when you talk about SLI, they are measurable metrics that are used to assess the performance and reliability of a service. Now, these metrics are typically derived from user interactions or system behavior and are used to track the achievement of SLOs. So, for example, SLI can include latency, error rate,
availability, throughput, or even the response time. Let's now talk about defining SLIs for alerting. You need to identify the critical SLIs that directly impact the user experience and align with SLOs defined for the service. You need to determine that thresholds values or targets for each SLI that indicate acceptable performance levels. Now, these thresholds should be based on the desired SLOs and expectations of users. Then comes setting up alerting policies. You need to navigate to the monitoring sections and navigate to the alerting page. And there you can create the policy by clicking on create policy button. This will help you create a new alerting policy. You can define different conditions for triggering alerts based on selected SLIs. Now, this could typically involve getting threshold values or conditions that, when breached, can indicate a degradation in service quality. You can also specify the notification channels where the alert should be sent. Now, these notification channels could include email, SMS, pager duty, Slack, or in fact, you can use any third party integration if you need to. You can configure additional settings such as alert frequency, duration, and suppression to prevent alert fatigues and ensure timely notification of relevant events. Then comes configuring alerting based on SLOs. You need to map the alerting policies to the corresponding SLOs to ensure that alerts are aligned with the service's overall reliability and performance objectives. You can define the error budget or acceptable error rate for each SLO. The error budget represents the amount of time or resources that can be consumed without violating the SLOs. Alerting policies can be configured to trigger alerts when the error budget is being exhausted or exceeded. Then comes the testing and iterating. Now, before implementing these policies, you need to test the alerting policies, and you want to do this to ensure that they are correctly configured and trigger alert when expected. You need to monitor the effectiveness of the alerting policies over time and iterate as and when needed to fine tune thresholds. And you would also need to iterate over the notification settings and other parameters if required. Then you need to gather feedback from stakeholders, including users and operation teams, to validate the relevance and usefulness of the alerts and make adjustments accordingly. Then there is integrating with incident response processes. You need to integrate the alerting policies with incident response processes to ensure timely resolution of issues that impact service reliability and performance. You also need to define the escalation procedures, on call rotations, and incident severity levels to prioritize and respond to alerts effectively. You also need to document response procedures and conduct regular drills to ensure that teams are prepared to handle alerts and incidents efficiently. Let's now talk about the benefits of SLI based alerting. By proactively configuring alerting policies based on your SLOs and SLIs, you can empower your team to respond swiftly to potential issues, minimize downtime, and deliver a more reliable and satisfying experience for your users. Because this is going to be a very guided approach. You are not just defining any policies, but you're making your policies based on SLOs and SLIs. Therefore, it will have very concrete results. So let's talk about the benefits. So there is proactive incident detection. You can identify issues early before they significantly impact your users or services within the GCP environment. Then there is data driven decision making. You can use SLO data to prioritize engineering efforts and allocate resources effectively. Then there is improved communication, which will help you clearly communicate reliability expectations to stakeholders and team members. Then there is enhanced reliability, which helps you drive continuous improvement of service reliability by focusing on meeting SLO targets. Just to quickly recap, in this particular topic, we talked about configuring alerting policies based on SLOs and SLIs. We talked about various parts to it. So we talked about understanding the SLO and SLIs. defining SLIs for alerting, setting up alerting policies, configuring alerting based on SLOs, testing and iterating, and then integrating with the incident response processes. And then we also talked about the benefits of SLO, SLI based alerting. So, benefit included proactive incident detection, data driven decision making, improved communication, and enhanced reliability.
Now, in this particular topic, what we are going to do is we are going to see a demonstration of how Cloud Trace does the performance monitoring of an application. And we'll also see what happens if the application is unreachable, then what will happen to Cloud Trace and whether it will still be able to throw an error or something like that. So we'll see that. Now, there are a lot of things that needs to be done before we get to monitor the application performance. So there are two APIs that need to be configured or enabled. So one is the Kubernetes Engine API that would be running the containers with your application. And second is the Cloud Trace API. Now, both of these need to be enabled in the Google Cloud Platform. Now, once you have enabled them, then you would need to create the cluster. And you can create the cluster first, or you can clone a repository and then navigate into it to deploy a sample application. Now that has already been done because these were time consuming tasks. So that has already been done for you. So you can simply use the git clone and the repository name, and then you can also run another command which is cd and then navigate into the local repository, and you can also run the setup.sh file at the same time, or you can run it separately. It's up to you. Now, in this command, we have done it in a single command. And then next one is create cluster, which is the container cluster. And then you would need to configure the kubectl to automatically refresh its credentials to use the same identity as the Google Cloud CLI. What this means is whatever credentials you are using with the Google Cloud CLI, it's going to automatically start using those. And now the commands are listed here. So first one is basically G Cloud container clusters create SKS cluster, which is the cluster name, and then it defines the zone name. And the second one is G Cloud container clusters get credentials, SKS cluster, and then the zone name. Now, these two tasks have already been done for you. And now, going ahead in this task, what needs to be done is there are series of things that we would need to do. So we would need to get the cluster nodes. We would need to create a trace, get the IP address. If we don't have the IP address for the cluster, then we would use curl or web browser to make several requests to this IP address. And then finally, we'll go ahead and clean up the resource. If we need to keep the cluster, then we won't. But in this demo, we are not cleaning up the cluster, but this is the command that you can use. This is the first command, which is kubectl get node. So I'm going to just copy that, head over to the Cloud Shell and paste this command over there. And this is going to give us the nodes from the container cluster. I need to authorize. Once I do that, this pop-up is going to happen. And because I'm already logged into my Google Cloud, it's going to just take those. And there you go. The clusters container pods are already listed. Next is we need to create a trace. So I'm going to just go ahead and copy this command and then head over to Cloud Shell once again, paste the command and press enter. Now this is going to create the trace, and obviously there is no result here. Then again, I'm going to go back to the notepad, get the IP address of the cluster if I need to. And since this is an optional step, I don't have to do it if I know the IP address. But just for the demonstration purpose, I'm going to just go ahead and copy this command and run it here. And I would get the IP address. So I'm going to press enter. There you go. So 35.239.99.102. In your case, when you set it up, it might be a different IP address. Next thing I'm going to do is I'm going to copy this curl command with the IP address, and I'm going to head over to the Cloud Shell and I'm going to paste this command, press enter. So I'm going to just click on this command and notice that it has opened a website and it is attempting to load the website. But there are going to be latency issues, and that's why it's not going to load the command. But using the same command which I executed earlier, there are several traces that have been mentioned here on the Cloud Trace window. And this is what we are going to see. Whichever is selected will have the Gantt chart displayed at the bottom. And again, it has not been able to load. That is primarily due to, if you notice that this particular Cloud Shell at the bottom of the right column, this shows the latency is more than 1100 millisecond, which is quite high. And that is probably one of the reasons why it is not able to get to the website. Well, in this particular topic, just to recap, we talked about CloudTrace. We saw the commands for setting up a cluster. We saw the command for cloning a Git repository and also ran the command for setting up the trace for application monitoring. In this topic, we are going to compare Google's managed service for Prometheus versus other monitoring solutions. And we are going to do this in a tabular format, and there are various features on which we are going to measure them. So, these are some of the features that we are going to be talking about. So, it is hosting. It will basically tell you how each service is hosted. Then there is integration with GCP, which will reflect the ease or complexity of integration with GCP. Then there is query language, which specifies the query languages used, which is important for users familiar with PromQL or proprietary languages. Then we are going to talk about the scalability feature and see how scalable a particular solution is. And then we are going to talk about the cost, which is the total cost of that particular solution, and the multi-cloud support. So let's get started with hosting. So when you talk about Prometheus or Google Cloud's managed service for Prometheus, and it is acronymed as GMP. Now it is a fully managed by Google Cloud, therefore relieving users from operational overhead. Then there is Prometheus, which is self-hosted, that requires users to set up and manage their own Prometheus instances, including handling upgrades and scaling. Then there is Datadog, which is a software as a service solution. And here, Datadog hosts and manages the infrastructure. Then there is New Relic, which is another software as a service solution with all management and scaling handled by New Relic. Then there is Grafana, which has the Prometheus data source. It can be self hosted or used as a managed service in Grafana Cloud. Users can integrate it with self hosted or managed Prometheus instance. The next feature is integration. Now, when you talk about Prometheus, it seamlessly integrates with other Google Cloud services. Prometheus, which is self hosted, can be integrated with GCP but requires manual configuration and setup. Then there is Datadog, which offers some integration with GCP, but not as deep or native as managed service for Prometheus. Then there is New Relic, which has limited integration with GCP services, not as comprehensive as managed service for Prometheus. Then there is Grafana with Prometheus data source that integrates with GCP. It requires manual setup, typically involving configuring data sources and dashboards. Then the next feature of comparison is query language. Now, GMP uses Prometheus query language or PromQL, which is standard for Prometheus users. Prometheus self-hosted also uses PromQL. Datadog uses its proprietary Datadog query language or DQL, which is tailored for its platform. New Relic uses New Relic query language or NRQL that is designed specifically for querying within New Relic. Grafana uses PromQL when connected to Prometheus data source, therefore providing a similar experience for Prometheus users. The next feature of comparison is scalability. GMP is highly scalable because it leverages the Google's Monarch time series database for backend support. Prometheus self-hosted, it requires manual intervention for scalability, such as setting up Prometheus Federation or using Thanos or Cortex for long-term storage and scalability. Datadog offers high availability out of the box and is designed to handle large-scale deployments without user intervention. New Relic also provides high scalability as managed service, which is capable of handling extensive data. Grafana scalability depends on underlying Prometheus setup, which could be self-hosted solution that may require manual scaling efforts. Then there is cost as the next feature. So GMP
The cost is generally higher, particularly for smaller workloads due to fully managed nature and enterprise level features. Prometheus self-hosted has lower cost as it involves only infrastructure and maintenance cost, therefore making it cost effective for smaller setups. Datadog can be expensive for large deployments due to its comprehensive feature sets and SaaS or software as a service pricing model. New Relic has the same cost model as Datadog, and it can be costly due to its extensive monitoring and analytics features. Grafana has lower cost if self-hosted, with costs primarily for infrastructure and maintenance. Managed services like Grafana Cloud can be more expensive. The next feature to talk about is multi-cloud support. GMP supports multi-cloud environments, therefore making it versatile for hybrid cloud setups. Prometheus self-hosted can be deployed in any cloud or on-premises to support multi-cloud configuration. Datadog offers robust multi-cloud support, therefore allowing monitoring across various cloud providers. New Relic provides comprehensive support for multi-cloud environments and integrates with multi-cloud platforms. Grafana with Prometheus data source supports multi-cloud through its ability to connect to various data sources across different environments. Let's move to the next slide to look at some more features. So there are more features that we are going to talk about. So we are going to talk about ease of use. How easy is it to use one of these tools? Then what kind of customization that is supported by these tools? What are the strengths and weaknesses? And what are going to be the idle use cases? So we are going to talk about these features and compare each of these tools. So let's first talk about ease of use. So GMP is pretty easy to use, especially for users familiar with Prometheus due to its managed nature and integration with GCP. Prometheus self-hosted requires expertise to set up, manage, and scale, therefore keeping a steeper learning curve. Datadog is user-friendly and has interface that is designed for ease of use even for non-experts. New Relic is also user-friendly with intuitive interfaces for monitoring and analytics. Grafana has steep learning curve for customization and setup, although it's powerful once it is configured. The next feature is customization. GMP offers limited customizations compared to self-hosted solutions, but still offers configurable options. Prometheus self-hosted provides high customization, therefore allowing users to tailor configurations, integrations, and scaling strategies to their needs. Datadog offers limited customization because it's a software as a service model. It mainly focuses on ease of use and out of box functionality. New Relic also, just like Datadog, offers limited functionality, and it has an emphasis on pre-built solutions and integrations. Grafana offers high customization capabilities for dashboards and visualizations, therefore providing extensive flexibility. Let's now talk about the strengths. So GMP is fully managed, native GCP integrated, and highly scalable service. Prometheus self-hosted is open source. It offers flexibility, extensive customization, and large community support. Datadog offers comprehensive monitoring, integrations with numerous services, and user-friendly interface. New Relic offers advanced application performance monitoring or APM, end-to-end visibility, and strong analytics features. Grafana offers powerful visualization capabilities. It is open source and it offers extensive dashboard customization. Let's now talk about the weaknesses. GMP, there is a higher cost because primarily it is GCP specific. There is a limited customization compared to self-hosted. Prometheus self-hosted, there is an operational overhead because you need to manage it. You need to have expertise to manage and scale effectively. Then there is Datadog, which can be costly. There is a complex pricing model, and there are limited customization compared to open source solutions. With New Relic, there is a high cost, limited customization, and it is primarily focused on predefined metrics and dashboards. Grafana, it offers limited functionality and used without other tools, and it relies heavily on Prometheus for data collection and storage. Let's now talk about the idle use cases.
When you talk about GMP, there is a large scale deployment in the GCP environment and it is idle for existing Prometheus users. Prometheus self hosted is idle for smaller setups and specifically where customizations are needed. Datadog can be used for full stack monitoring and diverse environments. New Relic is idle for application performance monitoring or APM, and you can use it where you want to do in depth APM or application performance monitoring. And it is comprehensive infrastructure view that is available with the New Relic. And when you talk about Grafana, you can use it when you need good amount of visualizations and custom dashboards. Just to recap, in this particular topic, we talked about Google's managed service for Prometheus and compared it with various other tools like Prometheus self-hosted, Datadog, New Relic, and Grafana. And we talked about different features on which we did the comparison. We talked about hosting, integration with GCP, query language, scalability, cost, multi-cloud support. And then we also talked about ease of use, customization, strengths, weaknesses, and idle use cases. In this topic, we are going to talk about preemptible VMs with committed use discounts. We have a table on this particular slide, and this table compares two types of virtual machines that are offered by cloud providers. Now, these are preemptible VMs and committed use discount or CUDs. Both these VMs can significantly reduce your GCP compute costs, but they do so in different ways, each with its own trade offs in terms of reliability and flexibility. Preemptible VMs are short lived, low cost virtual machines that can be interrupted by Google if resources are needed elsewhere. CUDs or committed use discount offers discounts in exchange of a commitment to use specific amount of compute resources, something like virtual CPUs or memory in a particular region for 1 year or 3 years. So let's talk about the features of each one of them. And then we are going to basically in this table, we are going to be comparing them on different features like cost saving, reliability, flexibility, upfront commitment, and suitable workloads. So let's start with cost saving. Preemptible VMs offer significant cost saving of up to 80% compared to standard virtual machines. This is because they utilize excess capacity in the cloud provider's infrastructure, which can be reclaimed if needed. While not as inexpensive as preemptible VMs, they still provide substantial cost reductions compared to standard on-demand pricing. These discounts are earned by committing to using a certain amount of resources over a period of usually 1 or 3 years. The next feature is reliability. Preemptible VMs have low reliability. They can be interrupted or terminated at any time by the cloud provider if resources are needed elsewhere. This makes them unsuitable for applications that require constant uptime. CUDs, on the other hand, offer high reliability, similar to standard virtual machines. Resources are guaranteed to be available for the duration of the commitment, therefore ensuring uninterrupted operation of critical applications. Then there is flexibility. Preemptible VMs provide high flexibility as they can be used for various workloads as long as they can tolerate interruptions. This makes them suitable for batch processing, data analysis, and other fault-tolerant tasks. On the other hand, CUDs are less flexible because they require a commitment to specific resources in a specific region for a fixed duration. This might limit the ability to scale resources up or down quickly based on demand. Then there is upfront commitment. Preemptible VMs have no upfront commitment. Users pay only for the time they actually use the resources. CUDs, on the other hand, require an upfront payment or monthly installments for the committed resources, even if they are not fully utilized. The next point is suitable workloads. Preemptible VMs are idle for batch processing, data analysis, fault-tolerant workloads, and tasks that can be interrupted without causing significant disruptions. On the other hand, CUDs
are better suited for web servers, databases, steady state workloads, and applications requiring high reliability and consistent performance. Let's now talk about choosing the right strategy. So, first one is the workload pattern analysis. You need to understand the resource requirement and uptime need for your applications. Then there is cost benefit analysis. You can calculate the potential cost savings of each option and weigh them against the risk of interruptions for preemptible VMs or the CUDs for which the commitment is required. Then there is hybrid approach. You must consider a combination of preemptible VMs for non-critical workloads and CUDs for those that require high availability. Then there is regular review. You must reevaluate your choices as your needs change. GCP offers tools like pricing calculator and recommender to help you make informed decisions. Now, by carefully considering these factors and choosing the right combination of preemptible VMs and CUDs, you can significantly optimize your GCP compute costs without sacrificing the reliability and performance of your critical applications. Now, just to quickly recap in this particular topic, we did compare preemptible VMs with committed use discounts or CUDs VMs. Now, we compared on features like cost saving, reliability, flexibility, upfront commitment, and suitable workloads. And then we talked about choosing the right strategy, which included workload pattern analysis, cost benefit analysis, hybrid approach, and regular review. In this topic, we are going to talk about logging and monitoring access controls. Now, securing your logging and monitoring infrastructure is crucial to protect sensitive data, ensure compliance, and maintain the integrity of your observability systems. Implementing logging and monitoring access controls is crucial for maintaining the security and integrity of the systems and the data within an organization. Now, these access controls are divided into different categories. So, there is authentication and authorization, data encryption, log integrity and immutability, audit logging, network security, and regular reviews and updates. So, let's go ahead and look at each one of them in the subsequent slides. So let's start with authentication and authorization. So there are different sets of controls. So there is strong authentication, there is role-based access control or RBAC, and then there is principle of least privilege. So let's start with strong authentication. You need to enforce strong authentication mechanisms for accessing, logging, and monitoring tools and APIs. You can use multi-factor authentication or MFA, single sign-on or SSO, or other robust methods to identify the identity of users and systems. Then there is role-based access control or RBAC. You need to implement RBAC to grant users and service accounts the minimum permissions necessary to perform their tasks. You must avoid overly broad permissions that could lead to unauthorized access or misuse of data. Then there is principle of least privilege. You must follow the principle of least privilege by granting access only to the specific logs or metrics that are relevant to a user's role. For example, a developer might only need access to logs related to their own applications, while a security analyst might need broader access. Let's now talk about data encryption. So there is encryption at rest. You need to ensure that log and metric data is encrypted at rest using strong encryption algorithms. This protects the data from unauthorized access even if storage systems are compromised. Then there is encryption in transit. You must use secure protocols like Transport Layer Security or TLS to encrypt data in transit between your applications, monitoring agents, and logging systems. This prevents eavesdropping and tampering with sensitive information. Then there is key management. You must implement secure key management practices to protect encryption keys and ensure that only authorized personnel can access them. Let's now talk about log integrity and immutability. So there is write once, read many, or warm storage. You can consider using warm storage solutions for storing logs to prevent tampering or deletion. This ensures that log data remains intact and can be used for auditing and forensic analysis. Then there is hashing and checksums. You should calculate cryptographic hashes or checksums for log files to verify their integrity and detect any unauthorized modifications. Then there is digital signatures. You should sign log files with digital signatures to provide an additional layer of integrity assurance and traceability. Let's now talk about audit logging. So there is activation of audit logs. You must activate audit logs for your logging and monitoring systems. This records who accessed what data, when, and from where. Then there is audit log monitoring. You must regularly review audit logs to detect any suspicious activity, unauthorized access attempts, or potential breaches. Then there is alerting. You must set up alerts to be notified about any critical events or anomalies in your audit logs. Then there are network security controls. So there are firewalls. You can use firewalls to restrict access to your logging and monitoring systems to authorized networks and IP addresses. Then there is network segmentation. You must segment your network to isolate logging and monitoring infrastructure from other parts of your environment. Then there is intrusion detection and prevention systems, or IDPS. You can deploy IDPS to detect and prevent unauthorized access attempts or suspicious activities. Let's now talk about regular reviews and updates. So there is review of access controls. You must periodically review and update access controls for your logging and monitoring systems to ensure they align with current security policies and user roles. Then there is patch management. You must keep your logging and monitoring software up to date with the latest security patches to mitigate known vulnerabilities. Then there is security testing. You must conduct regular security assessments and penetration testing to identify and address any potential weaknesses in your logging and monitoring infrastructure. Now, just to quickly recap, in this particular topic, we talked about logging and monitoring access controls. So, we talked about 6 different categories of controls. So, these were authentication and authorization, data encryption, log integrity and immutability, audit logging, network security, and regular reviews and updates.
In this topic, we are going to talk about Cloud Profiler for identifying performance bottlenecks. Now, Cloud Profiler is a powerful tool that can continuously gather CPU and memory usage data from your production applications. By analyzing this data, you can identify the specific code paths and functions consuming excessive resources. Therefore, it can help you optimize your application for improved performance and resource utilization. So let's talk about the implementation process, which has some 6 steps. So it starts with enabling Cloud Profiler API and installing the profiling agent, then configuring agent settings, and it's an optional step. Then deploy and run your applications, analyze profiling data in Cloud Profiler, and then identifying performance bottlenecks, and finally optimizing your code. So let's go ahead and talk about each step in detail. So let's start with enabling Cloud Profiler API and installing the profiling agent. In your GCP project, you must enable the Cloud Profiler API. This gives you the access to the profiler's functionality and allows it to collect data from your application. You need to then integrate the Cloud Profiler agent library into your application code. This agent is responsible for collecting profiling data and sending it to the Cloud Profiler service. GCP provides libraries for various programming languages, which can include Java, Python, Go, Node.js, and Ruby. The next step is configuring agent setting, which is an optional step. So if you don't need to reconfigure it, you can skip this step. However, you can customize the agent's behavior through configuration options. Now, this could include setting sampling rates for CPU and memory profiling, defining profiles to capture and specifying the project, and service to which the data should be sent. Then the next step is deploying and running your application. You would need to deploy your application with profiling agent enabled. The agent will start collecting data in the background while your application runs in production. Then there is analyzing profiling data in Cloud Profiler. You must access Cloud Profiler interface in the GCP console, and then you will see flame graphs, call trees, and other visualizations that represent the CPU and memory usage of your application. The next step is identifying performance bottleneck. So you can use different things like flame graphs, call trees, memory allocation. So let's talk about flame graphs. Focus on the widest part of flame graphs because they represent functions that are consuming the most CPU time. Then there is call trees. You need to drill down into call trees to see the sequence of function calls and identify which functions are calling the most expensive functions. Then there is memory allocation. You must examine the memory allocation profile to detect excessive memory usage or potential memory leaks. The last step is optimizing your code. So you would need to target the bottlenecks. Now, based on your profiling data, you must optimize the code in the functions or areas identified as bottlenecks. This might involve improving algorithms, caching data, reducing object allocations, or using more efficient data structures. Then there is redeploying and monitoring. You must redeploy your optimized application and continue monitoring its performance in Cloud Profiler to verify the effectiveness of your optimizations. Let's now talk about the key considerations for implementing Cloud Profiler. So there are various considerations. So there is low overhead, security, data retention, and integration. So let's start with low overhead. Cloud Profiler is designed to have minimal impact on your application's performance. However, you need to be mindful of the sampling rate and profile duration you set to avoid unnecessary overhead. You should evaluate how Cloud Profiler collects performance data during application runtime. It captures CPU usage, memory allocation, and other metrics without significant overhead. You should assess the frequency and granularity of data collection to ensure it provides sufficient insights into application performance characteristics. You should also ensure that you verify that Cloud Profiler integrates seamlessly with application runtime environment such as Google Kubernetes Engine or GKE or Compute Engine instances. Let's now talk about security. You must ensure that Cloud Profiler agent is securely integrated into your application and that sensitive data is not captured in the profiles. You should consider the security and compliance implication of using Cloud Profiler, particularly regarding the collection and storage of sensitive performance data. You should ensure that Cloud Profiler complies with relevant security standards and regulations such as GDPR or SOC 2 and provides adequate controls for data access and encryption. Then there is data retention. Cloud Profiler retains profiling data for a specified period, typically 30 days. You must consider exporting or archiving data if you need to retain it for longer, and there could be circumstances or situations where you may need to retain it for longer time to meet certain compliance standards or certain law. Then there is integration. Cloud Profiler can be integrated with other monitoring and logging tools such as cloud monitoring and cloud logging for a bigger picture of your application's performance. You need to evaluate how Cloud Profiler integrates with the development workflow to facilitate performance analysis and optimization. You should also assess whether it provides actionable insights and recommendations for improving performance based on the collected data. It is always good to review the ease of integration with development tools and IDEs to streamline the optimization process for developers. Just to recap, in this particular topic, we talked about the implementation of Cloud Profiler, in which we talked about 6 steps that we need to perform to implement Cloud Profiler. So we talked about enabling Cloud Profiler API and installing the profiling agent, then configuring agent settings, which is an optional step, then deploying and running your application. The next step was analyzing, profiling data in the cloud profiler, and then identifying performance bottlenecks, and finally optimizing your code if required, if there are bottlenecks. And then we talked about the key considerations for implementing cloud profiler. So we talked about low overhead, security, data retention, and integration. In this topic, we are going to talk about various strategies for log optimization. Managing logs effectively is crucial for troubleshooting, monitoring, and understanding the behavior of your applications and infrastructure. However, unoptimized logs can quickly become overwhelming, leading to storage costs, performance issues, and difficulties in analysis. So, we are going to talk about some strategies that can address these challenges. So, there is multi-line logging, there is log exclusion, log sampling, structured logging, and log rotation and archival. So let's go ahead and look at each one of them in detail in the upcoming slides. So let's first talk about multi-line logging. Now, there could be too many log messages, especially those related to errors or stack traces, and they can span multiple lines. Traditional logging systems often treat each line as a separate entry, therefore making it difficult to correlate related events and understand the full context of an issue. So how do you solve this problem? Multi-line logging allows you to group related lines into a single log entry. This improves readability, simplifies analysis, particularly for error logs and stack traces. So how do you implement this? So there are log agents. Many log agents like FluentD or Logstash provide built-in multi-line parsing capabilities. You can configure them to identify patterns that indicate the beginning and the end of multi-line messages. Then there are custom parsers also. If your log format doesn't fit the standard pattern, you can create custom parser to handle multi-line logging correctly. Let's now talk about log exclusion. Now, some logs might be too verbose, containing repetitive information or data that is not even relevant to your analysis. Now, these logs can clutter your log storage and make it harder to find important information. So, how do you solve this problem? You use log exclusion, which allows you to filter out specific log entries based on various criteria such as log level, message content, source, or tags. Filtering helps reduce the log volume and focus on most relevant data. So how do you implement this? There are two different ways you can do it. So one is the logging agent configuration. You can define exclusion rules in your log agents configuration file, or you can use cloud logging exclusion filters, which help you selectively exclude logs based on defined criteria. Let's now talk about log sampling. Now, there might be high volume of log sources. Storing every log entry can be prohibitively expensive. So how do you solve this? You can use log sampling that allows you to selectively store a representative subset of your logs while capturing important events and trends. So how do you implement this? So there are various methods that you can use. You can use random sampling, which stores a random percentage of logs. You can use adaptive sampling, which adjusts the sampling rate dynamically based on traffic or log volume. And you can also use filtered sampling, which stores only logs that match specific criteria such as errors or high priority events. Let's now talk about structured logging. So there are unstructured logs that are difficult to parse and analyze programmatically. So how do you solve this? You use structured logging format log entries. Now, they would be consistent, machine readable, for example, in the JSON format. Now, this format allows you to easily extract specific fields, perform aggregations, and create custom metrics from your logs. How do you implement this? You use logging libraries or frameworks that support structured logging in your applications, or you can use log parsers. If you have existing unstructured logs, you use log parsers to extract relevant fields and convert them into structured format. Let's now talk about log rotation and archival. Logs can accumulate quickly because there are events taking place in your application or even in your infrastructure. So most of these events are getting tracked. So what happens is when so many events are taking place, the logs tend to accumulate quickly. And once they accumulate, they start to consume large amount of storage space and therefore potentially impact the performance also in many cases. So how do you solve this problem? You implement log rotation policies that will automatically archive or delete old logs. This helps you manage storage costs and ensures that your logging systems remain efficient. How do you implement this? So if you are talking about Linux, you can use log rotate that can manage log rotation. And then there is cloud logging retention policies. You can define retention policies in cloud logging to automatically delete logs after a specific period. Let's now talk about the benefits of log optimization strategies. Now, there are several strategies that you can use, and not all strategies need to be implemented at once. In some scenarios, you might be able to use one strategy. In some scenarios, you might use more than one strategy simultaneously. So, by using these log optimization strategies, there are several benefits you would gain. So, there is reduced cost storage. You will minimize the amount of storage space consumed by logs. Then there is improved performance because you will streamline log processing and analysis for faster results. Then there is enhanced observability because it would focus on most critical log data for better insights rather than scanning through millions of lines of log entries. Then there is simplify troubleshooting, which makes it easier to correlate events and identify root cause of the issue much quicker and in much more efficient manner. Now, having said this, you have to remember that log optimization is an ongoing process. It is not static. You need to regularly review your logs, adjust configurations, and adapt your strategies as your applications and infrastructures evolve. Now, just to quickly recap in this particular topic, we talked about different strategies for log optimization. We talked about multi-line logging. We talked about log exclusions, log sampling, structured logging, and log rotation and archival. In this particular topic, we are going to talk about role of cloud monitoring in tracking application performance. Cloud monitoring is a main tool in GCP's observability suite, and it provides a comprehensive and powerful toolkit for tracking the health, performance, and behavior of your applications. It helps you proactively identify issues, optimize resource utilization, and ensure a seamless user experience. So let's talk about its role and features. So there is metric collection and aggregation. Cloud monitoring automatically collects a wide array of metrics from GCP services like Compute Engine, App Engine, Kubernetes Engine, and many other applications and services. These metrics cover essential aspects such as CPU utilization, memory usage, request rates, error rates, and latency. You can define and collect custom metrics from your applications or infrastructure to track specific indicators important to your business or use case. Cloud monitoring helps in aggregating metrics across different dimensions like time, resource type, and location, which allows you to analyze performance trends over time, compare performance across various components, and identify correlations between different metrics. Let's now talk about dashboarding and visualization. Cloud monitoring provides pre-built dashboards for common GCP services, offering a quick way to visualize key metrics and gain insights into your environment's health. You can also create tailored dashboards to display the most relevant metrics for your applications. You can combine charts, tables, and other visualization elements to create a comprehensive view of your system's performance. Now, the biggest thing with dashboards is they update in real time. Therefore, they help you with a dynamic view of your application performance as it evolves. Let's now talk about alerting and anomaly detection. You can set up alerts to trigger when specific metrics cross predefined thresholds. This allows you to proactively address issues like high latency, error spikes, or resource exhaustion before they impact users. Cloud monitoring also employs machine learning algorithms to automatically detect anomalies in your metrics, even if you haven't explicitly defined thresholds. This helps you uncover hidden performance issues or unusual patterns. You can choose from various notification channels, for example, email, SMS, or pager duty, to ensure alerts reach the right people promptly. Then there is uptime checks and synthetic monitoring. You can monitor the availability of your websites, APIs, and services from multiple locations around the world. This helps you ensure that your applications are accessible to users globally. You can also create synthetic tests that simulate user interactions with your applications. This allows you to proactively detect performance problems and validate functionality. Then there is tracing and profiling. You can integrate cloud monitoring with CloudTrace to gain detailed insights into request latencies, dependencies between services, and potential bottlenecks. You can also use Cloud Profiler to analyze CPU and memory usage in your applications, therefore identifying performance hotspots and optimization opportunities. Let's now talk about the best practices for cloud monitoring. You need to define meaningful SLIs and SLOs. You need to establish clear service level indicators, which is SLI, to measure your application's performance. And you also need to define service level objectives, which are SLOs, to define reliability targets. Then there are custom dashboards. You should tailor your dashboards to visualize the metrics most critical for your specific applications. Then there are alerting strategies. You can develop effective alerting strategies that strike a balance between timely notifications and avoiding alert fatigue. Then there is correlation with logs. You must combine metric data with logs from cloud logging to get a deeper understanding of the causes of performance issues. Then there is RCA, which is root cause analysis. When an incident occurs, you can use cloud monitoring's rich data and visualization tools to pinpoint the root cause and resolve it quickly. Just to quickly recap, in this particular topic, we talked about the role of cloud monitoring in GCP. We talked about various roles and features, which included metrics collection and aggregation, dashboarding and visualization, alerting and anomaly detection, uptime checks and synthetic monitoring, and finally, tracing and profiling. We also talked about several best practices for cloud monitoring, which included defining meaningful SLIs and SLOs, custom dashboards, alerting strategies, correlation with logs, and RCA, which is root cause analysis. In this topic, we are going to talk about benefits of VPC flow logs. Now, what are VPC flow logs? They are the feature offered by GCP that provide a wealth of information about the network traffic flowing in and out of a virtual private cloud or VPC. Now, by capturing and analyzing this data, you can gain valuable insights and unlock a range of benefits. And some of these benefits would include enhanced network visibility, improved troubleshooting, enhanced security, and cost optimization. Let's look at each one of them in the upcoming slides. So let's talk about the enhanced network visibility first. So there are traffic patterns. Flow logs reveal detailed traffic patterns, including source and destination IP addresses, ports, protocols, and packet counts. This allows you to understand how your network is being used and identify potential anomalies or bottlenecks. Then another benefit is network performance. Now, by analyzing the flow log data, you can assess network latency, throughput, and packet loss. This information helps you optimize network performance, troubleshoot connectivity issues, and ensure smooth operation of your applications. Then there is security analysis. Flow logs enable you to detect and investigate suspicious traffic patterns that might indicate unauthorized access attempts, data exfiltration, or other security threats. The next benefit is improved troubleshooting. So there is root cause analysis. When network issues occur, Flow log provide a detailed record of traffic flows, therefore making it easier to pinpoint the root cause of the problem. This allows you to resolve issues faster and minimize downtime. There is debugging network configuration. By examining flow logs, you can verify that your firewall rules, routing tables, and other network configurations are working as intended. This helps you identify and rectify misconfigurations that could be causing connectivity problems. Then there is troubleshooting application issues. Flow logs can be correlated with application logs to troubleshoot issues related to network communication, latency, or errors. Let's now talk about another benefit, which is enhanced security. So there is intrusion detection. By analyzing flow log data, you can detect unusual or suspicious traffic patterns that might indicate a security breach. This enables you to take proactive measures to protect your systems and data. Then there is security group analysis. Flow logs can help you identify overly permissive or restrictive security group rules, therefore ensuring that your network is adequately protected without hindering legitimate traffic. Then there is compliance. Flow logs can be used to demonstrate compliance with security standards and regulations by providing evidence of network traffic monitoring and analysis. Let's talk about another benefit, which is cost optimization. So there is network traffic analysis. By understanding your network traffic patterns, you can identify opportunities to optimize your network infrastructure. For example, you might be able to consolidate resources, reduce unused bandwidth, or adjust routing to reduce costs. Then there is billing verification. Flow logs can be used to verify network traffic billing, therefore ensuring you are only paying for the resources you actually use. Let's now talk about the key considerations for VPC flow logs. So there is sampling. VPC flow logs typically sample a subset of traffic to avoid excessive storage costs. You can consider the sampling rate carefully to ensure you are capturing enough data for your analysis needs. Then there is data retention. You can determine how long you need to retain flow log data based on your compliance and analysis requirements. Then there is security, in which you can ensure flow log data is stored securely and that access is restricted to authorized personnel. Just to quickly recap, in this particular topic, we talked about the benefits of VPC flow logs. We talked about enhanced network visibility, improved troubleshooting, enhanced security, and cost optimization. And then towards the end, we did talk about the key considerations for VPC flow logs, in which we talked about sampling, data retention, and security. In this topic, we are going to talk about two distinct case studies which will focus on auto scaling and right sizing, and then cost optimization and cost governance. So we are going to talk about two different case studies. The first case study is going to be focused on auto scaling and right sizing. Now, in this case study, we have a hypothetical company, which is an e-commerce company, and the problem is that they are facing fluctuating demands on its online platform. Now, because of this fluctuating demand, they don't know how much resources to maintain and how much resources to let go. And this is causing a bigger problem because when the demand increases, they are unable to meet that requirement and provide more resources. And when the demand decreases, they are unable to use that extra resources that is there available to them. So this is basically increasing their costs. Now, the challenges they are facing is high infrastructure costs during peak demand periods. And this is because they have to make that much infrastructure available. Obviously, with more infrastructure, the cost goes up. Then there is underutilization of resources during off-peak hours. When there is a less demand, because they have that much infrastructure and the resources available, they are unable to utilize them. So there is underutilization, due to which there is not much of use of those particular resources that are lying idle. Then there is difficulty in predicting and scaling infrastructure based on demand fluctuations. Now, this is a typical problem with a lot of organizations because they are unable to predict the demands
They keep on having those resources underutilized, and as and when demand increases, they are unable to cope up with the demands because the infrastructure doesn't have that much resources to meet those demands. So this is a particular prediction problem and scaling the infrastructure as and when required. So let's see what they did. So the implementation they did was auto scaling and right sizing. Now, when you talk about the auto scaling, you can implement auto scaling policies for compute resources, so such as Google Kubernetes Engine or GKE clusters or compute engine instances. Now, with the auto scaling policies, they can dynamically adjust capacity based on demand. They configured auto scaling based on metrics like CPU utilization, request rates, and custom application metrics to automatically scale resources up or down in response to change in demand. They also utilized horizontal pod scaling, which is HPA, for Kubernetes workloads and managed instance group MIGs for compute engine instances to ensure efficient resource utilization. Now, they also used right sizing, which is basically analyzing resource usage patterns and right size VM instances to match workload requirements more accurately. They use tools like Google Cloud's right sizing recommendations to identify over provisioned or underutilized VM instances and resized these instances and containers accordingly. Then they also adjusted VM instance type, machine sizes, and configurations based on workload characteristics and performance requirements. This helped them optimize resource utilization and reduce cost. Now, as a result of auto scaling and right sizing, what was the result? So, there was cost saving, which was one of the biggest problems for this organization because of underutilized resources. Now, when they implemented auto scaling and right sizing, the company achieved significant cost savings by eliminating over provisioning and optimizing resource utilization. Then there was improved performance. Auto scaling ensured that the resources were dynamically scaled to meet demand, therefore maintaining optimal performance during peak periods while minimizing costs during off peak hours. Then there is scalability. The company also gained scalability and flexibility to accommodate fluctuations in demand without manual intervention. This helped them with seamless operations and a consistent user experience. Let's now talk about the second case study, which is focused on cloud cost governance and optimization. So we have this company called Shoppies. It's an e-commerce company, and now it is experienced sudden performance degradation on their GCP hosted website. Most of the customers are reporting issues like slow page loads, timeouts, and errors during checkout. Now, due to these errors, the user experience and sales both are heavily impacted. Now, what was the challenge for Shoppies? Now, they had lack of visibility and accountability for cloud spending across the organization because they didn't know how much resources were being used. They had insufficient resource allocation and utilization, leading to wasted cloud spend. Because there were underutilized resources, there were excessive resources which were not being utilized. So obviously the cost was high. There was wastage of resources. Therefore, they had difficulty in enforcing cloud saving best practices and policies. Now, these were some of the challenges that Shoppies faced. And now they had to identify the root cause of the performance degradation and resolve it to minimize further impact on the business operations. So they had to do this. Now let's move to the next slide and see what kind of solution did they come up with. So they came up with cost visibility and cost optimization. Cost visibility, basically they implemented centralized cost management and reporting using tools like Google Cloud's billing reports and cost management APIs. This helped them with gaining visibility into cloud spending across projects and teams. They also created custom billing reports to track costs by project, service, and resource type, and they also analyzed cost trends and anomalies over a period of time. They also established cost allocation tags and labels to attribute cost to specific teams, departments, or cost centers, which help them with
accountability, and cost transparency. Then they also implemented cost optimization. Now, they implemented cost saving measures and best practices to optimize cloud spend and reduce the unnecessary costs. Now, the team at Shopee's utilized tools like Google Cloud's Cost Explorer and recommendations. Now, using these tools, they were able to identify the cost saving opportunities. So, for example, they were able to right size the virtual machine instances, they leveraged sustained use discounts, and they even migrated workloads to preemptible virtual machines. And along with this, they enforced budget alerts and quotas to control spendings and prevent the cost overruns. Now, so what was the outcome of this or the result of implementing cost visibility and cost optimization? They were able to control the costs. They implemented cloud cost governance and optimization practices. With this, they were able to gain control over cloud spending and reduce the overall costs. Then there was also increased efficiency. Because of improved resource allocation and utilization, it led to more efficient use of cloud resources, and it also helped Shopees eliminate wastes, which in fact maximize the return on investment. Then there was compliance and accountability. Centralized cost management and reporting ensured that there is a compliance and cost saving policies, and it also helped them with accountability for cloud spending across the organization. Just to quickly recap, in this particular topic, we talked about two distinct case studies. One focused on autoscaling and resizing, second focused on cloud cost governance and optimization. Case study on monitoring and cloud logging. In this topic, we are going to talk about a case study of an organization called Shopees that has a GCP hosted website. Now, the problem with this particular website is that it has slow page loads, it has timeouts, and there are errors during checkouts, and which is making the customers unhappy. And as an outcome, the customers have started to move out of their website and try to look for other competitors. So that is causing a big problem for Shopees because they are losing customers. Now, that is an adverse impact on user experience and sales, because when your customers move out, you lose sales, and it also puts a bad impact on the user experience. Now, to be able to resolve this, the technical team needed to quickly identify the root cause of the performance degradation and resolve it to minimize the future impact on business operations. And they needed to do this quickly without impacting the overall user experience going forward. So let's move to the next slide and look at what they have done. So how did they resolve this issue? So they did a series of steps. So they did the initial assessment, they did a deeper dive, they did a correlation and analysis, and then they did the root cause identification, and finally the resolution. So let's look at each one of them in detail. So when you talk about the initial assessment, they did it with cloud monitoring. They used the cloud monitoring dashboards where they noticed significant increase in error rates and latency for several key services, including the front-end web server, backend API, and database. Without cloud monitoring dashboard, this would have not been possible for them. They also observed spike in CPU utilization on the web server instances. All this data they were able to figure out with the initial assessment using cloud monitoring. So the next step was deeper dive, which is using cloud logging. Now they have accessed cloud logging to examine the logs for the affected services. So in the initial stage, they identified the services or the systems or the web servers. Now they are going to access the logs for those affected services. The web server logs revealed numerous 502 bad gateway errors, which suggested an issue with communication between the web server and the backend API. Now, that is going to be a major problem to solve, because now if the customers or the users are experiencing 502 bad gateway error, that is going to make them really unhappy. So they also digged out the API logs that showed connection timeout errors, which indicated potential database connectivity problems. So somewhere they are able to figure out that there is some bit of communication error happening in the backend and as well as with the web server and the backend API. So then they moved on to correlation and analysis using cloud monitoring and cloud logging. Now, the team correlated the timestamp of the errors in the web server and API logs with the CPU usage spikes in the cloud monitoring. So there was a pattern that emerged. CPU usage spiked shortly before the error started occurring. So this suggested that the high CPU load on the web server was triggering a cascading effect on the backend API and the database. Now comes the step of root cause identification. So they have done one level of investigation and they have also investigated the web server logs. They also identified a memory leak in the newly deployed application component. Now, this particular memory leak was consuming excessive resources on the web server, which was causing the web server to become unresponsive and leading to the downstream failures. So now, if you go back, so all this started because there is a memory leak problem which caused the web server resource consumption, excessive rather, and then from there onwards there were bad gateway errors, then there were problem with the database communication and all that, and it all happened because there is a memory leak in the newly deployed application component. So how did they resolve this? So the development team promptly rolled back the problematic deployment. So they rolled back that particular component and they implemented a fix for memory leak and redeployed the application component. And of course, this was done after thorough testing. The error rates and latency quickly returned to normal levels and everything started working fine. So now the customers were no longer facing the 502 bad gateway errors or any similar errors or slow page load and all that. So because of a very systematic approach from initial assessment to resolution, there were series of steps that the team followed and therefore they were able to resolve that error quickly and in more efficient way rather than doing hit and try and trying to find out what the issue is, which they would have eventually resolved, but it would have taken them many days to figure out that there is a memory leak. Now, to quickly recap in this particular topic, we did talk about the case study of Shopee's and how they faced a problem with their website, which was hosted on GCP, and how did the team followed a very systematic approach of resolving that problem. In this topic, we are going to talk about error reporting. And we are also going to talk about the practical use cases, and then we're going to talk about an example of error reporting. Let's first talk about what error reporting is. It is a powerful tool that acts as a vigilant guardian for your applications. It automatically detects, tracks, and aggregates errors from various sources, therefore providing insights to help you to quickly diagnose and resolve issues that impact your application's reliability and user experience. So let's talk about the working of error reporting, basically how it works. So when your application encounters an error, it could be a crash, unhandled exception, or failed request, error reporting automatically detects that particular error. It works seamlessly with various GCP services like App Engine, Cloud Function, and Compute Engine. Then there is error grouping. Error reporting intelligently groups similar errors together. This consolidation reduces noise and allows you to focus on fixing the underlying root causes rather than individual occurrences. Then there is error analysis. For each error group, error reporting provides detailed information including error message, stack trace, contextual data, and occurrence timeline. Let's now talk about alerting and notification. You can configure error reporting to send alerts through various channels. It could be your email address, it could be SMS, or even PagerDuty. Now, these alerts are sent when new errors are detected or when the rate of existing errors increases significantly. Now, this helps you ensure that you are promptly notified of critical issues. Then there is integration with monitoring and logging. Error reporting integrates with cloud monitoring and cloud logging, which allows you to correlate error data with other monitoring and logging information for comprehensive troubleshooting. Let's talk about the practical use cases. So there is rapid issue identification. When an error occurs in your application, error reporting immediately alerts you, therefore providing details like error message and stack trace, which enables you to quickly identify and locate the problem. Then there is prioritization and triage. Error reporting groups similar errors, which helps you prioritize issues based on their impact and frequency. You can focus your efforts on fixing the most critical and frequent errors first. Then there is root cause analysis. By examining the stack trace and contextual data provided by error reporting, you can trace the error back to its origin in your code and understand the sequence of events that led to it. Then there is proactive monitoring. You can track the trends and patterns of errors over time to identify recurring problems or areas of your application that are more prone to errors. This enables you to take proactive measure to improve code quality and prevent future issues. Then there is post-incident analysis. You can use the historical data collected by error reporting to conduct post-incident reviews, which is basically post-mortem. This helps you understand the root cause of incidents, learn from mistakes, and implementing preventive measures. Let's now talk about an example of troubleshooting a backend API error. So there is an alert. Error reporting sends an alert about a sudden increase in 500 internal server error responses from your backend API. You basically start the investigation. You navigate to the error reporting and find a new error group for the 500 errors. Then you do the RCA or the root cause analysis. You examine the stack trace. You discover that error originates from a specific function in your code that is trying to access a database that is unavailable. Then you implement the resolution. You fix the issue by adding a retry mechanism to the database connection and redeploy your code. Then there is monitoring. You continue to monitor the error rate for API endpoint to ensure that the issue has been resolved and it does not occur. Just to quickly recap, in this particular topic, we talked about what error reporting is, its working methods. Then we talked about the practical use cases. And finally, we looked at an example of troubleshooting a backend API error. Illustrate advanced log filters and their application in real-world scenarios. In this particular demo, what we are going to do is we are going to create advanced log filters, and we will also see that logging also gives you suggested filters. So we are going to walk through those as well. Now, to be able to use them, what you need to do is you need to select Logs Explorer, and from here, what you will get is the query window. Now, there are recent, saved, suggested, and library. So we are in the query window. Now what I'm going to do is I am going to enter the code for specific advanced log filters, and these would be, so what this filter is going to do is it's going to retrieve specific logs related to Google Compute Engine or GCE virtual machine instances. Now the beauty of this particular code is that it narrows down the vast amount of logging data to focus on activities, data access, system events, and policy changes that directly affect your GCE instance. Now, let's talk about this particular code, what it does. So it says resource type is equal to GCE instance. Now, this part of the filter tells the logging system to only look for logs associated with the GCE instances. Now, these are your virtual machines that are going to be running within the Google Cloud environment. The next line states log ID, which is cloudaudit.googleapis.com/activity. Now, this particular line focuses on logs that record the administrative activities performed on your GCE instances. So, it could also give you output
For example, that includes creating, deleting, starting, or stopping an instance. The next part talks about log ID and then cloudaudit.googleapis.com/data underscore access. Now, this part of the filter looks for logs that detail how data within your GCE instance is accessed. Now, this is going to be important for auditing and security purposes. Then the next part is again log ID, cloudaudit.googleapis.com/system underscore event. Now, this filter includes logs about system level events that impact your GCE instance. These could be automatic restarts, infrastructure maintenance events, or other system generated actions. Then the next part states log ID again cloudaudit.googleapis.com/policy. Now, this filter zooms in on logs that track changes to the policies governing your GCE instances. This helps you monitor who's modifying permissions and configurations. So let's go ahead and run this particular query. But before we do that, notice that there is and, then there is or. Now, and means that this condition, which means this or any of these, which are basically having or in between, need to be displayed as the output. So, what I'm going to do is I'm going to run this particular query. And once I do that, the output is going to be displayed. So what it does is it not only shows the graph, but it also shows the tabular format of the events that have been captured from the logs. Now, instead of going through vast amount of logs, what we have done is we have narrowed down to very, very specific requirement, and that is what we have converted into the query. Now, this query helps us get us what we want, and notice that there are only two key events that are shown to us. Think of going to the logs where there were thousands of events and we had to find only these two. But with this particular query, we are able to narrow down to just two logs in a few seconds of time. Now, let's go to suggested. Now, what logging does is it generates these suggestions for you. For example, GCE instance started. Now, if I click on this, what it is going to give me is it is going to give me the code for this particular query. Now, again, it says resource type is GCE instance, and the instance ID is the instance that is running in the background. And then there is a zone, there is a method name, which is stop, reset, automatic restart, guest terminate, instance, manager halt for restart. And then it is going to find the log ID again, which is activity, or it is going to look for system events. So what I'm going to do is I'm going to run this query. Again, there will be a graph if there are events, and there is going to be tabular format in which we will get the output. Now, let's go back to suggested, and this time I am going to try for something like alerting policy violation, which is SKS001 underscore policy, and I am going to run this. But before we do that, let's go ahead and click on this particular query. Again, what it does is it gives us the details which we have already talked about. So I'm going to go ahead and run this query. So it should generate a series of events from the logs. So notice that the VM name is Jenkins-1-VM, and then stopping the Apache HTTP server. Then there are a lot of other activities that have been performed, or a lot of things that have taken place. So these are basically nothing but events. Now, notice that there are there are red flags. There are invalid SSH key entry, which is expired key. Then there is another similar event. Now, if we just continue to scroll up, we will see there are a lot of other events that have been taken place. So let's go ahead to the top and then see what has happened, what are other events that have taken place. All right, so again, there is over limit and these kind of events that have taken place. Now, these are the things that you can perform with very, very specific queries, and these are advanced level queries that you can write. And in most cases, you can also always check for suggested, where logging generates these queries for you, and you can just simply go ahead and run. Now, the recent tab basically will continue to list the queries that you have executed recently. So there are a lot of other queries that I executed before I shot this demo. Now, these queries have been listed here. Now, just to quickly recap, in this particular demo, what we did was we talked about the advanced log filters. And these filters were basically what we are talking is, and or these were the kind of filters that we used. And then we basically generated specific output with the help of these filters.
In this particular topic, we are going to talk about the strategies for effective use of network tiers. Now, there are two types. One is premium, one is standard. So let's go ahead and talk about each one of them. Let's first start with premium tier. So there is a global network. Now it utilizes Google's extensive low latency global network to handle traffic between GCP resources and end users. And therefore, it ensures quick data transfers between vast distances. Then there is advanced routing. It uses sophisticated algorithms to optimize traffic paths, therefore reducing latency and ensuring a smoother user experience. Then there is high availability, which provides robust redundancy and resilience, therefore minimizing the risk of outage and disruptions. Let's look at the use cases of premium tier. So there is latency sensitive applications. Now, you can use premium tier where applications require minimal delay and it is crucial for them to have low latency. So it could be something like online gaming, real-time collaboration tools, or financial trading platforms. Then there is high traffic websites and APIs. So the next one would be high traffic websites and APIs. There would be services that would need to handle a large volume of requests with consistently fast response times. So you would need to use premium tier in such scenario. Then there is mission critical workloads. Now you would have applications where downtime is unacceptable. So it could be something like a healthcare system or critical financial services. One thing you have to remember, the premium tier is more expensive due to its superior performance and global reach. However, the additional cost is often justified for applications where high performance and reliability are critical. Let's now talk about the standard tier. So there is regional network. It relies on standard internet service providers or ISPs for traffic between GCP resources and users within the same region. So there is cost-effective routing. It employs simpler routing algorithms, therefore optimizing for cost over performance. Let's now talk about the use cases for standard tier. So you would use it for cost-sensitive workloads, applications where cost savings are more important than performance. Then you would use the standard tier. One of the best example I can think of is batch processing. Another example could be data analysis or development or testing environments. Then there is internal traffic, which remains within a single region and doesn't require the global reach of the premium tier. Now, one thing we have to remember is that standard tier is more budget friendly. Therefore, it is a good choice for workload where cost is primary concern and minor latency variations are acceptable. Let's now talk about the strategies for optimization. So the first one is workload analysis. You must understand the origin, destination, volume, and usage pattern of your traffic to determine the appropriate tier. You can define acceptable latency and throughput levels for each application to align your network tier choice with your performance needs. Then there is selective tier use. You can use a mix of premium and standard tier to balance performance and cost. This approach allows you to optimize each workload according to its specific requirements. GCP allows you specifying network tier for individual resources. For example, you can define it for virtual machine instances. You can also tailor the network tier to specific needs of each application or service. You can also employ load balancer or traffic management tools to direct traffic based on criteria such as source, destination, or application specific needs. Then there is regular monitoring and optimization. You can continuously track network traffic and performance metrics to identify bottlenecks and opportunities to switch tiers for improved efficiency. You must continuously monitor network performance metrics, which could be something like latency, throughput, or error rates. Now, these metrics would help you identify bottlenecks and areas for optimization. You can utilize network monitoring and analysis tools provided by GCP to track network performance and diagnose issues in real time. You should adjust network configurations, routing policies, and network tier selections based on performance data and workload characteristics to optimize performance and cost effectiveness. You should also review network costs to ensure efficient spending. You must consider transitioning to the standard tier for workloads where premium tier advantages are unnecessary. Just to quickly recap, in this particular topic, we talked about two different network tiers. So, one was the premium tier, and second one was the standard tier. We also talked about the use cases for both of them, and then we also talked about the strategies for using a specific tier. So, we talked about workload analysis, selective tier use, and regular monitoring and optimization. In this particular course, we did cover a series of topics. We talked about managing logs and metrics with cloud logging and cloud monitoring. And we also talked about configuring the cloud logging agent. And then we did talk about collecting logs and creating and analyzing custom metrics from logs. Then we moved on to talk about setting up and customizing a monitoring dashboard in GCP and also configuring alerting policies based on SLOs and SLIs. Moving further in the course, we did compare Google Cloud's managed service for Prometheus with the other monitoring solutions. And we talked about implementing logging and monitoring access controls. Then, towards the end of the course, we did talk about strategies for optimizing logs and the benefits of enabling VPC flow logs. And finally, towards the end, we did talk about a case study of Shop Ease where we discussed how cloud monitoring and cloud logging help them resolve a particular errors. And then we did talk about applying advanced log filters. So this is the end of this particular course. So what's coming up next? It is a course on optimizing service performance. In this particular course, we did cover a long series of topics. We covered methods for diagnosing service performance issues and using service mesh telemetry. We did talk about strategies for troubleshooting compute resource issues. And then we also talked about addressing deployed and runtime issues with applications. Then, moving on in the course, we did talk about troubleshooting network issues with tools like VPC flow logs and then using Cloud Trace for performance monitoring. And then later on in the course, we did compare the preemptible VMs with committed use discounts. And we also implemented Cloud Profiler to identify performance bottleneck. Then towards the end of the course, we did talk about the role of cloud monitoring in tracking application performance. And we did discuss two case studies which were focused on cost and other things. And then we talked about the error reporting to manage application errors and also the strategies for effective use of network tiers. So, what's coming up next? It would be the course on managing infrastructure as code and immutable architectures. Let's talk about the objectives. So, in this particular course, you will go through various topics under following objectives. So, you will learn the concept of immutable architecture and its benefit in the cloud environments. You will also learn the concepts of using Cloud Foundation Toolkit for infrastructure management. Then you will learn the benefits of managing infrastructure as code or IAC using Terraform in GCP. Then we will talk about deploying infrastructure changes using best practices and blueprints. Then moving on in the course, we'll talk about comparing config connector to other IAC tools, and then integration of Helm for managing Kubernetes applications. Let's move to the next slide and look at some more objectives. So you will also talk about the strategies for creating and managing dynamic environments using Terraform. Then we'll outline the process of transitioning to an immutable architecture in GCP. Then towards the end of the course, we'll talk about the common pitfalls and challenges in implementing immutable architecture. Then we'll discuss a case study of a successful IAC implementation in GCP. Then finally, towards the end, we'll talk about version control systems for managing infrastructure configurations. And then finally, the security considerations in IAC practices. In this topic, we are going to talk about immutable architecture and its benefits. Now, immutable architecture is a design philosophy. It is not a technology and simply a design philosophy where servers, virtual machines, or containers are never modified after they are deployed. Instead of updating existing components in place, entirely new instances are provisioned with the desired changes and the old instances are decommissioned. This new version is typically built from a template or an image that has been thoroughly tested and validated. This approach treats infrastructure components as immutable, meaning they are unchangeable once created. Think of it like a photo album. If you want to update an photo, you wouldn't scribble over the old one. Instead, you would reprint the picture with the desired changes. Similarly, in immutable architecture, we don't modify the live server. We simply go ahead and create a new server from a known good state. Let's now talk about the workings of immutable infrastructure. So there is process of creating image, deploying instances, making changes, and replacing old instances. So when you talk about creating images, this is the first step in setting up immutable infrastructure. You would create a base image of your server or container configuration. This image contains everything needed to run your application, including the operating system, runtime environment, libraries, and application code. Then you move to the next step, which is deploying instances. When you need to deploy your application, you create new instances from this base image. Each instance is an exact replica of the image, therefore ensuring consistency and predictability. Then the third step is making changes. If you need to update your application or infrastructure, you don't modify the existing instance. Instead, you create a new image with the desired changes and then deploy new instances from this updated image. And finally, the last step, which is replacing old instances. In this, old instances are then decommissioned and traffic is redirected to the new instance. This process can be automated using infrastructure as code tools like Terraform or Ansible. Let's now talk about the benefits of immutable architecture in cloud environments. Immutable architecture offers several compelling advantages, particularly when you're talking about cloud computing. So let's go ahead and talk about each one of these advantages or benefits. So there is improved reliability. Each new server instance is created from the same well-tested template, therefore ensuring that every deployment is consistent and predictable. This reduces the risk of unexpected errors due to configuration drift or manual changes. Since instances are never modified, the risk of configuration drift or unintended changes is eliminated. This leads to a more stable and predictable environment, therefore reducing the likelihood of errors and outages. Then there is faster deployments. With immutable infrastructure, deployments are generally much faster. You don't need to go through the lengthy process of updating existing servers. You simply replace them with new ones. Deploying new instances from pre-built images is generally faster than updating existing ones in place. This enables quicker rollouts of new features and fixes. Then there is simplified rollbacks. If a deployment goes wrong, you can easily roll back to a previous version by simply redirecting traffic back to the old instances. There is no need for complex rollback procedures or worrying about incomplete or inconsistent updates. Then there is enhanced security. Immutable architecture makes it easier to maintain a secure environment. Since you're constantly deploying new instances, it is easier to patch vulnerabilities and implement security best practices. By creating new instances from a known trusted image, you reduce the attack surface and minimize the risk of vulnerabilities introduced by manual updates. Then there is scalability. Immutable architecture lends itself well to scaling. You can easily create multiple identical instances from the same image to handle increased traffic or load. Scaling up, which means adding more instances, or scaling down, which means removing instances, becomes incredibly easy with immutable architecture. You can simply spin up new instances from your predefined templates or shut down existing ones without worrying about complex updates or configurations. Then there is cost optimization. While initially counterintuitive, immutable architecture can lead to cost savings. The automation and standardization involved can reduce operational overhead and minimize manual intervention, which translates to lower cost over time. With immutable infrastructure, you can take advantage of thermal resources which are short lived and can be terminated when no longer needed, therefore, reducing your overall cloud costs. Let's now talk about the considerations for immutable architecture. So there is automation, that is the key part of it. Immutable architecture heavily relies on automation tools, something like infrastructure as a code, which can be done using Terraform or any other similar tool. Now, this is needed to manage the creation, deployment, and termination of server instances. Then there is data persistence. Immutable servers don't inherently handle persistent data, which would be something like user information or application state. You will need to use external storage services, something like database or object stores, to manage this data. Then there is initial investment. You need to create and maintain a library of base images, which will require upfront effort. Then there is storage requirements, which is about storing multiple images that would consume storage space. And then there is learning curve. Team needs to adapt to a new way of thinking about infrastructure changes. Now, this brings us to the end of this topic. Just to quickly recap, we talked about what immutable infrastructure is. We then talked about working of immutable infrastructure, which included four key steps: creating images, deploying instances, making changes, and replacing old instances. Then we talked about benefits in the cloud environment. And then finally, we talked about considerations, which included automation, data persistence, initial investment, storage requirements, and learning curve. In this topic, we are going to talk about what Cloud Foundation Toolkit or CFT is, and then we are going to talk about uses of CFT in the infrastructure management. So let's first talk about Cloud Foundation Toolkit. Now, it is a set of open source tools and best practices that are developed by Google Cloud Platform to streamline and automate infrastructure management tasks. It provides a framework and a collection of reusable templates, scripts, and configurations to help establish and maintain a secure, compliant, and well architected cloud foundation. Let's now talk about the uses of CFT in infrastructure management. So there is standardized infrastructure configuration. CFT offers predefined templates and configurations based on best practices and industry standards for setting up foundational cloud infrastructure on GCP. These templates provide a standardized approach to configuring resources such as networks, IAM policies, service accounts, and resource hierarchies. Therefore, they offer consistency and compliance across environments. Then there is automated deployment and provisioning. CFT enables automated deployment and provisioning of cloud resources using infrastructure as a code principles. Users can define their infrastructure configurations using declarative templates such as Terraform or Deployment Manager and deploy them programmatically using CFT's automation capabilities. This streamlines the provisioning process, reduces manual effort, and ensures reproducibility and consistency in infrastructure deployment. The next point is security and compliance controls. CFT includes security and compliance controls to enforce security best practices and regulatory requirements within cloud environments. It provides configurations and policies for implementing network segmentation, access controls, encryption, logging, and monitoring, therefore helping organizations mitigate security risks and achieve compliance with standards like SOC 2, PCI DSS, and HIPAA. Then there is cost optimization. CFT offers cost optimization features and recommendations to help organizations manage and optimize cloud spending. It includes configuration for implementing budget alerts, resource tagging, usage quotas, and cost allocation, which helps organizations to monitor and control cloud costs effectively. Let's now move to the next slide and look at some more uses. In continuation from the previous slide where we talked about various uses of CFT in infrastructure management, in this slide also we are going to continue talking about the uses of CFT. So the next one is operational efficiency. CFT improves operational efficiency by automating routine tasks such as resource provisioning, configuration management, and policy enforcement. It provides reusable scripts, automation workflows, and integration with CI/CD pipelines to streamline DevOps processes and accelerate time to market for cloud-based applications and services. The next one is scalability and flexibility. CFT is designed to scale with evolving needs of the cloud environment, therefore supporting deployments across multiple regions, projects, and environments. It offers flexibility in terms of configuration options that allows organizations to customize and extend CFT's templates and configurations to meet their specific requirements and use cases. Then the next one is continuous improvement. CFT is continuously updated and maintained by Google Cloud Platform with regular releases and updates incorporating new features, improvements, and best practices. Users benefits from ongoing support, documentation, and community contributions, therefore ensuring that CFT remains up to date and aligned with latest cloud technologies and industry trends. Just to quickly recap, in this particular topic, we talked about Cloud Foundation Toolkit or CFT, and then we talked about the various uses in the infrastructure management. So we talked about uses like standardized infrastructure configuration, automated deployment and provisioning, security and compliance controls, cost optimization, and then we also talked about operational efficiency, scalability and flexibility, and continuous improvement. In this topic, we are going to talk about Terraform and its benefits in GCP. Terraform, it is a widely adopted IAC tool that brings a host of benefits to GCP infrastructure management. By defining infrastructure as declarative code, Terraform empowers you to streamline provisioning, improve reliability, and enhance collaboration within your teams. So let's talk about the benefits. The first one is declarative infrastructure definition. Terraform allows you to describe the desired state of your infrastructure using human-readable configuration files, and now this declarative approach focuses on what rather than how, therefore making it easier to understand and maintain your infrastructure code. Terraform keeps a track of your infrastructure's actual state, enables it to calculate the necessary changes to reach the desired state, therefore reducing the risk of configuration drift. Terraform maintains a state file that tracks the current state of the infrastructure, and maps it to the desired configuration specified in the Terraform files. State management allows Terraform to track changes to infrastructure resources, identify differences between desired and actual states, and then apply only the necessary updates during deployments. The next benefit is automation and efficiency. Terraform automates the provisioning, updating, and decommissioning of GCP resources based on your configuration. This eliminates manual, error prone processes and accelerates infrastructure deployment. Terraform automatically manages dependencies between infrastructure resources, therefore ensuring that resources are provisioned and configured in the correct order to meet dependencies. Terraform's dependency graph enables efficient resource provisioning and minimizes the risk of errors or inconsistencies in infrastructure deployment. Terraform ensures that your infrastructure is deployed consistently across different environments, which would include development, staging, production, testing, and it minimizes configuration discrepancies and reduces the risk of human errors. Terraform promotes modularity and reusability by allowing users to define infrastructure configurations as reusable modules. Modules encapsulate infrastructure components with well defined inputs and outputs, therefore, enabling users to create modular, composable infrastructure designs and share them across projects and teams. The next benefit is collaboration and version control. Terraform configuration files can be stored in version control systems like Git, therefore, enabling multiple team members to collaborate effectively on infrastructure changes. Version control provides a historical record of changes which allows you to track modifications, roll back to previous configurations, and audit your infrastructure. You can also integrate Terraform with code review processes to ensure infrastructure changes are peer reviewed and meet quality standards. Then there is multi cloud support. GCP is cloud agnostic, which means you can use it to manage infrastructure across multiple cloud providers. So, we have been talking about GCP, but it can do the same task on AWS and Azure or even in the hybrid environments. Terraform supports multi cloud and hybrid cloud environments and enables users to manage infrastructure across multiple cloud providers. With Terraform, organizations can leverage a single tool and unified workflow to manage infrastructure resources regardless of the underlying cloud platform, which simplifies cross platform deployments and migrations. Then there is reliability, stability, and scalability. In case of failed deployments, Terraform can automatically roll back to the previous state, which minimizes downtime and ensures service continuity. Terraform can detect any manual changes made to your infrastructure and automatically bring it back to the desired state defined in your configuration. Terraform is also highly scalable and flexible, capable of managing infrastructure of any size or complexity. It supports a wide range of GCP services and features, which can include compute instances, storage, networking, databases, and Kubernetes clusters. It allows users to provision and manage diverse cloud resources using a single tool. Then there is cost optimization. Terraform allows you to visualize your infrastructure and its associated costs, therefore makes it easier to identify and eliminate unused or underlying resources. By previewing the changes that Terraform will make before applying them, you can estimate the cost impact of your infrastructure changes. Let's now look at an example, which is provisioning a GCP virtual machine with Terraform. Now, there are a bunch of lines of codes that are given. So the first one starts with resource Google Compute Instance example. This line declares a resource type Google Compute Instance in Terraform. This means you are creating a new virtual machine instance in GCP. Example is the name that you give to the specific resource in your Terraform code. Then the next one is name is equal to my instance. Now, this is the name of the VM instance, but you can change it later on if you require. Then there is machine type, which is E2 standard 2. This is the type of machine specifying its CPU and memory resources, and it is a standard type with 2 vCPUs and 8 gigabyte of memory. Then there is zone, which is mentioned as US Central 1-A. Now, this is the zone within GCP region where the VM will be created. Then the next section in this code is the boot disk. The next section is boot disk. This block configures the virtual machine's primary storage disk. So there is initialize param, which is used to initialize the boot disk when the VM is created. Then there is image is equal to Debian-cloud Debian 10, which specifies that the boot disk will be initialized with the Debian 10 operating system image from Google's image library. Then the next block of code or the next section is network interface. So this configures how the virtual machine will connect to the network. So network is equal to default, which connects the virtual machines to the default network in your GCP project. You can replace this name with a specific network if you have created one. So how does this code work behind the scene? So there is execution, there is resource creation, and then there is state management. When you run the Terraform apply command, Terraform will analyze your configuration and compare it to the existing state of your infrastructure in GCP. Then, if the VM or the virtual machine instance does not exist, Terraform will send a request to GCP API to create it with specified parameters. So we have mentioned the name and the operating system and the boot disk and the network configuration. So all that will be used for resource creation, which is the virtual machine. Then there is state management. Terraform maintains a state file that records the configuration of your resources. This helps Terraform track changes and ensure that your infrastructure is always in sync with your code. So with this is the end of this particular topic. Now, just to quickly recap, in this particular topic, what we did was we talked about the benefits of managing IAC using Terraform in GCP. We talked about various benefits like declarative infrastructure, automation and efficiency, collaboration and version control, multi-cloud support, reliability, stability and scalability, and cost optimization. And then we also looked at a code example which showed how to create a virtual machine using Terraform in the GCP environment. Deployment of infrastructure changes using best practices and blueprints. Now, in this topic, what we are going to do is we are going to use infrastructure as code with GCP Deployment Manager and blueprints. Now, there are going to be certain prerequisites that you need to meet. You need to have an active GCP project, and along with that, you need to have a text editor, which could be something like VS Code, Sublime Text, or it could be anything that can work with YML files. If you don't have any of these, you can invoke the Cloud Shell and then use its editor, and that is exactly what we are going to do now. So I'm going to just go ahead and invoke or activate Cloud Shell. Now, once this gets activated, what we are going to do is we are going to open the text editor, which is open editor button. We just click on it and the text editor will open. Now, in this text editor, what I have done is I have already saved a file name my-vm-instance, and now this particular instance is what is going to get created, whatever is mentioned here. And this, what we are going to do is we have already this file existing in our Cloud Shell. So if I just go back to the terminal and if I just list the files, so I'm going to just go ahead and clear the screen first. And what it says is gcloud deployment manager deployments. So it's going to create a deployment and the create will create the deployment, my first deployment, and then --config my blueprint.yml file, which we just saw. I'm going to go ahead and press enter. And now this should start the process of creating that virtual machine. All right. Now, once this process starts, what we can do is we can come to the, I'm going to just go ahead and close this particular instance of Cloud Shell, and I'm going to just refresh this page. That particular virtual machine that is mentioned, which is my -vm-instance, notice that The process of creation has already started. Now, it's got the external IP, it's got the internal IP, and this process is completed. So no errors, state completed. Type is compute dash VM dot instance, and so it is done. Now, this process is going to take some time to finalize the instance. Now, other than this, now, once if you are done with this, it is always good to clean up your resources so that you don't have to bear the charges. And what you need to do is go back to the Cloud Shell and you need to type this command called gcloud deployment dash manager, then deployments. Again, you need to, instead of create, you need to type delete, and then you need to give it a name which was there earlier we defined. All right. So this is the command that you need to execute. Now this is still getting finalized, but we are going to go ahead and execute this command. All right. So what it says is the following deployments will be deleted. I just go ahead and say yes. So it is working. It's going to take a little bit of while before it deletes out the deployment. And once the deployment is deleted, you will notice that the virtual machine is also gone. So we'll just go back and refresh that page and see if the virtual machine is deleted or not. So let's head back to the compute engine. And if I try to refresh this, so this should still have that VM instance listed. All right, it does. Now, once this process is completed, only that virtual machine will be deleted. So we'll have to just wait and watch. All right, so delete operation completed successfully. And let's see if I just go ahead and refresh this page. So it should not have that particular virtual machine listed. There you go. We can always use the refresh option here, but I usually just go ahead and refresh the entire page. Now, so this is done. This is done, and you've seen how to use a blueprint to deploy a virtual machine. And there are certain best practices that you might want to use. Now, when you are connecting to the text editor, so it was saying that you should connect to the repository. So it is always good to store it in a version control system. So, for example, you can store it in Git, and you should always break down your large infrastructures into smaller reusable blueprints. And before you deploy your blueprints into the production environment, you should test them out. And then you should also use GCP's security best practices while designing your infrastructure. And be mindful of the cost. You need to choose the appropriate machine time and consider using preemptible instances for cost saving. Now, just to quickly recap in this particular topic, what we did was we used a YML file which was called my-blueprint.yml, and we deployed a virtual machine using Google Cloud Deployment Manager. And once the machine was successfully deployed, we went ahead and deleted that particular virtual machine. And then we also spoke about some of the best practices. In this topic, we are going to compare config connector with other IAC tools, and we are going to compare them on different parameters. And these parameters are basically what we are talking about is configuration language, approach, reconciliation, GCP integration, multi-cloud support, and then we'll also look at other features or parameters on which we are going to be comparing, which is tooling strengths, weaknesses, and idle use cases. So let's get started with configuration language. Now, when you talk about config connector, it leverages Kubernetes YAML, which is a widely used format in the Kubernetes ecosystem. This makes it a natural fit for teams already managing applications with Kubernetes. When you talk about Cloud Deployment Manager, it offers a choice between YAML and Python. YAML is simpler for basic setups, while Python provides more flexibility for complex deployments and custom logic. Then Terraform uses its own HCL language, which is basically HashiCorp configuration language. Now, it is designed for describing infrastructure, offering features like modules and functions for reusability. The next feature we are going to talk about is approach. Now, all three tools are declarative. This means you describe your desired state of infrastructure and tool figures out how to get there. Then the next feature is reconciliation. So Config Connector excels here with its Kubernetes native reconciliation. It continuously monitors your infrastructure and automatically corrects drifts, therefore ensuring it matches your desired state. Cloud Deployment Manager and Terraform require manual reruns to apply changes or integration with external tools like CI/CD pipelines to achieve similar continuous reconciliation. Then there is GCP integration. Config Connector and Cloud Deployment Manager both offer deep native integration with GCP services. This means they have direct access to GCP APIs, therefore providing smooth and efficient management. Terraform, on the other hand, offers extensive GCP support through its Google provider. While not as tightly integrated as native GCP tool, it still provides a wide range of capabilities in the GCP environment. Then there is multi-cloud support. Config Connector and Cloud Deployment Manager specifically designed for GCP and do not offer native multi-cloud support. Terraform is a clear winner here. It is designed to be cloud agnostic, therefore supporting a vast array of cloud providers and services. Now let's move to the next slide and look at some more features and the comparison between these three tools. So in continuation from the previous slide, let's continue with the comparison and look at some more features where we are going to compare these three tools. So next feature is tooling. So there is Config Connector that integrates seamlessly with Kubernetes CLI and GitOps tools, which makes it easy to manage infrastructure as code alongside application code. Then there is Cloud Deployment Manager that works with gCloud CLI and offers a web UI for visual management. Then there is Terraform that relies on its own CLI and boasts a large ecosystem of community-created IDE extensions and integrations. Next, we are going to talk about the strengths. Config Connector with Kubernetes native approach simplifies management for teams already familiar with Kubernetes. Automatic reconciliation is a major plus. On the other hand, Cloud Deployment Manager has tight integration with GCP and a well-established reputation, which makes it a reliable choice for GCP-specific projects. Terraform is unmatched when you talk about multi-cloud support. It has a massive community and flexibility, which makes it ideal for complex multi-provider environments. Let's now talk about weaknesses. Config Connector is limited to GCP and requires some Kubernetes knowledge to effectively use in that particular environment. Cloud Deployment Manager lacks the flexibility and extensibility of Terraform, which makes it less suitable for very complex scenarios. Terraform uses HCL that has a steeper learning curve and configurations can be more verbose when compared to YAML. Let's now talk about the ideal use cases. Config Connector is best for Kubernetes-centric environments where teams want to manage GCP resources using familiar Kubernetes tools and practices. Cloud Deployment Manager is well suited for infrastructure-focused projects solely within GCP and particularly those with simple to moderate complexity. Terraform shines in the multi-cloud or hybrid environments where flexibility, customization, and a broad range of supported providers are essential. Now, just to quickly recap, in this particular topic, we compared Config Connector with two more tools, which is Cloud Deployment Manager and Terraform, and we compared these tools based on various features like configuration language, approach, reconciliation, GCP integration, multi-cloud support. And then we continued to the next slide and we talked about various other features for comparison, which were tooling, strengths, weaknesses, and ideal use cases. In this topic, we are going to talk about Helm and its integration into Kubernetes environment. So let's get started. So let's talk about Helm first. Now, Helm is the de facto package manager for Kubernetes, and It is similar to apt-get or yum for Linux. It empowers teams to simplify the installation, upgrading, and management of applications within Kubernetes clusters. So, how does it work? So, there are charts, repositories, releases, and values. Let's first talk about charts. Helm's fundamental building block is the chart. A chart encapsulates a collection of pre-configured Kubernetes resources that define a Kubernetes applications. Now, these resources could be deployments, services, config maps, and so on. Charts are written in YAML and utilize a template-based structure. Therefore, it is easy to adapt them to diverse environments. Then there are repositories. Charts are stored and shared in repositories, both public and private. Helm's official repository, which is Artifact Hub, hosts an extensive collection of community created charts for a wide array of applications. Then there are releases. A release in the Helm environment represents a running instance of a chart within a Kubernetes cluster. You can create multiple releases of the same chart, each with its own tailored configuration. Then there are values, which are nothing but customization knobs for a chart. They allow you to modify the behavior of your application without directly altering the chart's template code. Let's now talk about integrating Helm into a Kubernetes workflow. So you need to first install Helm. You begin by installing Helm CLI or the command line interface on your local machine or environment where you will orchestrate Kubernetes. Then you create or find a chart. You have the option to build your own Helm chart from the ground up. However, there are many applications which have pre-built charts that are readily available in Artifact Hub. You can explore the repository to discover a chart that aligns with your needs. Then, the next step is customize values, which is an optional step. If the default configuration of a chart requires adjustment, you can modify the values in values.yml file to match your specific requirements. Then you install the chart. You use the Helm install command to deploy charts in your Kubernetes cluster. You can provide a release name and optionally override default values as needed. Then there is upgrade and rollback. With Helm Upgrade, you can seamlessly update an existing release with a newer chart version or modified values. If necessary, Helm Rollback provides a simple way to revert to a previous version. Then the last step is managing releases. Helm offers intuitive commands for listing, inspecting, and deleting releases, which help you in getting full control over your deployed applications. Let's now talk about why Helm is essential in Kubernetes environment. So there is simplified deployment. Helm dramatically streamlines the deployment of even complex Kubernetes applications, condensing multiple manifest creation and management tasks into a single command. Then there is repeatability and consistency. Charts ensure consistent deployments across various environments, which help you mitigate the risk of configuration discrepancies and errors. Then there is version control. You can treat your Helm charts like any other code, versioning them back to track changes and effortlessly roll back if needed. Then there is sharing and collaboration. Charts are readily shareable through repositories, therefore fostering collaboration and reusability within teams and across Kubernetes community. Let's now move to the next slide and look at some more reasons for why Helm is essential in the Kubernetes environment. Now, in continuation from the previous slide where we talked about the reasons why Helm is essential in the Kubernetes environment, we are going to talk about more of those reasons on this slide as well. So the next one is customization. Values enable fine-grained tailoring of your application's behavior without the need to directly edit charts templates, therefore balancing flexibility with standardization. Then there is lifecycle management. Helm's comprehensive commands simplify the entire lifecycle of your Kubernetes applications, from installation and upgrades to rollbacks and uninstallation. Then there is dependency management. Helm seamlessly handles dependencies between charts, which allows you to automatically resolve them during installation and upgrades. Then there is CI/CD integration. Helm seamlessly integrates with your continuous integration and continuous delivery pipelines, which allows you to automate version control deployments of your Kubernetes applications. Now, just to quickly recap in this particular topic, we talked about Helm and we also talked about integrating Helm into Kubernetes workflow. So, we talked about steps like installing Helm, creating or finding a chart, customizing values, installing the chart, upgrading and rollback, and managing releases. Then we talked about why Helm is essential in Kubernetes environment. So we talked about various reasons. We talked about simplified deployment, repeatability and consistency, version control, sharing and collaboration. And then we also talked about customization, lifecycle management, dependency management, and CI/CD integration. In this topic, we're going to talk about creating and managing dynamic environments using Terraform. So, we are going to talk about these strategies, and these strategies are basically the foundational strategies that help you utilize the Terraform's flexibility and robust features that makes it the right choice for managing dynamic environments. Now, there would be instances where infrastructure needs to evolve rapidly to meet changing demands. And that is where Terraform can help you. And we are going to talk about these strategies where we can leverage Terraform's capabilities. So the first one is workspaces. Workspaces segment different environments like dev, staging, production within the same Terraform configuration. Each workspace has its own state, which allows independent resource management without cross-environment interference. You can tailor your infrastructure by overriding variables and configurations per workspace, which helps you adapt to unique needs of each environment. You can also seamlessly switch between workspaces using Terraform Workspace Select command. Next one is parameterization and input variables. When you talk about parameterization, you can employ variables to define configurable values for your infrastructure, which would include instance type, regions, and replicas. Now, this promotes code reusability across diverse configurations. For input variables, you can declare them and provide values via command line flags, environment variables, or TF-var files, which helps you with the dynamic adjustments to your infrastructure. Then there is sensitive variables, which are basically something like passwords and API keys. You need to securely store these secrets in environment variables or dedicated secret management systems like HashiCorp Vault, or if you talk about any other cloud provider like AWS, then you can use the secret manager. Next one is modules. You can construct modular Terraform code that encapsulate reusable infrastructure components like VPCs or database clusters. This enhances code reusability, consistency, and maintainability. Modules abstract away implementation details, which help you simplify your main configuration files and improve readability. Then you can also maintain version control of your modules to track changes and ensure compatibility across different environments. The next one is environment variables with conditional logic. You can utilize environment variables to supply distinct values for variables in different environments. For instance, Terraform underscore env variable can differentiate between development and production. Then there are conditional resources. You can leverage Terraform's count or for each meta arguments to create or destroy resources based on environment. We just spoke about the foundational strategies. Now we are going to talk about the advanced strategies. So let's first talk about remote state management. You can store your Terraform state remotely in a shared storage, which will help you foster seamless collaboration among team members on the same infrastructure. You can also implement state locking to prevent concurrent modifications and avoid conflicts when multiple users work on the same configuration. And then there is versioning also. You can select backends offering state versioning to track changes and facilitate rollbacks to previous or prior states. Then there is CI/CD. You can integrate Terraform with your CI/CD pipelines to automate infrastructure provisioning and updates. This empowers you to deploy new changes confidently and consistently. You can also integrate automated tests to validate your Terraform configurations and ensure they produce the desired infrastructure outcomes. Then there is monitoring and alerting. You can establish monitoring and alerting mechanisms to promptly detect infrastructure issues. You can integrate Terraforms with tools like Prometheus or Datadog to collect metrics and trigger alerts. You can also implement automated responses to address common infrastructure problems, which could be something like restarting failed instance or adjusting resources based on demand. In this particular topic, we talked about creating and managing dynamic environments using Terraform. We talked about the foundational strategies, which included workspaces, parameterization and input variables, modules, and environment variables, and conditional logic. Then we also talked about advanced strategies, which remote state management, CI/CD pipelines, and monitoring and alerting. In this topic, we're going to talk about transitioning to immutable architecture in GCP or Google Cloud Platform. Adopting an immutable architecture within your GCP environment is a transformative shift that enhances reliability, deployment speed, and security. So, we are going to talk about a structured roadmap that can help you guide this transition. The first step is assessment and planning. You need to thoroughly document your existing infrastructure components, which would include virtual machines, containers, storage, network configuration, etc. You need to also document their configurations and their interdependencies. You need to determine which components are suitable for immutability. Stateless applications, microservices, and batch processing workloads are often ideal candidates. Then you need to select the tools and technologies to implement immutability. You can consider Packer or Docker for image creation, Terraform or Cloud Deployment Manager for orchestration, and a container registry like Artifact Registry for image storage. You also need to develop a clear plan for reverting to a previous state if deployment fails. This could involve retaining older images or implementing blue-green deployment strategies. Then the next step is image creation and management. You need to create foundational images for your servers or containers that include the operating system, runtime environment, libraries, or any essential configuration. You need to implement a clear versioning scheme of your images to track changes and easily identify specific versions for rollbacks. Then you need to rigorously test your images in the staging environment to ensure functionality and adherence to requirements before production deployment. And you would also need to scan your images for vulnerabilities and implement security hardening best practices to protect against potential threats. The next step is deployment orchestration. You need to use IAC or infrastructure as code to define your infrastructure and configuration as code, therefore ensuring consistent and repeatable deployments. You need to automate the deployment process using CI/CD pipelines or orchestration tools like Cloud Build or Cloud Deploy for rapid and reliable deployment of new images. You also need to implement rolling update strategies to incrementally replace older instances with new ones, which would help you minimize downtime and ensure a smooth transition. Then there is monitoring and logging, which is going to be the next step. You need to establish comprehensive monitoring of your infrastructure and applications to detect issues early and gain performance insights. You need to utilize tools like cloud monitoring. And you would also need to collect and analyze logs from your instances to troubleshoot problems and identify areas for improvement. And for this, cloud logging is a valuable resource here, which can be used for doing this task of collecting and analyzing logs. Then there is continuous improvement. You need to go back and gather feedback from your team and stakeholders to assess the effectiveness of your immutable architecture. You would also need to pinpoint areas for refinement. And Then you continuously refine your image creation, deployment, and monitoring processes to enhance efficiency, reliability, and security. Let's now talk about an example in which we're going to be talking about transitioning a web application. So we start with the assessment. So a web application which is currently running on multiple virtual machines in GCP is experiencing frequent configuration drift due to manual updates. Now with this, there are inconsistencies between virtual machines and which makes it harder to troubleshoot problems amongst these virtual machines. To address this, the team decides to adopt an immutable architecture approach. So as the next step, the team creates a base image for the web server using tool like Packer or Docker, and this image includes operating system, web server software, application code, dependencies, and configurations. Then comes the next step, which is deployment. Now, in this deployment, the team uses Terraform to define the desired infrastructure stage. It creates a template that refines the base image and configures scaling parameters, something like desired number of virtual machines. And whenever an update is needed, a new virtual machine is launched, health checks are performed, traffic routing is configured. So you could have a load balancer which gradually shifts traffic from old virtual machines to the new one, and then the old virtual machines are terminated. Now, this is done when your new virtual machines are healthy and handling traffic. You can easily, without any problem, you can decommission the old virtual machines. Then there is monitoring. The team collects metrics like CPU usage, memory, response time, and so on from the web application and the virtual machines. And this helps them perform proactive alerting on potential performance issues. The team also aggregates logs from all virtual machines, which provides them centralized visibility for debugging and troubleshooting. And team also creates visualization to monitor key performance indicators, which are KPIs, and overall system health using custom dashboards. Now, with these steps in this given scenario and the example that we are talking about, team gains various benefits. So there is consistency. Now every virtual machine runs the exact same tested configuration, which eliminates configuration drift. Then there is reliability. Rolling updates minimize downtime and provide a path for quick rollback if issues arise. Another benefit the team gained was efficiency. Infrastructure management is simplified and automated through Terraform. Then team also gained the benefit of observability. Cloud monitoring and cloud logging provide insights to ensure optimal performance and quickly address the problems. Now, just to quickly recap in this particular topic, we talked about transitioning to immutable architecture in GCP. We talked about steps like assessment and planning, image creation and management, deployment orchestration, monitoring and logging, and continuous improvement. Then we also talked about an example of transitioning a web application where the team was facing problems with inconsistent configuration of virtual machines, which caused a lot of problem and troubleshooting was becoming challenging. So they followed the steps of assessment, image creation, deployment, and they also did monitoring, which is the continuous monitoring, and they were able to resolve these issues. In this topic, we are going to talk about the common pitfalls and challenges in implementing immutable architectures. So let's talk about the challenges of immutable architectures. While immutable architectures offer significant benefits like enhanced reliability, faster deployments, and improved security, they are not without their challenges. Organizations venturing into paradigm shift must be prepared to address several pitfalls. We'll be discussing these distinct categories of challenges: technical, organizational and cultural, and operational. Let's move ahead and discuss them in detail. Let's first talk about technical challenges. So there is initial investment and learning curve. Transitioning to immutability necessitates an upfront investment in tools, processes, and image management practices. teams may face a learning curve as they adapt to a new workflow, or rather workflows, and embrace infrastructure as code or IAC concepts. Then there is image management complexity. Maintaining numerous immutable images and ensuring proper versioning and tracking and optimizing image sizes can become increasingly complex. Security patching and managing ephemeral storage pose additional considerations. Then there is state management. While stateless is an ideal for immutability, stateful applications require careful planning for persistent data management, including external storage solutions or data replication mechanisms. Then there is debugging and troubleshooting. Troubleshooting in immutable environments can be less intuitive than in traditional mutable steps. Teams need to rely more on logs, metrics, and tracing tools for diagnosing and resolving an issue. Let's now talk about organizational and cultural challenges. There is a mindset and cultural shift. Embracing immutability often requires a shift in mindset and practices. Resistance to change, lack of stakeholder buy ins, and organizational inertia can hinder adoption. Then there is legacy system and dependency. Integrating existing legacy systems that are not designed for immutable deployments can be complex and may require significant modifications or workarounds. Then there is collaboration. Effective implementation necessitates close collaboration among development, operations, and security teams. Communication and shared understanding are crucial to make it a success. Then there are operational challenges. So, security and compliance is the first one. Immutable architectures demand robust security controls and compliance measures to mitigate risks associated with continuous deployments and rapid changes. Resource orchestration and automation is the next one. Sophisticated automation and orchestration frameworks are essential for managing resource provisioning, configuration, and lifecycle management in immutable environments. Then there is dependency management and versioning. Maintaining consistency and compatibility in immutable architectures relies on meticulous dependency management and versioning practices. Then there is testing and validation. Comprehensive testing strategies and automated testing frameworks are vital for verifying the correctness, reliability, and performance of immutable deployments. Then there is monitoring and observability. Implementing specialized monitoring tools and observability practices is crucial to gain insights into the behavior of dynamic and ephemeral resources in immutable architectures. Then there is cost optimization and resource efficiency. Proactive resource management, capacity planning, and optimization techniques are necessary to manage cost and ensure efficient resource utilization in immutable environments. Let's now talk about the strategies for mitigation. So, first is the phased approach. Now, you should start small and then there should be gradual expansion. Instead of a wholesale switch, identify a pilot project or a less critical application to begin your immutable journey. This will allow you to test the waters and identify potential issues and refine your processes with minimal risk. Once the pilot is successful, you should progressively expand to more components and applications. This gradual approach enables learning, adoption, and fine-tuning before fully committing your entire infrastructure. The next strategy is training and education. You should ensure your teams are well versed in the principle of immutable architecture, including its benefits, challenges, and best practices. You should conduct or offer workshops, training sessions, or online courses to bridge any knowledge gaps. You should also provide opportunities for practical experience with the tools and technologies involved in immutable architecture. You should encourage experimentation in sandbox environments, pair programming, and mentoring to accelerate learning. Then you should also create comprehensive documentation outlining your immutable architecture strategy, processes, and tools. This serves as a valuable reference for both existing and new team members. Then there is Robust tooling. You should choose a tool like Packer or Docker to automate the creation of standardized and secure images. These tools enable versioning, dependency management, and vulnerability scanning for robust image management. You should also use tools like Terraform or Cloud Deployment Manager to define and manage your infrastructure as code. These tools streamline provisioning, configuration, and orchestration of your immutable resources. You should also implement a monitoring solution like Cloud Monitoring or Prometheus to gain visibility into the health and performance of your immutable infrastructure. You should configure alerts to detect and respond to anomalies promptly. Then you should also conduct automated testing and use these frameworks like TerraTest or Kitchen Terraform to validate your Terraform configurations and ensure they produce the desired infrastructure outcomes. Then the next strategy is thorough testing. You should replicate your production environment as closely as possible in a staging environment. Test your images and deployment processes rigorously in the staging setup before promoting them to production. You should also integrate automated testing into your CI/CD pipeline to validate changes early and often. This includes unit testing, integration tests, and end-to-end tests to ensure your immutable infrastructure performs as expected. You should also introduce new versions of your application or infrastructure gradually to a subset of users or servers. This allows you to assess the impact of change in a controlled environment before rolling them out fully. Let's continue to the next slide and talk about some more strategies for mitigation. Now, in continuation from the previous slide where we talked about various strategies for mitigation, we'll continue to do the same on this particular slide. So the next one is monitoring and observability. You need to aggregate logs from all your immutable instances into a centralized logging system like cloud logging. This enables you to easily search, analyze, and correlate logs for troubleshooting and identifying performance bottlenecks. You should also implement distributed tracing to track requests across your microservices architecture. You should use tools like OpenTelemetry that can help you pinpoint latency issues and optimize performance. You should also collect and visualize metrics from your infrastructure and applications using tools like Cloud Monitoring or Prometheus. You can create custom dashboards to track key performance indicators and overall system health. The next strategy is collaboration and communication. You need to break down silos and foster a collaborative environment where development, operations, and security teams work together seamlessly. This ensures that everyone understands the immutable architecture and its implications. You should also encourage a sense of shared responsibility for the success of the immutable infrastructure. You should implement practices like code reviews, blameless postmortems, and knowledge sharing to build a culture of continuous learning and improvement. Then the next strategy is continuous improvement. You should establish feedback loops to gather insights from both technical and non technical stakeholders. This feedback is invaluable for identifying areas for improvement and prioritizing future enhancements. You should continuously refine your image creation, deployment, and monitoring processes based on the feedback you receive. You should embrace experimentation and adopt your practices as your infrastructure evolves. Just to quickly recap, in this particular topic, we talked about the challenges of immutable architecture and we divided these challenges into three distinct categories, which is technical, operational and cultural, and operational. Then we talked about the strategies for mitigation of these challenges, in which we talked about phased approach, training and education, robust tooling, thorough testing, and monitoring and observability, collaboration and communication, and continuous improvement. In this topic, we are going to talk about a case study about streamlining infrastructure with IAC at Global FinTech. Now, Global FinTech is a multinational financial services company which is facing challenges in scaling its infrastructure to accommodate rapid growth and evolving business needs. Now, global fintech has had phenomenal growth, and due to which they have expanded their infrastructure across multiple locations. Now, just like any typical IT company, they are also facing challenges because previously they did not have any automated environment or they did not have any automation. So they were doing a lot of work manually, and they were doing work like manual provisioning where they were setting up new environments or making changes to existing ones, which was taking a lot of their time, and it was error prone because different people would do things differently, and this was a manual process which eventually brought a lot of inconsistency and configuration drift. They had a lot of virtual machines running, and each virtual machine had its own configuration. So as and when somebody updated, its counterpart virtual machine, which was sharing the workload, would have different configuration than the first one. So these kind of problems started to occur when they started expanding. Then there was limited collaboration. Now there was no centralized repository for infrastructure configurations, which hindered collaboration and knowledge sharing among the teams. Another issue was auditing and compliance. Now, since everything was manual, tracking changes and maintaining an audit trail of infrastructure modifications was challenging. This was making compliance with regulatory requirements even more difficult. Now, global fintech had to do something to overcome these challenges. And let's go to the next slide and see what they did. So, as a solution, global fintech chose to adopt Terraform, and they wanted to use its flexibility, multi cloud support, and declarative approach. The team at Global Fintech used the phased approach to do their implementation. So they started with proof of concept. Now, Global Fintech started with a small scale POC or proof of concept to validate Terraform's capability. They wanted to ensure that it aligned with their requirements. So, as a result, they experimented with provisioning basic GCP resources like virtual machines, networks, and storage buckets using Terraform. Then they moved on to module development. Now, once the POC was successful and they were sure that Terraform will help them achieve what they wanted to achieve, they focused on creating reusable Terraform modules for common infrastructure patterns. And they did this for databases, load balancers, and security groups. This promoted standardization and streamlined their future deployments. Then they moved on to the next phase, which was integration with CI/CD. They integrated Terraform with their existing CI/CD pipeline using Cloud Build. This enabled them to automate the provisioning and updating the infrastructure whenever code changes were committed to their repository. So far, so good. Terraform was helping them achieve all this. And with the help of Terraform, they moved to the next phase, which was environment management. So they used Terraform workspaces to create separate environments for development, staging, production, testing, and they would use these environments for testing and deployment. Each workspace they created had its own state file, which allowed the teams for independent management of resources without affecting other environments. Then they moved to the next phase, which was version control. Now, all Terraform configurations and modules were stored in a version control system, which was Git in this scenario. And Git not only version controlled their configuration files, but it also helped them collaborate and track changes. And it also allowed them to roll back any configuration if there was a need. Now, so the implementation is done, the solution has been implemented. Let's look at what were the results and the benefits of this solution implementation, which involved Terraform. So there was accelerated provisioning. Now, infrastructure provisioning time was reduced by 80%, which allowed the team to deliver faster time to market for new products and services. Then there was improved reliability because everything was through configuration files, so there were less configuration errors. And This allowed the team to build a more stable and reliable infrastructure. Then there was enhanced collaboration. Because there was Git involved, the teams were able to collaborate on infrastructure changes, and they were able to do version control and code review in the Git repository itself. Then there was stronger auditing and compliance. Terraform statefile provided a clear audit trail of all infrastructure changes, which helped the team meet the compliance audits. Then there was cost reduction. Now, eliminating manual errors would obviously save time. It would increase the productivity of the team members because they did not have to deal with manual errors. And this helped the team optimize resource allocation that led to significant cost savings simply because instead of doing the firefighting with the manual errors, the team was able to work on some new features or do something else which was more productive than trying to eliminate manual errors. Just to recap, in this particular case study, we talked about global fintech. We talked about the challenges which were manual provisioning, limited collaboration, and auditing and compliance. Then we talked about the solution, which was in the phased approach. And phases included proof of concept, module development, integration with CI/CD, environment management, and version control. Then we finally moved on to results and benefits, which included accelerated provisioning, improved reliability, enhanced collaboration, stronger auditing and compliance, and cost reduction. Version control systems in managing infrastructure configurations. Now, in this particular topic, what we are going to do is we are going to work with Git repository using our Cloud Shell. Now, here, what I'm going to do is I'm going to first change over to the repository that I have created locally, and then I'm going to just list the files here. And there is test and test1. What I'm going to do is create a new file, which is test2. All right. So this is a blank file. The intent is to just push that particular file into my Git repository. And to be able to do that, let's see what commands we need to execute. So the first command that I'm going to execute is I'm going to add this particular file to the repository, which is git add test2. That is the file name. I'm going to press enter. Then I'm going to go ahead and commit the change. So this is git commit -m. Basically, this is a comment that you want to add that who's changed and what the changes were. So I'm just going to write test file here, and then one file changed. And now it is time for us to go ahead and use another command, which is push this particular file to my Git repository on GitHub. And I'm going to go ahead and press enter. Now, once this is done, now if I simply just go ahead and open my Git repository here, and I'm going to just go ahead and open it up. And we are going to move to the first app repository, and this file should be there, and here it is. And it says now, which means that it has been pushed now. And similarly, what you can do is you can create any configuration file, and using these 3 or 4 simple commands, you can push it out to the Git repository and basically keep your all configuration files in a centralized location. And if you have multiple developers working and they have access to the Git repository, they can do the same, which means your Git repository will do the version controlling for you. Now, if I just open this file, for example, if I just go ahead and take any file, let's say cloudbuild.yml file, I open it up. And here I can check the history by clicking on this history button. And then I need to click on this browse history. Now look at this. All that has been done. It's been tracked, and this is the username, when this was committed, and then you can basically go ahead and open this particular version and view what the changes were. So it tells you 1 changed file with 4 additions, 3 deletions. So once you save that file, again, you can come back here and you can use it for whatever purpose. For example, you can use a YML file for deploying a virtual machines using Cloud Deployment Manager. Now, just to quickly recap in this particular demo, what we did was we created a blank file with the touch command. Then we added that file to the local Git repository. And then finally, we committed the change and pushed it out to the Git repository on GitHub. In this topic, we are going to talk about the security considerations in infrastructure as code practices. So let's get started. Now, there are going to be various security considerations that we are going to be talking about, and we will start this with, we are going to take a look at them in detail. But here we are going to just briefly talk about, so it's going to be secure your code repository, secure your IAC templates, secure your deployment process, and secure your infrastructure. So let's first talk about secure your code repository. So the first one is access control. You need to limit access to IAC code repositories. You should allow only authorized personnel to view, modify, or execute these configurations that are stored in the IAC code repositories. You should use strong authentication mechanisms like multi-factor authentication. Then there is version control. You need to implement robust version control to track changes, therefore enabling rollbacks in case of security issues. You should regularly audit commit logs for unauthorized modifications. Then there is scanning and validation. You need to scan IAC code for vulnerabilities and misconfigurations using static analysis tools or dedicated IAC security scanners. These tools can help you identify potential risks before they are deployed into your infrastructure. Then the next one is secret management. You should never, ever store sensitive information like passwords, API keys, or SSH keys directly into your code. You should leverage secret management solutions like Google Secret Manager or HashiCorp Vault to securely store and reference secrets. Let's now talk about securing your IAC templates. So there is input validation. You should ensure proper validation and sanitization of input parameters used in your IAC templates. This helps prevent injection attacks and other vulnerabilities. Then you should define IAM roles and permissions with the principle of least privilege. You should grant only the permissions that are absolutely necessary for specific tasks. And this is because granting excessive permissions to infrastructure components can lead to unauthorized access, privilege escalation, and potential security breaches. Now, to avoid these issues, you should adhere to the principle of least privilege by granting only the necessary permissions required for each infrastructure resource. Then there is immutable infrastructure. Whenever possible, you should adopt immutable infrastructure practices where infrastructure components are replaced rather than modified in place. This reduces the risk of configuration drift and unauthorized changes. Then there is resource tagging. You should use tags or labels on your infrastructure resources to categorize them and facilitate easier tracking and management. Let's now talk about securing deployment process. Integrating IAC pipelines with CI/CD tools and version control systems introduces potential security risks such as unauthorized access to source code or compromised build environments. Implementing secure pipeline integration practices help you protect source code, artifacts, and build environments from unauthorized access and tampering. And there are multiple ways you can do that. So there should be code reviews. You can perform peer code review of your IAC templates to identify potential security flaws, logic errors, and misconfigurations. Then there is change management. You must implement robust change management procedures. This will help you ensure that all infrastructure changes are approved and tracked, including changes made through IAC. Then there is monitoring and logging. You should monitor your IAC execution logs for unusual activities or unauthorized changes. You should implement robust logging mechanisms to track infrastructure modifications. Then there is automated testing. You should automate security testing of your IAC templates before deploying to production environments. This includes unit tests, integration tests, and compliance checks. Let's now talk about securing your infrastructure. So first one is immutable infrastructure. You should avoid direct changes to deployed infrastructure. Treat it as immutable and replace components rather than modify them in place. Then there is infrastructure drift detection. You should use tools to monitor and detect configuration drifts where deployed resources deviate from the defined IAC configuration. Then there is regular security audits. You must perform regular security audits of your infrastructure to ensure compliance with best practices and identify potential vulnerabilities. Then, last one is the security hardening. You need to apply security hardening best practices to your cloud resources, such as locking down access, patching vulnerabilities, and enforcing encryption. Just to quickly recap in this particular topic, we talked about the security considerations for IAC. We talked about securing your code repository, securing your IAC templates, securing your deployment process, and securing your infrastructure. In this course, we did cover a lot of topics, which included immutable architecture and its benefits, using Cloud Foundation Toolkit, which is the CFT. Then we talked about benefits of managing IAC using Terraform and deploying infrastructure changes using best practices and blueprints. And moving ahead in the course, we talked about config connector and other IAC tools. And then we also talked about integrating Helm to manage Kubernetes applications. Then moving on, we talked about creating and managing dynamic environments using Terraform and then transitioning to an immutable architecture. We did talk about the common pitfalls and challenges in implementing immutable architectures. And then towards the end, we did talk about where the manual errors were causing a lot of problems. And finally, towards the end, we did talk about version control systems for managing infrastructure configurations and then the security considerations in IAC practices. So what's coming up next? It is a course on advanced CI/CD techniques and security practices.